Okay, 100 Integrals by Blackpenredpen. And today, well, not just today, I'm going to probably do this in many different sessions, but I'm going to finish all 100 of them. And so let's just get started. Number 1 is integral of tangent to the 5th times secant cubed x dx. Now, what you may think of doing is, see, these are both odd powers. Now, it might be kind of weird to try to mess with them, but I'll give you an idea. We can take one secant and one tangent out and put it to the side, and that will give us even powers on both of these. And not just that, secant x tangent x is actually the derivative of secant x. So that allows us to do some manipulating with our remaining tangent terms to make a u substitution, right? So that's the plan. And usually whenever you do any integral where you're not exactly certain about what the steps are going to look like, you want to at least have some kind of a roadmap in mind, right? So that's how I'm going to be doing the rest of these integrals. Now, see, there's a secant x tangent x. Now all I need to do is turn this tangent to the 4th power into a secant squared minus 1, and then squared, right? Because tangent to the 4th is just tangent squared, which is just secant squared minus 1 squared. So, making that conversion, we get secant squared minus 1 squared, right? And then here, we still have the remaining secant squared, and also the secant x tangent x dx. Here, now we can just make a u substitution since all of these are in terms of secant, and this is just our differential. So let's let u equal to secant. And then differentiating both sides implicitly, you get du is equal to secant x tangent x dx. So that's nice, right? So now what we can do is just plug in a u wherever we see a secant. So here we have open parentheses, and then there's a secant there, but remember it's squared, and just like that, minus 1, and then squared, right? Here we have a secant squared, so we're just going to write down a u squared. And the secant x tangent x dx, you can see we can just replace it with du since they're equal to each other. Now what we need to do is integrate this, and for this, let's just combine it, right? So because they're both squared, you're able to just move the square to the outside like this, right? So this entire thing would be multiplied by that, and then these are both squared, so we can do that, and then we just multiply this into that. Actually, no, you know what? Let's just expand it out. There's no need to make this that complicated. You would do that if you were factoring it or something, but I think for now, the best course of action is just simply to expand it out. So here we had, I'm just going to write down what we originally put down. Right. And then u squared. So to expand this was just binomial squared, right? And then we just raise everything inside 2 powers because you're just multiplying in a u squared on the side. So that's pretty simple. So expanding this out, you would get u to the 4th, right? But you raise it by 2, so now you get u to the 6th. Minus 2u squared, but you raise it by 2 again. And you would end up getting minus 2u to the 4th. And then finally you have just 1 squared, which is 1. Raise it by 2 powers, you get u squared. And then with respect to u, now all we got to do is integrate, since this is just a very simple power rule case. So integrating this, we get add 1 to 6, divide by the new power, you get 1 over 7, u to the 7th, but u is just secant, so I'm just going to plug it right back in. And we don't need this parentheses anymore, these parentheses. All right. Same idea here, raise the power by 1 divide by it, you get minus 2 over 5. And of course, u is just secant, so I'm going to replace it. And then our new power is to the 5th power. And then finally, our u squared term, integral of u squared, is very simply 1/3 u cubed. And of course, u is just secant cubed. And then add c, since everything is fully simplified, right? And it's all in terms of x again. So yeah, that is our first integral. And this might take a while, a lot longer than he does, because I'm going to work slower through these. Okay, number 2. We're going to stick with trig functions, but instead of messing with tangent and secant, we're going to mess with sine and cosine. So number 2 is the integral of, on top we have cosine of 2x, and on the bottom we have sine x plus cosine x. And I'm pretty sure a cloud layer is passing over right now, so that's why it suddenly got dark, but forgive the darkness. I'm going to just switch on a light. Okay, so here, notice that cosine of 2x, you're able to rewrite it in terms of an equivalent form, and that is just cosine squared minus sine squared, right? And then on the bottom, you solve this. Now, factoring, this is a difference of squares. Factoring this, you get cosine x plus sine x, cosine x minus sine x. And actually, those would cancel, right? Cosine x plus sine x, and this on the bottom would cancel. So you're left with the second factor, which is just cosine x minus sine x. So in reality, this entire thing simplifies down to cosine x minus sine x dx, right? And then integrating cosine, of course, you get sine. And then integrating negative sine, you get positive cosine. Plus c. This is pretty cool. It reduced down really nicely. Okay. Yep. Number 3 is the integral of, on top we have x squared, it's minus 1, right? X squared plus 1. And the bottom, we have an irreducible quadratic on top and an irreducible quartic on the bottom. Minus, right? Minus x squared plus 1. So what do we do for this one? You might think maybe try to factor the bottom, which you can do, right? And then do partial fractions. Or, because it's a lot easier this way, all we need to do is divide everything by x squared. It's like a shortcut, right? You don't necessarily need to do all the complicated algebra if you know the shortcut. And the shortcut here is just dividing everything by x squared. So dividing the top by x squared, you get 1 plus 1 over x squared, right? And the bottom, x to the 4th over x squared gives you just normal x squared. X squared divided by x squared, you get 1, and then the 1 divided by x squared, you get 1 over x squared. And the reason why we did this is because if you pay attention to the new denominator, this is almost actually a perfect square, right? The middle term, the constant term in this case, is actually off by 1. So what we can do is we can add 1 and subtract 1 to the bottom. So what we end up getting is x squared, and we subtract 1, right, to be able to get minus 2 plus 1 over x squared, and that gives us our perfect square. But remember, we had to add 1 back to maintain equality, and then, yeah, on the top, we still have that guy. Now, what we can do on the bottom is simply rewrite this as a perfect square. And what you notice after rewriting it is that the top is just the derivative of the inside of the square. So rewriting that, you get x minus 1 over x squared. And then on top, you solve that. Now what you may notice is that the derivative of x is 1, and the derivative of negative 1 over x is positive 1 over x squared. So let's make a u substitution. We would let u equal to whatever is in the square. We have x minus 1 over x. Du would equal to the top, right? So it would be 1 plus 1 over x squared dx. And right, now let's just rewrite it, because you would notice that this is a very familiar form. And on top, I'm going to write this as just a du, right? If we have 1 over sum of squares, right, then this is just inverse tangent. It's a pretty standard form, so this is just inverse tangent of u because you're in the u world. And of course, u is just that. So I'm going to just write that into the argument of the inverse tangent. Yeah, and then add c and you're done. Pretty cool how this went from a rational expression into, well, another kind of, well, yeah, I think it's pretty interesting. Yep, there you have it. That's number 3. And we're going to do more stuff into inverse tangent later. There is a standard formula for the sum of squares in the denominator. However, I'm not going to do that quite yet. This eraser's getting dirty. Okay, number 4 is our first exponential. We're getting exposure to literally everything. X plus e to the x squared dx. You see it's squared. You can't really do a substitution on the inside since that will result in some weird crap happening. So my suggestion would just be to simply expand it out, right? So expanding that out, we get the square goes onto the x. So you got x squared. And then you would have 2 times the first term times the second term, which gives you 2x e to the x, and then the third term, e to the x all squared, just gives you e to the 2x. Close the parentheses and write in a dx, right? And you're actually able to integrate, so I'm not going to do this, but we have to do it term by term, right? So integrating x squared isn't all that bad. We just get 1/3 x cubed, right? And then integrating the last term isn't all that bad either, because you just use the reverse chain rule, divide by 2, right? So you get 1/2, and then since it's an exponential function, it stays, it repeats, right? However, this is a little bit weird. Now, what I would do for it is, of course, integration by parts. So, because you're able to differentiate one and have it eventually go to 0, and the other one is very easy to integrate. So here, let's just differentiate 2x, and then differentiating 2x, you get 2. Differentiating again, you get 0, and integrating, you would have the other factor, right? E to the x. And then you would integrate this and do it again, right? It's always just e to the x. Now, I'm going to be using this setup for integration by parts, not UDV, because it's a lot easier to do it multiple times in a row, whereas UDV, you have to do it once at a time. So this is the fastest way to do it. So now we just multiply the diagonals, and typically we'd integrate the final row. However, because there's a 0 here, the integrand would just be 0, and integrating 0 just gives you a constant. So we multiply these two and those two. So 2x times e to the x, right? And then we have a minus sign, 2 times e to the x. And then add c, and yep, there we have it for this one. So, yeah. That's number 4. This eraser, I don't actually reuse these all that. Well, I don't buy new ones all that often, so I just reuse them. And I just wash it, you know. It helps a bit, at least, with how clean you can get the board. Number 5 is another trig integral. We have the integral of cosecant cubed times secant. Now this is trig. It might seem kind of easy. However, notice that cosecant and secant, they don't really work well together like sine and cosine do, or secant or tangent do. So here, what I'm going to actually do with this is just write them all in terms of its primitive form. Whenever you have a trig function that doesn't have, whenever you have an integrand that doesn't have trig functions that work nicely together, you always want to rewrite them in its most primitive forms in terms of sine and cosine. Right? So, cosecant, you get 1 over sine, and don't forget the cubed, right? Because cosecant, and I'm going to be using this a lot, is just the reciprocal of sine. This is a trig identity you typically learn in pre-calc. And secant, of course, is just the reciprocal of cosine. And yeah, you close that. Now, what you end up getting, if you just multiply the fractions together, 1 times 1 just gives you 1, and the bottom just multiplies together like that. So, that's your new integrand. Now, you can see it's still not all that nice. So what I'm actually going to do is whenever you see a 1 somewhere here and you think it might help, it probably will. So let's replace the 1 with the sine squared plus cosine squared using the Pythagorean, because, yeah, Pythagorean identity. Sine squared plus, x plus cosine squared x. And then you divide it. The bottom stays the same. Okay, so now, because there's actually stuff on top to work with now, let's split this into 2 fractions, right? So the first one would be sine squared over this denominator, and the second one would be cosine squared over this denominator. So, to simplify the first one, sine squared over that, you just get 1 over sine x cosine x. And in addition to splitting the integral, I'm also going to be in addition to splitting the fraction, I'm also going to be splitting the integral. So we have 1 over sine x cosine x dx. And the second term, we just have 1 cosine left on top and then the sine cubed on the bottom, since one of the cosines cancel. So you would add a cosine on top and then a sine cubed on the bottom. So this second term, you might see what you can do here. Just make a u substitution where u equals sine, because the top, cosine x dx, is just your differential. So that's relatively simple. So I'm actually going to be working on this one right now. There's 2 ways to approach it. Either you recognize the pattern on the bottom is actually very similar to sine of 2x. You multiply it in a 2 on the top and the bottom, and what you end up with is just 2 over sine of 2x, which is probably the easier way out, but you are able to do a lot of simplification with your final result, right? Or you're able to do what we did here again, right? Rewrite the top as the Pythagorean identity, because, besides doing the trig identity stuff, there's not much we can do with that. So I'm going to do that because that's the solution that Blackpenredpen provided, and that's the solution I came up with the first time I did this a long time ago. So this is just sine squared plus cosine squared. I'm going to get a new red pen after this. And sine x cosine x dx. And we'll deal with the second term later, but for now, notice if you just split it, then you get some nice cancellation. So, and I'm also going to be splitting the integral again. So, first term, you get sine squared over sine x cosine. One sine cancels out with another sine. You get sine over cosine, which is, using a trig identity, we get tangent. Okay, and then the second one, what you get is 1 one of the cosines cancels with the cosine on the bottom. You get cosine over sine. So that's just cotangent. Right. So in reality, this boils down to that. Right. Okay. Secondly, let's do this. So here, let's make a substitution. Let u equal to sine, as I mentioned earlier, and then differentiating both sides, you get du is equal to cosine x, which is, dx, which is what we have on top. So here, you can just replace the bottom with u cubed, right? And then the top cosine x dx is just du. So now let's go on to the next line. So what we can do with this is, you can see it's just reverse power rule, but to make it a little bit more intuitive to work with, let's actually write this in terms of just a normal exponent. So, the u would technically stay the same, right? And the exponent now becomes -3. And then multiply by du. Alright, these three are all standard, right? This one, what you can do to prove it, I guess, I'm not gonna actually do it right now, but what you can do is split this up into sine over cosine, as I said earlier, and then you see that the top is the derivative of the bottom, almost, right? And then that's how you do that. Same idea with this, right? But for now, I'm going to just use the standard results. So here we get the natural log of absolute value of, I think this is secant x, right? Here you would get the natural log of the absolute value. You would first subtract, right? The natural log of the absolute value of, let me think. Oh, sine, cosine. Yeah, sine. No. Actually, this would be cosecant if you have the negative sign out front. But, of course, using the log property, what you're able to do is put it up in the exponent, and then you get cosecant x to the -1. Not inverse cosecant, right? And then that's just 1 over cosecant, which is just our sine. So, yeah. And then for this one, of course, is just a case of chain rule, reverse chain rule. So bringing the so first adding 1 to the -3, you get -2. Bring the -2 to the front, so you get -2. And then u is now to the -2. Sorry, no, you don't bring it to the front. You actually divide it. So it's 1 over 2. Right, so that's that. And then these two, you're able to simplify more using log properties. So because this is subtracting off cosecant, this would go in the denominator, right? So this is just secant over cosecant. And if we just do some math up here, I'm going to write it like this because in this case, we don't really need to know what the argument is, since everywhere here, the argument of the trig functions is just simply x. So secant is, of course, 1 over cosine. And then you want to divide that by 1 over sine. Okay, so now to simplify this, just multiply the top by sine, cosine, right? So the cosine cancel out. On the top, you're left with the sine. And in the bottom, the cosine and the sine, the sine and the sine cancel out, so you're left with the cosine. So in reality, secant over cosecant is just tangent, right? So this would give you natural log of, right, just tangent, it should be. Unless there's been an oversight, which I don't think there has been. Yeah, seems this is right. So, now absolute value of tangent x. Right, and then up here what we do is just, first of all, this is u to the -2, right? So this is 1 over 2u squared in the denominator. And then u is, well, you know what? In fact, look at it like this, right? u is just our sine, right? Sine, the reciprocal of sine, right, is just cosecant. So this is 1/2 cosecant squared, because the negative sign is what allows you to do that. So, I'm pretty sure we're missing a value here. What are we missing? Why are we missing it? What? Dude, no. Nope, I don't. No, never mind. We're not missing value. Yeah, this is correct. I thought there was 1 plus tangent x on the inside. It's not. It's just normal. So now let's deal with this. Earlier, as I was saying, we have 1/2 times cosecant squared x. So now everything's in terms of x. Add c, and you are done with this integral. Okay. Yeah. All right. Next, we have a nice substitution to make in number 6. So number 6 is less about what you can do initially, but more about like the steps after doing the substitution. Because most of the time, the substitution is the difficult step. Here, it's pretty easy to spot. Very easy to spot. Bottom, you have sine squared x minus 5 sine x minus 6. And on the top, you have cosine x, and then this is with respect to x. There's a substitution here that can be made, and actually this is pretty nice. So think about what a roadmap of this integral would look like. So, I mean, the substitution is pretty easy. Everything here is in terms of sine. And then, of course, we have a cosine dx. That's just our differential. So let's do that first. And then secondly, what you may notice is the bottom is factorable. And then you can do partial fraction decomposition from there. So that's what the roadmap would look like. So let's just make the substitution. Let u equal to sine, right? And then, of course, differentiating, you get cosine x, and then dx. All right, so here on the bottom, sine is just u, and of course in the first term it's squared, and then second one is minus 5 times sine, which is u, and then there's just a minus 6. Cosine x dx is just 1 times du, right? 1 times du is just cosine x dx. So I'm going to write a 1 up here and a du down here. Now, this is a factorable quadratic, right? And what you factored into is you have a u minus, what was it, 6? Yeah. Right, actually, I should be writing this all in red. So on the bottom, you get, well, let's write the top first. 1 over u minus 6 times u plus 1, right? And then du. So now you have two factors on the bottom and an innocent looking top. So let's just do partial fractions. So we want to break this into two fractions. Yeah. So the first fraction is going to have the denominator of the first factor, right? And of course the top needs to be 1 degree less, so we're going to have it be a constant over the first factor. And then the second one is the same idea, right? So we're going to have a constant over our linear factor. Now to be able to solve for this, there are two methods. Either you can use a shortcut, which is our cover-up method, or you can just use algebra. And I think for this first time, I'm going to be using algebra since it's a lot more rigorous in proving what A and B actually are. But if you would like to know a shortcut, I'll introduce that in the future since we have a lot more to go. So, multiplying both sides by a common denominator, which is just whatever's in the denominator here, what you get is that in the first term, u minus 6 cancels with u minus 6. So you're left with a u plus 1. That's multiplied in, right? So you have your a, but you have to multiply in a u plus 1. Secondly, in this term, similar thing happens, except it's a u plus 1 canceling with the u plus 1. So you just have b times u minus 6. Now all you need to do is expand it out. I'm going to start writing this in black. Well, I'm not going to do that. Here. A times u is just au. A times 1 is just a. B times u is bu. B times negative 6 is negative 6b. Okay, so now what? Now what you want to do is group these by term degree. So we have 2 linear terms and 2 constant terms. The linear terms is au and bu. So we'd actually want to group the coefficients. We have a plus b times ru. And over here, we just have, we just group our constant terms, right? So a minus 6b. And of course, this is equal to 1. Now, what you notice is that the left-hand side and the right-hand side have to be equal, right? Since we already established that here, here, here. Now, what that means is that, well, now you notice that on the left-hand side, there's no linear term. That means there can't be a linear term on the right-hand side either, since they're equal. So that means this coefficient has to equal 0. So our first equation in the system we're about to set up is that. Second one is that this is our constant, and then the constant on the left-hand side is 1, right? So that means the only constant on the right-hand side has to be equal to the only constant on the left-hand side. Therefore, a minus 6b has to be equal to 1, right? Now, you can solve this however you want to. Here, it's actually really easy. Just use elimination, right? So a minus a is 0. B minus negative 6b is just b plus 6b, which is 7b. And then 0 minus 1 is just simply negative 1. And then divide 7 on both sides, you get that. B is equal to negative 1 over 7. So that is our answer number 1. Okay, what about A? Now we'll just plug it in. In fact, let's do this mentally. Plug negative 1 over 7 in here. You get A minus 1 over 7 is equal to 0. Add 1 over 7 on both sides. You get A is equal to 1 over 7. So that means we get A is equal to normal 1 over 7. This thing is absolutely running out. Damn. Okay, so now all we need to do is plug these guys back into here. Okay, so what we end up getting is, since we see that this is equal to this is equal to that, then that means this is really just equal to that. So we're able to put it in our integrand. So A is just 1 over 7. And then, of course, we just write down over u minus 6. And then we add on, B is negative 1 over 7 over u plus 1. And it's still with respect to u. But now you can do mental math. You can make a u substitute. You can make any kind of substitution in your head where the denominator equals your new variable. You see that du is equal to your new differential, right? So what you really get is just a natural log, since the top is some constant times the derivative of the bottom. And in this case, the constant's 1 over 7. So you can factor out a 1 over 7, and what you end up getting is 1/7 times the top becomes 1 here. And if you want to, you can bring this negative down here, and then here, the 1 over 7 just becomes 1. So you can do mental math, right? This is just 1 over 7 times the integral of that, which is just a natural log of the absolute value of u minus 6. And then let's actually just distribute the negative 7 straight back in. So here we have a minus sign. We're going to be putting down a minus sign here too. And then 1 over 7 times the natural log of u plus 1, right? Okay, so now what we can do is we're actually able to, let's go straight back into the X world. So it's not all that difficult. But what you notice is that for u, where u is equal to sine, right? Sine wave kind of looks like this. It's crooked on the left-hand side, but what you notice is that the absolute minimum is -1, and the absolute maximum is 1. So u minus 6 is shifting the entire thing down by 6, right? So that means all of this is going to be negative, right? So what absolute value is really doing is taking the positive y values of all of these, and what that is doing is just multiplying it by -1 or dividing it by -1, right? It's flipping it over the x-axis. So here what we can do is we can actually just reverse the order of subtraction, since you want to take the negative of this because everything is being flipped by the absolute value. So, and the reason we're doing this is so we can get rid of the absolute value, right? So what we actually get is 6 minus u, where u is sine. And then, of course, the same concept applies to this second one. Now, the second one, notice that shifting the wave up by just 1 unit makes it so that the absolute minimum is just 0, right? So you just get this. Or no, this is slightly incorrect because it's incorrectly phase shifted, but you get the idea. We're just talking about the range. So the least it can go is 0. So the absolute value being there is not really doing anything because this is always non-negative. So we can just get rid of them, straight up get rid of them. And then u is, of course, sine. Right, and then we do +1, and then close this. Right, and then there you go. And then feel free to combine the natural logs if you would like to. But I think this looks nicer since, well, you can't really do anything with them combined. Yeah, that's it for number 6. Okay. Number 7. First, I need to check if my phone is still recording. Indeed it is, thank God. Okay, number 7 is integral of 1 over the square root of e to the x dx. And this one's actually pretty simple. See, we have an exponential function here, right? Let's just write everything, and because this is a square root, it's just really exponent of 1/2. Let's write everything inside of the exponent, inside the argument of the exponential function. So, since it's the denominator, we can flip it up and just make the exponent negative, right? So we have an e to the negative, right? And then we have something x. And because this is a square root, this is just an exponent of 1/2, basically, right? So 1/2. And then we still have to multiply in our x dx. So this is simple because it's just an exponential function, right? Here, the input is just linear, so you're able to do reverse power. Not reverse power rule, reverse chain rule. So you divide by whatever's up there, which would just give you -2 multiplied by we multiplied by this because it repeats, right? But we saw that this is really just equal to that, right? So we have a -2 as our coefficient, and then we have to multiply by this. So this is really just -2 over the square root of e to the x. Add c, you're done, because this is just an exponential function. Pretty simple. Okay. So the next one is another one having to do with exponentials. So let's just write it down first, because I don't remember explicitly how to solve this. looks kind of intimidating at first, but let's just make a substitution real quick. We see that e to the x dx is just our differential if our u were to be just e to the x, right? So let's just make that substitution and hope it works. So, we would let e to the x equal to u, and then differentiating both sides, you get e to the x dx is equal to our du. So, as a result, e to the x dx, we're going to ignore that for now since that's our du. We'll put that at the very end. On the top, we have the square root of e to the x minus 1. E to the x is just u, so this is really just u minus 1. In the bottom, we have e to the x plus 3. E to the x is just u, so it's just u plus 3. Okay, and then what about our du? We'll just put that down. Right, this is just e to the x dx, and we just got rid of the e to the x and made it that. Okay, what about now? So, now, what do we do? I think it's possible to just make a substitution where this entire, where the entire root is just our new variable. Let's call it t, right? Now, the reason why we're doing this, why we know we can do this, is because whenever you make a substitution and the variable or the expression you're substituting is a root with a linear term inside of it, you always know it's going to end up looking nice. And it's for reasons I'm about to demonstrate. So we would let t equals to root of u minus 1. Right, and then differentiating both sides, you get dt is equal to 1 over 2 times the root of u minus 1. And because the chain rule, we don't really multiply anything in, except for du, right? Okay, now for this one, notice that the bottom right here is really, this root in the bottom is just our t. So, in fact, what we're able to do is just rewrite this as 1 over 2t. And to isolate du, because there's just a du here, there's nothing to cancel with, we can multiply this on both sides. And what we get is that 2t dt is equal to du. So, yeah. So on the top, we just have a u, right? And then, sorry, no, not u, t. Our new variable is t. We have a t over, and then to solve for the bottom, let's just algebraically manipulate this. Squaring both sides, you get t squared, and then adding 4 on both sides, you get this is equal to u, right? So the bottom is just t squared plus 4. And then what you get is you just multiply in I'm going to put the 2 outside first of all, right? And then 2t, so that makes it t squared, and then dt, right? Really nice. Then what you can do with this is add a 4 and then subtract a 4. Because what you're doing in essence is adding 0. However, what you see is that these two terms up front here and then this denominator, they cancel to make a 1. So coefficient stays, but integral, you end up with a big 1 here. And then you still have minus 4 over that. So yeah. Alright, so in fact, you're able to integrate this right here, right now. And it may not look like it to a beginner, but you are. This is still sum of squares, you might say. Let's introduce a trig substitution. And that's how you would solve it. However, this is actually standard. There's a formula for this, and no one wants to go through the trig sub every single time, right? So let's derive how this is actually equal to inverse tangent of something and how the formula actually works. So let's say we just have integral of 1 over x squared plus a squared, right? With respect to x. Since what we're doing is just sum of squares right here and right here, right? And then the 4 up here, you can just factor it out. No, not factor it out. You can just bring it outside of the fraction, right? So in reality here, you would have a 4 sitting there, right? But for now, this is like our general form for the integral of 1 over sum of squares. To do this, we, as I said earlier, we do a trig sub. We would just let, and for it to be nice, because we have a sum of squares, we would need to use tangent theta, right? Since tangent theta plus 1 is just secant squared, and that'll let us do some nice trig. So we would let x equal to, and in all cases of trig sub, we'd want to be a times our function that we're going to be using, and then differentiating both sides. You get a secant squared theta. Okay, so let's just and sorry, no, there's a d theta here, but let's replace 1 times dx with just that. So on the top we have a times secant squared theta, right? In the bottom, and you have a d theta on the side. On the bottom you have a tangent theta into x, right? But distributing the square, you get a squared times tangent squared. So you get a squared tangent squared theta. And then you would add on your pre-existing a squared. Notice on the bottom, the reason why we have an a here is because now, after implementing it, we're able to factor it out. So let's do that. And in addition to doing that, let's also bring the a on the numerator outside. So we get a on the top, and then we factor out an a squared on the bottom, right? And then we'll simplify this later, but for now, on the top we have secant squared. On the bottom, you just left with tangent squared plus 1, which is secant squared. Right? Okay. Now simplifying the outside, you just get 1 over a, really simple. On the inside, you just get integral of d theta, which is just theta. Okay, now what's theta? This is pretty simple. All you do is first divide by a on both sides. So you get x over a, right, equals to tangent theta. And then you take the inverse tangent. So you get inverse tangent of x over a. And then this is equal to simply theta, right? So of course this is equal to 1 over a times the inverse tangent of x over a. So that's how you would manually go back from sum of squares to your final result. But this is a formula to be memorized, since this is a lot of steps. No one wants to do that every single time you're computing an integral. So here we'll just be using that. So the first term is relatively easy, right? You just get, I'm going to be distributing the 2. Integral of 1 dt is just t. So you get 2t as your first term. Minus, let's distribute it into 2, and then also multiply it with 4. You get an 8. And then you would get this, right? In our case, remember you want sum of squares, so you want x squared plus a squared. That means 4 is our a squared. That means a is 2. So you want to divide it by 2, right? And then you just have an inverse tangent expression here, and then in the inside you have your variable t over your a, which is 2. Right? This looks like a result you would have achieved through Weierstrass substitution, which you don't need to know yet, but is a very helpful tool while doing trig integrals. However, it isn't, and we absolutely did not do that. Anyways, let's now go back all the way to the x world. We went through the u world. So let's write t in terms of x, since we don't want to go back that through more than just a couple steps, right? Okay, so we know that t is equal to root u plus 1. Sorry, no. Root of u minus 1. E to the x is equal to u, so therefore t is equal to root of e to the x minus 1. And that's really all there is to it. So here, what we get is 2 times, then t is just the root of e to the x minus 1, right? Then you would subtract off 8 times 1/2, very simple, just 4. Inverse tangent is there, right? And then in the numerator you have a t, which is just that, root of e to the x minus 1. And in the bottom, you still have a 2. Close the parentheses, add c, and you are done. Very cool. Okay, so that's number 8. Keep this in mind. This is very, very important. Also, keep the idea of making substitutions with the square root in mind, because that's also very it's just very nice, right? And whenever you see a root, you might want to do that. So yeah, keep all of the introduced concepts in mind. This is especially important, right? Okay, that's number 8. Okay, number 9. We have integral of 1 over x plus root x dx. Remember what I said earlier about substituting root x being very nice? Let's try it again, right? Remember, since last time we got a really nice differential in terms of our original variable. So yeah, let's do that. We would let u equal to root x, differentiating both sides. Well, there's another way to do this, but yeah, there's another way to do it, and that is just squaring both sides first, right? U squared is equal to x, and here you've isolated x, and all that's necessary now is to differentiate both sides. You get tu du is equal to dx, right? Okay, so here, since tu du is multiplicative, let's bring the 2 outside, and let's shove the u right on top. Right, and we still have our du on the side. The bottom right here, remember, root x is just u, and then we actually wrote this down somewhere. X is just u squared. Now what you notice is that there's a common factor on both the top and the bottom, it's just a u. So let's divide both the top and the bottom by u, and we get 2 times the integral of, dividing u by u, simply 1, and then dividing u squared by u, you get u. And then u divided by u again is just 1. Still with respect to u. And of course, this is just a natural log, right? Since you can make a u substitution in your head if you'd like to, but it's just the 2 stays outside, and then you have the natural log of the inside, u plus 1. Of course, our u is just root x, but you know what? Let's write down u plus 1 for now. And the reason why I do that is because when we introduce the root x, we realize that root x is always has a range of 0 or above, right? And adding 1 to it makes it so that it's always positive, so we no longer need the absolute value bars. We can change them to parentheses, so we just get u is equal to root x right here, and then plus 1, and there we go. That's your final result. Add c, and you're done with number 9. Yep. All right, and finally we have number 10. It's a pretty fun one. It's our first bounded integral, and bounded integrals are going to be far less common than actual indefinite integrals, because indefinite integrals most of the time it requires a lot more integration and actually reverting it back to x, right? You're finding an antiderivative. Bounded integrals is more about finding area, so it's slightly different. But here we're going to find a whole lot more indefinite integrals than these guys. How do you even mess with absolute value, right? Think about it. Now, you can... I'm pretty sure the easiest approach to this is just the geometric intuition. Absolute value, if you've ever seen the graph of absolute value, right? It looks like this. It's just a diagonal line coming in and then going right back out, right? So, yeah. And then, of course, you're subtracting away a constant in the argument. And what that does is it just shifts it by whatever that constant is. So the idea is if there's an x minus a in the argument, the a is going to be how many units to the right you shift it. So if it's like x plus 1, then you shift it 1 unit to the left. And in this case, x minus 3, you shift it 3 units to the right. So here, we have the integrand, right? So yeah. Okay, now we're gonna find, and this is very nice because it's just a straight line, right? It's just a bunch of triangles. So going from -1 to 5, let's divide this evenly out, right? So this is -1. We're gonna go from here all the way up to 5. So this is 4 and this is 5. You get this area underneath right here, right? And then, so of course, to find the y value of where this intersects, since this is just your height, right? However, you need to know what that value actually is. You just plug -1 into here. -1 minus 3 is -4. And absolute value of -4 is just 4. So the height is equal to 4, right? And similar idea with this one, I'm just going to tell you that the height is equal to 2. And here you see that earlier we said that we're going to shift it to 3, right? So that means the base is 2 for this smaller triangle, and the base is 4 for this larger triangle. So let's just use triangle areas. So we get 1/2 base, which is 4, times height, which is also 4, right? Then we add it with the smaller triangle, which is 1/2, and then you would multiply it by the base, which is 2, and then the height, which is 2. Here, that happens, and then here you get 16/2, which is just 8, and then on the second term, you're left with a 2. Yeah. And finally, 8 plus 2, you can do it with your fingers. So if you have 8 fingers up, and no, that was a joke. Let's just write down the answer. So 10 is your final answer. 10 is the area under that, right? Because that's what integration fundamentally is. All right. Okay, integral number 11. We have integral of sine x, right? Not too bad so far, but then the main point of this integral is this in the denominator, secant to the 20/19th x. And of course, this is going to have a really nice solution. And for now, let's just write this in terms of sine and cosine and see what we can do with it. Should be pretty obvious, honestly. So this is just cosine to the 20/19th x, right? And then you multiply by your pre-existing sine x dx. Here, it's now evident what we can do. We can make a substitution because the derivative of cosine x is just negative sine x, right? So we would let u equal to cosine x. And this is a new red pen, by the way. It doesn't feel the best so far, but we'll see how it goes. So we let u equal to cosine x. And then differentiating both sides, you get du is equal to negative sine x dx. Here we have sine x dx, but no negative. So what I'm going to do is I'm going to isolate the negative by multiplying by negative on both sides. On the left-hand side, you just get negative du. On the right-hand side, negative cancels to get a positive sine x dx. So now you have everything you need. First of all, because this negative du is multiplicative across the entire integral, I'm going to take the negative sign outside like this. Okay, and next we have the cosine to the 20/19th. Cosine, of course, is just u, but it's still to the 20/19th. Then sine x dx is just negative du. We already counted for the negatives, so we're going to just put down du. Okay, now it's as simple as just doing reverse power rule. So the negative sign stays, but adding 1 to the power and then dividing by the new power, you get 1 over 2020 u to the 2020, right? And of course, u is just cosine. So putting in cosine, we get negative 1 over 2020 times cosine to the 2020 of x. And then add c. And we're done. This is exactly the antiderivative of this function in here. I think it's the secant that kind of masks how easy it is, because if you write it like this, everyone can see that you can just make a substitution. But yeah, that's number 11. Okay. Number 12, back to some relatively normal, not kind of challenging integration. We have x times inverse sine of x over root of 1 minus x squared dx. Now, the inverse trig function there looks kind of uncomfortable, because without it, you're actually able to integrate this pretty well. So what we can actually do is use integration by parts, since you know how to differentiate the inverse trig function and you know how to integrate the other factors. So let's use the DI method for this. We want to differentiate, obviously just inverse sine, right? And then you want to integrate the other part, which is x over root of 1 minus x squared. And here, differentiating inverse sine, you get 1 over root of 1 minus x squared. Here, integrating this, let's make a u substitution. So let's on the side, let's do integral of x over root of 1 minus x squared, right? So what you find is that if you just made a u substitution, right, where u is the radicand, then you get that a multiple of the top is your differential. So that is actually negative 2x dx. On top, you have the x, so just isolate the x dx, right? And this implies that negative 1/2 du is actually just x dx. So here what we get is the 1/2 is multiplicative across the entire integral. I'm going to take that right out here. Okay, and then in here, the x dx just becomes 1/2 du, right? And then this looks like that. And then actually, I'm going to keep it inside. I'm going to take the negative outside, but I'm going to keep the 2 on the inside. Because what you may recognize is that this is a standard form. It just returns, and of course the negative is still outside, but root u. And of course root u is just root of that. So yeah. Okay, so that's this one. Now let's just multiply the diagonals and then integrate the rows. So multiplying the diagonals, I'm not sure which order you would write this in. Let's write the root down first then, I guess. So this is equal to the root of 1 minus x squared times inverse sine x. And then you want to subtract off this times that, right? Or no, the integral of it. So you have minus integral of, and they just cancel, right? So we just get integral of dx, which of course is just equal to x. So if we write this again, we get that, we get that this is all equal to 1 square root of 1 minus x squared times inverse sine x, and then minus integral of dx is just x, right? Add c and you're done. That's number 12. Okay, that's number 12. Next, we have number 14, which is, let's see, it's another trig one. So we have number 13, the integral of 2 sine x on top. So we have 2 sine x, right? And on the bottom, we have sine of 2x. Cancel out the 2, cancel out the sine x, and you just get integral of no. So the way you do this is, see how the bottom has an equivalent form? So we just rewrite it, right? And then that leads us to a pretty easy answer, because rewriting the bottom, you see that 2 of the factors actually cancel. The 2 and the 2 cancel, right? And the sine cancel. So you're left with integral of 1 over cosine, which is just secant. And of course, still with respect to x. And of course, the integral of secant is just a standard integral. However, here I'm going to work it out with you guys, because it's not so obvious what to do if you're just doing this. So right now is going to be the only time I'm working out the integral of secant. From now on, I think it should be expected that this is pretty standard. But anyways, to work this out, we just multiply 1 on a 1 into it, right? And 1, of course, equal to a over a. And in this case, our a is going to be secant x plus tangent x. I know it seems very random and very convoluted, since no one would ever think to multiply this in, right? To actually find the solution if they're solving this for the first time. But I mean, this is just how we abbreviate it, right? And expanding out the top, you get that secant squared x for the first term, right? And then plus secant x tangent x. And all I'm going to do in the bottom is just switch the order of addition. So I'm going to do tangent x plus secant x, because what you notice is that the top is just the derivative of the bottom, right? The derivative of tangent x is secant squared. Derivative of secant x is secant tangent. So what you can do is make a substitution. You would let u equal to the bottom, right? Because the top is the derivative of the bottom, and that means our differential will just slot right in. Du is equal to whatever we have going on top. So we have secant squared x plus secant tangent. And then, of course, our differential by chain rule. So, yeah, we have that this is just du over u. And I'm going to write this down. We have the integral of du on top, and then u on the bottom. And we know that this is just equal to the natural log of the absolute value of u. And, of course, plugging in u for what it is, we get the natural log of... I'm going to just write secant x plus tangent x, because that is the order we typically put it down in. And yeah, this works because commutative property of addition. I didn't need to switch the order here. The top would have still been the derivative of the bottom, but you know, it gives you a little bit more of a visual. Well, it's more intuitive. So yeah, this is your antiderivative of secant x. Right, and of course it came from there, but this is probably more important to show you guys, since this is standard. Always remember this. Okay, that was number 13. All right, 14. We got the integral of cosine squared of 2x. Looks kind of odd, right? So, what am I going to do with this? You know what? Let's see how I solved it originally. Okay, so, I mean, I guess what I can do is just treat 2x as, well, you know what? For now, let's just make a substitution. We would let u equal to the inside, right? Because this is the only place where x shows up. And making a linear substitution, right? Du would just be 2 dx. And then since we have a dx, we just isolate it. We have 1/2 du is equal to dx. And since 1/2 is multiplicative across the entire thing, we just bring it outside. And then on the inside, you just have cosine squared, right? But then now instead of 2x, we set it was going to be u, and our du, of course, right? So this is a lot easier now, because all you need to do for this is a trig identity, right? That's the only way you would typically solve cosine squared. So just use a trig identity. And the trig identity we're going to use is this, right? So this is another very important thing to have in mind, right? Cosine squared and sine squared are both integrated using identity. So identity for cosine is just 1 plus cosine of 2 times whatever variable you're on, and then over 2. And of course, du. Right? And for sine squared, this is the exact same. It's just that this positive is now negative. So sine squared u would be equal to 1 minus cosine of 2u over 2. See this 2u? You can bring it outside using the linearity of the integral. Here, the 2 is multiplying the denominator. You just get 1 over 4. Right? And then up here, of course, you still get 1 plus cosine of 2u. Now it's pretty easy. So the 1/4 stays outside. Integrating 1 with respect to u, you get u. Integrating cosine of 2u with respect to u, you get sine of 2u divided by 2 because of the reverse chain rule. So you get 1/2, right? Okay, right. So now we just distribute this in and then set u back to what it was. So we have 1/4 times 2x, right? And then we have 1 and then the 4 and the 2 multiplying the denominator, so you get 1 over 8. And then sine of 2 times and then u, which is 2x, right? Okay, and finally, one last simplification. 1 over 4 times 2 is 1/2 x, and then add 1/8. Sine of 2 times 2 is 4. So you get 1/8 sine of 4x. Add c because that's it, you're done. Alright, there we go. Okay. Alright, now, number 15. Oh god, this one is, I would say it's pretty insane, but it's not that bad as compared to some higher powers, but you'll see. It looks kind of innocent from the beginning, but you quickly come to find that situation's pretty hopeless. Just gotta go through with brute force algebra, and here, this is sum of cubes. We can only factor it. There's nothing else we can do. Right, so sum of cubes in the denominator, we factor it, right? You get x plus 1 times x squared minus x plus 1, right? And then on top, you just have a 1 dx. Can you do anything special? Any trickery? No, you can't. This is just, you gotta do the partial fraction decomposition. Okay, so let's decompose this fucking fraction right here. So we want it to break into 2, right? So, you know what, let's write PFD down here. And then we have 1 over x plus 1 times x squared minus x plus 1. Right, and then you want this to be equal to 2 fractions, with each of the denominators which each of the factors in the original denominator as their respective denominators. And you want the tops to be 1 degree less than the bottom, so 1 degree less than a linear, which is a constant. 1 degree less than a quadratic, you just get a linear. Okay, so, now, let's not do anything silly, right? Let's just expand it and see where it takes us. So, we do as we did earlier. We just multiply this common denominator on both sides, right? So what you get on the left-hand side is that you get 1, right? And then is equal to a times x plus 1, cancel out. You're left with the x squared minus x plus 1, right? And then in the bx plus c guy, and this should be in a parentheses, the quadratic cancels the quadratic. You're left with the linear. Okay, so now just expand it. Distribute the a out. You get ax squared minus ax plus a plus bx squared plus bx plus cx plus c. Okay, so this is currently what we're working with. Now all we need to do is group the terms by term degree. So we have two quadratics, a and b, right? A plus b, x squared. All right, and then now we add the linears, which there's a negative a b, and a c. So we have negative a plus b plus c. That's linear. And then finally we have the constants, which is just a and c. So we add on just simply a plus c. All right, and then recall that this is actually equal to 1. All right, now you see that there's no quadratics on the left-hand side, so that means there's no quadratics on the right-hand side, meaning a plus b must equal to 0. Similar situation with the cubics, linears, right? So you have negative a plus b plus c must equal to 0. Okay, and then finally, you have one constant on the right, one constant on the left, meaning the constants must be equal, meaning a plus c must be equal to 1. Okay, so there's some stuff that you can do with this, I guess. Yeah, how would it be solved? So what I would do first is I would subtract these guys, right, to an equation in terms of b and c only, and then just combine those or something like that, right? So we have two equations both in terms of b and c. So you know what? It's probably not the best idea. I think the best idea would be to find an equation either in terms of only a and b or a and c, because these are already only in terms of a and b and a and c, right? So we're going to use this middle one. So let's just try to find an equation in terms of a and b only by canceling out the c's from these two. To do that, you subtract it. So you want to do negative a plus b plus c, right? That's the middle one. And then you want to subtract off a plus c. All right, and then of course this is equal to 0 minus 1. Okay, so what you notice here, there's a negative 2a now. C's cancel, of course, and then you have just a b. And on the right-hand side, you get negative 1. So right here, what you do, plop it underneath. And then, well, yeah. You know what? Here. Subtract this and that so we can isolate a, right? So we have negative 2a plus b. And then you want to subtract off this, right? So you would do minus a plus b. And then by doing this, you see that, first of all, this is equal to negative 1, right? And then negative 1, you also want to subtract off the value of a plus b, which is, of course, equal to 0, so you're just subtracting 0. Here, the b's cancel out. You get negative 2a minus a, which is negative 3a. And, of course, this is still equal to negative 1. Divide by negative 3 on both sides. You get that a is equal to 1 over 3. And then I'm going to box this in red, just for us to refer to later. Now you're easily able to solve for the other variables. Plug 1 over 3 into a here. You just get b equals negative 1 over 3. Right, so that's our second variable. And of course we have an a down here. So plug 1 over 3 into this. You get 1 over 3 plus c is equal to 1. Subtract 1/3 on both sides. 1 minus 1/3 is just 2/3. So therefore, c is equal to 2/3. And box. Right? Okay, so, yeah. Okay, so now let's write this on our right, because So we just want to replace it with this, right? With that. So a is equal to 1/3 over x plus 1. And then you want to add b is equal to negative 1/3 times x, right? And then plus c, which is 2/3. And this is over our quadratic x squared minus x plus 1. All right, dx. All right, so that's enough for the partial fractions. Let's get rid of this because we need a lot more room to do this algebra. Now, it might look pretty simple right now. You have a linear over quadratic, right? It's pretty much easily doable every single time. However, let's just dig a little bit deeper, find that the whole is actually much bigger than you originally think. Factor out, let's break this integral into two, right? So this is actually equal to the integral of, and in the first integral, feel free to take the 1/3 outside, and then inside you're left with the 1 over x plus 1 dx, right? Second one, you want to move out. The common factor here is actually a negative 1/3, right? So make this a minus 1/3 outside the integral. And inside the integral, you just have an x. And then factoring out a negative 2/3 from there, you just get minus 2. And of course, in the denominator, you still have your boring old irreducible quadratic. That is stinky. Okay, first one, you know how to integrate, right? So we're going to set this aside for now. What about the second one? Well, the top's not the derivative of the bottom, right? So we can't really do a u sub. But when you have a linear over a quadratic where the linear is not the derivative of the quadratic, just try to... Okay, well, here, let me take the derivative of the bottom to show you what we're trying to achieve in the numerator. So the derivative of this, x squared minus x plus 1, right? We know is equal to 2x minus 1. Not plus c, because that's differentiation. So we're trying to find one of those in our numerator. So, I mean, the constant term, we can always break it off, right? So let's focus on getting the linear term to match. And to do that, let's multiply 2 on the top. But that also means to be able to maintain equality, you also gotta divide 2 on the bottom. So finding 2 on the bottom, just multiply the denominators, so you get 1/6. And then multiplying a 2 on top, this becomes 2x. And then this becomes minus 4, right? Okay, and here's what I meant by you can always just break off the constant term. So now you see we have the minus 4, right? But we want a minus 1. So we just take a minus 3, right? We make this one minus 1 minus 3, and then just take the minus 3 and break it off into another fraction. So, and in fact here, I'm not just going to break it off into another fraction. I'm going to just break it off into a whole another integral. So we have that, right? Then 2x, but now it's minus 1 because that's the derivative of the bottom. So we're able to make a u substitution in this middle term now. However, recall that we had a minus 3 over the same denominator that we broke off as a different fraction. So we're going to write that in a new integral. And of course, because we're breaking the integral as well, it needs to have the same, it needs to have the same exact coefficient on the outside. So you have a negative 3 on the inside, right, in the numerator, and then we have a negative 1 over 6 on the outside. That can reduce, if you just bring the negative 3 outside, to a positive 1/2, right? Feel free to check my math. And then here, you're just left with the 1 because we brought it outside. So 1 dx. Okay? So you're able to integrate these two. What about this one? Well, if you have an irreducible quadratic on the bottom, typically you just want to complete the square, right? Because if the quadratic's irreducible, either because it's not factorable, or because it's not or because it doesn't have any real roots, then completing the square will always work for you, because what you end up getting is either a difference of squares, right, where x is in the first term, or a sum of squares. And in both cases, they are absolutely solvable by trig sub. It is no question about it. So whenever you have this, just complete the square. So to complete the square for x squared minus x, you just, well, I'm going to just say it's 1/4 because, well, what you want to do is you take the b, right, -1, first square it, and then divide it all by 4, right? And then squaring -1, you just get 1, right? And then dividing 1 by 4, you just get 1/4. So we want to find a way to break off a quarter from this constant term we have out here, 1. And to do that, it's pretty simple. We just break it into plus 1/4 plus 1/3 plus 3/4, sorry. And then dx, because what you see here is that these two add to make 1, so it's equal to this guy back here. Okay, almost there. Now the reason why we did this is because it makes a perfect square trinomial. So here what I'm gonna do is I'm just gonna do that because I don't want to be rewriting this, right? So this is equal to x minus 1/2 squared plus, right? Because these first three terms condense into that. The third one, let's write it as sum of squares, right? So you want to take the square root of it and then write it all under square. So it would look like that because square root of 3 is root 3, square root of 4 is 2, and then of course you have to square it all to maintain equality. Alright, so now you have this. So why don't we just replace it with that? Because then all we're left to do is make a substitution. Alright, and in fact here this is such a standard form that you don't need any like real trig sub, because as I introduced earlier, sum of squares where your variables in the first term. Sum of squares in any order, because it's commutative. You always just use the inverse tangent formula, right? Okay. For the first one, let's introduce a substitution. We would let a equal to x plus 1, and therefore dA would just be dx, right? So not that complicated. You just get 1/3 times integral of inside 1 times dx is your dA. So I'm going to write that on top. At the bottom, we just have our a. So that's our first term. Second term, we set the top to be the derivative of the bottom. So that's very convenient. We just let the entire bottom be equal to a variable. Call it b, right? And then differentiating both sides, you get db is equal to the top, right? So you get 2x minus 1 times dx. So here you get minus 1 over 6 times the integral of that entire numerator is just db, and your denominator is just what we set as b. Okay, so these are both natural log cases, right? What about this third one? It's just inverse tangent. It's not that difficult. So here we just want this to become one variable. So let lowercase c equal to x minus 1/2, and therefore dc is equal to dx, right? Not that complicated. So here we add 1/2 times integral of 1 over, we just replace that with the c. However, this guy right here, there's no other way to write it. You just write it as that. And then of course, dx is equal to dc, so we're going to write that on the outside like that. Okay, so this first term, very easy to integrate. You get 1/3 times the natural log of a, right? And a is just x plus 1. So I'm going to just write down x plus 1. Second term, same thing, minus 1/6. And then you get a natural log, the absolute value of the inside of b, right? Which is the quadratic. And in fact, the quadratic is irreducible. So, because it is always positive, there are no roots, no real roots at least. So because it is always positive, we're going to get rid of the absolute value symbols and exchange them for normal parentheses. And then finally, we have our inverse tangent. So 1/2 times, you want to first multiply by 1 over a, which is just the reciprocal of your a value. So we have 2 over root 3. right? So notice that the 2's cancel, so I'm going to rewrite this as 1 over root 3. Okay, next you have the inverse tangent function, and then inside you have, well, we just have the reciprocal of a again, right? 1 over a, so that. And then we want to multiply by our variable c, which is equal to x minus 1/2. So it looks like we're done. However, there's simplification to be made. If you just distribute this out, this multiplies straight into x, right? No question about it. But then when you multiply into 1/2, the 2's cancel, right? So you get that x, but then you also have to subtract off this times 1/2. 2's cancel, you get 1 over root 3. Okay, and there's no more integration to be done, right? We have this all in terms of x, and I just swipe my finger across that and rewrite that. Okay, yeah, that is our final result, and it took a while, right? Partial fraction decomposition, but that's just the way it is, right? If you alter this number up here, as it goes bigger, the question becomes exponentially more difficult, right? I've integrated 1 over x to the 5th plus 1 before, right? That took around 2 hours, but maybe because I work slow. But yeah, this is like the beginning of the algebra for 1 over x to the n plus 1. Of course, you're able to use complex analysis, but there's no fun in that when you can actually integrate the entire thing algebraically. Right. Okay, so that's our enormous results. Not that big for advanced standards, but yeah, that's it for number 15. All right. Number 16 is a lot better than the algebraic hellfest we just went through. It is the integral of x times sine squared x with respect to x, right? Not as bad because you're able to just do integration by parts. Because as you differentiate a polynomial, it eventually approaches 0. And I'm sure you're able to integrate this as many times as you'd like to. Okay, so I'm going to use the DI method again. So you would differentiate x, it would become 1, and eventually 0. All right. Integrating, you have to integrate sine squared x. Integrating this, well, just replace this with its identity, right? So you have 1 minus cosine of 2x over 2. I told you this would be important earlier, so there's your identity. All right, and of course, integrating 1 over 2, you get 1/2. Well, in fact, I'm going to keep everything over. No, I'm not. Okay, so integrating 1/2, you get 1/2 x, right? And then subtract off 1/2 times, okay, integrating cosine, you get sine. All right, and then you also have to do reverse chain rule, divide by 2. So 1/2 is already there, and then divide by 2 again, you get 1/4. Okay, and of course, one more time, integrating 1/2 x, increase the power by 1. Gives you 2, divide by the power, you divide by 2, so you get 1/4 x squared, right? And then here, integrating negative sign, you get positive cosine, right? And then, of course, you have to do the reverse chain rule again, where you divide by 2, so you get 1/8. And yeah, so we just multiply the diagonals and integrate the rows. However, no rows to integrate once again. Okay, so here we just multiply. Let's just distribute in x, right? So we got 1/2 x, but now it's squared, and then minus 1/4, and we're gonna slot that x in right here, times sine of 2x, right? Next we have minus 1/4 x squared, and remember to distribute the negative 1/4 x squared, and then minus, of course, 1/8 cosine of 2x. All right, One thing here, notice that this and that are like terms, so you're able to combine them, and what you end up getting is 1/4 x squared, right? And then you have all the other terms again. So 1/4 x sine of 2x minus 1/8 cosine of 2x. Add c, and that's it for this one. Pretty basic. Not all that much depth to it. It's just integration by parts. Okay, so next, let's do number 17. Number 17, integral of x plus 1/x squared dx. So in fact, in a lot of factoring cases, we actually have to deal with this term a lot. So it's good to identify like what its square is, what its cube is, and sometimes what it is raised to the 4th power, right? But that's really down to you memorizing the Pascal's triangle for the binomial coefficients, right? Okay, but for this case, we can't do anything on the inside, so let's just expand it, right? So expanding this, we get x squared, and then there's a positive in there, so we plus 2 times this times that, but they cancel to make a 1, so we don't really do that. And then we have 1/x, but squared, because you square the last term. Okay. This is extremely simple. It's just a case of reverse power rule. Add 1 to the power here, and then divide by 1/3 x cubed. And then, of course, integral of 2 is just 2x. And then integral of 1/x squared is, I think it's pretty standard. You get -1/x. And then you add c, and then that's it. Just box it, because that is the final result for number 17. All right, pretty simple. Okay, so number 18. Remember earlier in question 15 when I said in the denominator, if all you have in the numerator is a constant and in the denominator you have an irreducible quadratic, you're going to want to complete the square. Well, here we're going to see that in action, right? See, notice how the bottom is A, not factorable, but also B, has no real solutions, right? Just drew 2 bad lines in a row. So what we want to do here is, well, I don't have any other solutions for you besides just some not partial fraction decomposition. Because we can't do that since we can't factor this, but we can do completing the square, as I mentioned earlier. So to complete the square for x squared plus 4x, we just want to split our next term into a plus 4 and then plus something else, right? So you have a plus 4 here. 29 minus 4 is just 25. Right, and then we have a 3 on top. Purpose of completing the square, of course, this is a perfect square trinomial. So this is actually x plus 2 squared, right? And then add 25. And then, of course, you have the 3 on top. Okay, so, yeah, let's do just the u substitution. I don't see a point in trying to explain this in a manner that's a little bit complicated. So let u equal to that, right? Since we want that to just be one variable, because it's better to look at, I think. But you're able to do this either way, because this is really just represents like a shift on the x-axis. So your differential is still going to be the same. It's going to be dx, right? Here, now we just replace that with a u squared, and then plus, and there's a 3 on top, right? And there's a dx is equal to du, so we just swap in a du for where we saw that dx. Okay, the second thing here is that this becomes sum of squares, right? Since this is a square, and that's also a square, so it's sum of squares. So you're going to be using the inverse tangent property, right? So you want to rewrite this as a sum of squares. So 25 is, of course, 5 squared. Okay, so here we go. This is just inverse tangent. This is we can use the definition, or no, the formula, right? So we have 1 over a, or actually no, we have the numerator right here, which is 3, right, over a, which is 5, times the inverse tangent function of the variable, but over a, so 5. And of course our variable is u, but we know that u is x plus 2, so let's just write x plus 2 in. Okay, add c and we're done. This one looked a little bit like intimidating at first, but it turned out to be not that bad. That's not going to be true for all of the quadratics we do, especially if they're inside of the square root, since we actually need to do trig sub at that point. But this is nice. Okay, so right, that's number 18. All right, number 19 is integral of cotangent to the 5th power x dx. How should we do this? We can just rewrite this, right? Cotangent, so, okay, think about tangent and secant. They work really nicely together because secant squared minus tangent squared is equal to 1. So we know of another property that is extremely similar, and that is that cosecant squared minus cotangent squared is equal to 1, meaning cosecant and cotangent must work very well together. So let's pull out a cosecant squared from this, okay? So let's reduce this to a cotangent cubed, right? And because we're going to pull out a cotangent squared, but we know that cotangent squared is just cosecant squared minus 1. Sorry, I'm going to include the argument. And then dx. So we distribute now, right? Not much else we can do. But along with distributing, I'm also going to split the integral, right? So now we have minus 1 times that. This one, you're ready to integrate. Let's work on this one. So, for that one, you want to do a very similar thing as to what you did before because, of course, cosecant is the derivative of cotangent. Well, cosecant squared is the derivative of negative cotangent. But regardless, we're still going to pull out another cosecant. So here we just have cotangent to the 1st power now. And then the cotangent squared we pulled out becomes cosecant squared minus 1. And then rinse and repeat, right? So cotangent to the 3rd power x, cosecant squared x dx, right? That's our first term. All right, split it once again. So first integral, we have this times that, right? So we have integral cotangent x times cosecant squared x dx. Okay, next term we have negative 1 times that, and of course don't forget the negative out front. Double negative makes a positive, so you just get positive integral of cotangent x dx. This is very standard, just like integral of tangent x. So yeah. Now we're just make some substitutions to integrate these two, and then that one is already standard. So let u equal to cotangent, right? That's the whole reason why we pulled out the cosecant, because the derivative of cotangent is cosecant squared dx. So differentiating both sides, you get negative cosecant squared x dx. But we have a negative sign here, so, and we don't have one here. So for this first term, well, you know what? let's just do this. For the second term, what I'm going to do is I'm going to bring the negative inside, right? I'm going to move the integral sign back a little. Integral, and then negative cotangent, right? All right, and then for this first one, it's not going to be all that complicated. I'm going to multiply a double negative, because a double negative, it just cancels to make a positive. So we have a negative on the outside, right? But more importantly, we have a negative on the inside, so that way now we have the negative cosecant squared of dx. Okay, so negative stays on the outside. However, negative cosecant squared dx is just our du, right? So all we need to deal with is a cotangent cubed. Cotangent is u, so this is u cubed. And then earlier we said all this crap was just du, so we put down a du. Similar story here, but now we only have cotangent to the first power, meaning this is just u, but to the first power, right? And then du. Okay, and you know what? This third one, I'll just leave it be. Let's just say plus integral of cotangent x dx, because I'm going to integrate all in one step, and that's going to be in this step. So negative sign stays. Integrating u cubed, you get 1/4 u to the 4th, but of course u is just cotangent, so I'm going to replace it with cotangent. Okay, and then next you have plus integrating u, very easy, 1/2 cotangent squared x, because u is just cotangent x. Finally, integral of cotangent x is standard. This is natural log of the absolute value of, let's use absolute value. Positive, this would actually give you sine, so absolute value of sine x. Okay, so that's it for this. So we can just add c at the very end. And now we have our finished integral. I think this is correct. Is it? Let me think. Positive natural log of sine x. Hold up, maybe I should integrate this. Since when it comes to the tangent, right, everything's positive, you're all happy. Cotangent, on the other hand, the derivative of cotangent is negative. So that puts into question whether this should be negative. So let's actually do the math in this. So integral cotangent x, because I'm having self-doubt. So cotangent is, of course, cosine over sine. Let u equal to sine, of course, you just get, this is du over u, which is just natural log of u. Right, so this is correct because u is just sine. All right, so that's it for number 19. This is the right answer. Let's box it before we move on. So, just for the formality. Okay, right. That is number 19. Okay, number 20. Another rare one that's pretty interesting. We're not going to do any real integration. That's a hint as to how you should treat this integral. So number 20 is bounded again. So we have -1 to 1, right? Then we have normal tangent x on top, and the bottom is actually completely algebraic. X to the 4th minus x squared plus 1. Okay, so how the fuck would you even start with this, right? You have bounds, you have a trig function, you have a algebraic function. But these bounds look oddly suspicious, don't they? They are negative versions of each other. And if you remember, we have a property that is derived from the fact that, see how these bounds are symmetrical? We're going from negative, let's just call this a, right? And then to positive a, right? Now, we know something about odd functions, and that's that if we have an odd function, right, that's one property of odd function is that they're rotationally symmetric. Rotate at 180 degrees, you get the same function. But area under odd function visually is obviously 0, right? Since anything on the left-hand side has a counterpart on the right-hand side. It's exactly this, right? But that's only if it's in symmetrical bounds, right? But it's always going to be net 0 no matter how wide the bounds are, because it's always symmetrical. Wherever there's a negative on the bottom, you rotate it, it's going to end up positive on the top, in the positive area right here. So we know that integral from negative a to a of an odd function, right, with respect to the variable, whatever the variable is always going to evaluate to 0, right? So this looks suspicious. Now we just figure out if this is an odd function or not. Okay, and you're seeing this because I tried and failed to give a really good explanation on the rest of that integral, right? From here, what we can do is find out whether the inside is really odd or not, because if it is odd, then we can leverage this property right here. So let's take a look at the integrand. We have tangent x over x to the 4th minus x squared plus 1. Okay, first of all, the top, right? Tangent x, you could just say that it's odd by taking a look at its graph, right? However, I want to break this down a little bit further into sine over cosine, because sine x and cosine x, they're better to picture because they're just pure waves, right? Tangent looks kind of odd, but sine and cosine, they're easier to think about because they're just waves. So let's take a look at the graph for sine, right? The graph for sine looks like this, right? So notice how this wave is rotationally symmetrical, meaning if you draw a little black dot there and you turn the entire graph along the black dot, which is, by the way, needs to be on the origin for this to be odd, and it is, right? Then what you end up getting is the exact same wave after rotating it 180 degrees, meaning sine x, right, is odd. All right, what about cosine, which is what's in the denominator? Cosine is the exact same wave, actually, right? They're both very organic-looking, nice waves. However, cosine is shifted off on the x-axis. So it would actually look like that. Well, that's off-center, but let me draw this better. So cosine would look like... I'm going to try to make this... look more or less intuitive, right? So what we have here is actually appears to be an even function, because an even function, if you just reflect the entire thing over the y-axis, right, then see how it's symmetrical. The axis of symmetry is the y-axis, right? So that means this is even, right? All right, so that is part 1. So now we see here we have an odd over an even function in the numerator. So how do we figure out whether this is odd or not? Well, like through just knowing this, right? We don't need to know that it's tangent. We just need to know that it's this, because we're trying to build steps to be able to come up with the solution to this. So the way I would look at it is through the simplest odd and even functions there are, right? And by the way, I'm not going to use the algebraic definitions or the function definitions, right? Because I want this to be graphically intuitive. Because just saying a function is odd or a function is even right, the numbers kind of look weird, so I'm gonna do this right here. Let's take a look at the most basic odd function we've got, and I think that would just be a line, right? A diagonal line at 45 degrees. This is just y equals x. All right, so that's part 1, and we also need an even function, so we'll just draw a line. Since a line right? A flat line, that's actually perfectly even since it is still symmetrical. All right. So now let's take a look at this point, right? Which I'll call negative a, since it's on the negative side of the x-axis. And we'll go to another point right here that is positive a. So that means this is very similar to the bounds right here. They are the same distance away from the y-axis, right? Well, what that means for the odd function is that this value right here, let's call it negative k, right? Is going to be the exact opposite, exact negative of this value, right? Which I'll just call k, all right? Keep this in mind. Now evaluating at the even function up here, well, our function, let's just call it y equals c, any constant, right? Then over here, it's going to be c, and over here, it's also going to be c because it's symmetrical. No matter if you plug in a negative or a positive, you're always going to get the same answer as long as the number behind the sign is the same. And in this case, it is. We're dealing with a. Okay, so now because we see we have an odd over even, what we can try to do is just divide, right? So let's call this, instead of x and y, let's call this f of x is equal to x, right? Because y and f of x mean the exact same thing. Let's call this g of x is equal to c, because the y value is equal to a constant. Now, because f of x is x, this is our odd function, and g of x is c, this is our even function, we're trying to find the properties of an odd divided by an even function. So let's write this like this, f of x over g of x, right? And let's call this new function h of x, all right? So what you're fundamentally doing is, if you're evaluating h of x at, like, say, negative a, then what you're doing is you're evaluating this thing at negative a. And f of negative a, we see that f is our diagonal line right here, and at negative a, it's equal to negative k, right? And then g of x, earlier we said that at negative a or a, they're the same exact number, they're both going to be c. So, right? Okay. So that is number one. Number two, take a look at this positive side now. What if we plug the positive number into our h? And then what we get is positive, and we're dividing f by g, right? So if you evaluate at f, you get k. And then if you evaluate at g, you get c, right? So, in fact, what you get right here is h of negative a and h of a, well, they're almost the same. It's just that this is the negative of that, right? So this is the exact definition of an odd function, right? Because odd function is, if the input is the same but just negative, then the output is going to be negative as well, right? So this is an odd function. But how would you picture this visually, right? So if you think about it visually, I think the way it would work best is to graph these 2 points. So here we would need a negative k over c. Let's just say it's right here. And it might look kind of confusing at first, but just bear with me. And then next up, we have normal k over c, right? And of course, this is going to be at the x value a. So it's going to be along this line right here. And notice that this is the negative of that. So it's going to be the exact same distance from the x-axis, but just it's going to be over here, first of all, and it's also going to be positive. So it's going to be up here. Okay, and then now you just repeat, right? Repeat for all possible points here. And what you end up getting is another line, right? And you can explain this very intuitively using algebra as well, because you see that dividing x by c, it just gives you another function, right? That's just a line, right? 1 over c times x. This is just in form of y equals mx plus b. It's a straight linear line. And not just that, it's proportional, passes through 0, 0 as well. And that means this is odd, because you see that if you take our new black line and then pivot it on this point, 180 degrees, you're going to get the same exact line back. Yeah. So that is all the intuition behind an odd divided by an even function. You get an odd function, both by the algebraic definitions after evaluating at this point, and also just graphing out a line by evaluating at more points, right? So this black line is our h of x. Okay, so we've established that odd divided by even is just odd. So now, if we take a look at what we have right here, right, and then we just move it down here so it's better to see. We see we have an odd function, which is our tangent x, because sine is odd, cosine is even, so we have an odd over even situation, which gives us odd, meaning tangent, which is sine over cosine, odd over even, is odd. All right, in the bottom right here, now we just have a sum of, well, it's a polynomial. But notice how this polynomial is special, right? We have x to the fourth is, first of all, let's do it down here. X to the fourth is even. X squared, you also know, is even. And you're subtracting that. And then 1 is, once again, even, right? So what's the intuition behind this, right? Like, it feels like it should be even because you're adding a bunch of even functions. But if you want to take a look at it on a graph and know for sure that it is even, I'm going to draw this up here for you. If you have, like, an even function, right? Let's just call this our even function. Then they all have the same axis of symmetry, right? They all have the same exact axis of symmetry. Oh, well, this one's slightly off, but yeah. But anyways, they all have the exact same axis of symmetry, and that's going to be y is equal to 0. Sorry, no, not y. X is equal to 0, aka your y-axis, right? So that means on this side, if you add all the values up, well, okay, no. Think about it like this. Flip all of this crap over to this side, right? Now, all that's different is that your inputs, the x values, are negative. However, you see that regardless of where you add them up, because they're the exact same graph, right? Like the reflected version of this and also the left side of the graph, you're going to get the same y value. So now let's graph, say, like the sum of these guys, right? It might look something like this. Okay, so now what I want you to do is, in your head, take what you just reflected, right? And you added it all up, so that's giving you just this left-hand side, right? Now leave one copy of it there, because that is what we originally had on our left-hand side, right? And then take what you reflected here, and then added it up, and then reflected to the other side. And of course, it's going to be symmetrical because you're reflecting everything here over our y-axis. So it's going to be symmetrical too. So if you add 3 even functions up, you're going to get another even function, right? So that's the graphical intuition. If you could follow me, then it would have made a little bit of sense. Okay, so now we see that this is really just odd, right, as we established earlier on the top, and then x to the fourth minus x squared plus 1, 3 even functions summed together gives you another even function. And once again, as I said earlier, here when we were doing this tangent x is odd thing, we were just establishing how you would figure this out, right? And you can see that the reason why we did that is because we need to apply it again. Odd divided by even. Remember, we earlier said this is odd, meaning this thing, which is actually equal to what we had in here, is now completely odd. So just ignore what we had in here. We found out that this is odd, right? And you see that these bounds, as I mentioned earlier, are negative a to a, right? They're symmetrical. This is just that, meaning this is just 0, right? I genuinely didn't need to explain that much, but, that's number 20. Okay, all right, let's get rid of this. The graphical intuition, it really helps a lot with understanding how even and odd functions interact with each other. Okay, and then Number 21, we have the integral of sine cubed cosine squared. And for this one, you see that this is sine times cosine, so it works very nicely. So all you need to do right here is to either isolate a cosine or sine. And in this case, the odd power is in the sine, so you're able to isolate sine. So, sorry, not isolate, but just like pull out a sine. So we have a sine, right? But we still have a sine squared. So we're going to turn that into 1 minus cosine squared. And then here, of course, we still have our cosine squared left. And then our dx. So what this does is it sets us up for a trig substitution. Sorry, not trig. U substitution, since the derivative of cosine is negative sine, right? Which is almost what we have here. So we would let u equal to cosine. And then differentiating both sides, you get du is equal to negative sine dx. And of course, recall that here we have a sine x dx, but we don't have the negative. So we have to isolate the sine x dx. So we get negative du is equal to sine x dx. Okay, so for this one, I'm going to ignore the sine x dx for now, since that all just becomes a du at the very end. Instead, we're going to take a look at the factors with the cosine. So we have a 1 minus, cosine is just u, and it is squared. And then we have another cosine on the outside that is also squared. And then we have our negative du, right? But yeah, remember that sine x dx is negative du, but we don't have a negative sign in here. I'm going to move the negative all the way outside since the differential is multiplicative. Okay, so this is a pretty simple task to integrate. What I'm going to do is I'm just going to multiply this in. You get a u squared minus u squared times u squared is just u to the 4th, and then du, right? Okay, so while we integrate this, I'm going to use the subtraction sign to switch the order of subtraction in here, right? By distributing it in. So integrating u squared, you get, let's reverse the order of subtraction, right? Because we're distributing the negative, so let's evaluate u to the 4th first. To integrate that, very simple, reverse power rule, you get 1/5 u to the 5th. However, u is visibly here cosine to the 5th. Then remember, we reverse the order of subtraction, so you have a minus sign. And then you have the integral of u squared, which is 1/3 u squared. But u is cosine, sorry, not squared, cubed, right? So this is what you get. And in fact, this is our final answer. Add C, and yeah, that's it, you're done. Very nice. So that's number 21. Okay, number 22. We have the integral of 1, in the denominator we have an x squared times an x squared plus 1. And on the top we have a 1, and then dx, right? So the thing with this is you see an irreducible quadratic inside of a square root. So what you do here is you simply use a trig sub, and since it's in the form of sum of squares, you would use tangent, because tangent squared plus 1 is equal to secant squared, and that is very nicely able to cancel with the square root. So here we go. We're letting x be equal to tangent theta, right? And then differentiating both sides, you get that dx is equal to secant squared theta d theta. Okay, so now we put it all into our integral. This x becomes a tangent, but don't forget that it is squared. And then earlier, as we discussed, this, after plugging in tangent, it just reduces it down to a single secant. So let's just plop down a secant there. And of course, we still have our differential to deal with. Dx is just that. So I'm going to write the secant squared on top. And then I'm going to write the d theta out here, right? Notice that we have the square canceling with this on the bottom. So we just have a secant over tangent squared. Now, secant over tangent squared, you can't really integrate that in any way. You can't do any manipulations, right? So, in fact, what I'm going to do now is I'm just going to write it all in terms of our primitive sine and cosines. So, secant, you get 1 over cosine theta, right? And then on the bottom, tangent squared, it's also sine over cosine. However, because the tangent squared, don't forget that needs to be sine squared over cosine squared. Like that. Notice here, to be able to get rid of the complex fraction, just multiply cosine squared on top and the bottom. On the top, cosine squared times 1 over cosine gives you a normal cosine, and on the bottom, it just cancels with the denominator of the denominator, and you're left with a sine squared. And see here, you're set up for another substitution, because the derivative of sine down here is just whatever you have on top. Cosine theta, d theta. So let's let u equal to sine, right? And differentiating both sides, you get du is equal to cosine, like this. So this gives you, on the top is just now a 1 times du, right? Since du is equal to that entire thing. On the bottom, since you have sine squared and sine is equal to u, you now have u squared. So you have 1 over u squared du. And this is, I'm fairly sure this is pretty standard. Everyone's able to recognize this. Integrating 1 over u squared just gives you negative 1 over u. Okay, so that's what we have. But now we want to be able to get back to the x world. And to do that, we have to first go back through the theta world, right? So what's u in terms of theta? Well, we have u is equal to sine theta here. So we have, this is really just equal to 1 over sine. However, 1 over sine is just cosecant. So here, the negative sign here stays, but then 1 over u is just cosecant. And not x, theta, because you're first going to go back to the theta world. All right, now let's make the step back to the x world, right? X is equal to tangent theta. And that means if you were to isolate our theta, because we need it to be able to plug in here, you just get that inverse tangent of x is equal to theta, right? And that's helpful because we're able to draw a right triangle to be able to find what the cosecant of inverse tangent is equal to. So, here we go. The argument of tangent is just an angle, so we're going to call that theta, right? And it represents an angle in, of course, a right triangle. So, and the output right here, x is just a ratio of tangent, of the trig function tangent, right? And that ratio is opposite over adjacent, right? So this ratio right here, x is just opposite over adjacent. So that means x is opposite and then 1 is adjacent, because x over 1 is still equal to x, right? And then to find this side, just do the square root of the sum of the squares of each of these respectively, right? Get square root of x squared plus 1. Okay, and now all that's left is simply finding cosecant, right? Since we plugged in this inverse tangent, but we want cosecant of this angle right here. So the cosecant is lesser known, but it's just a reciprocal of sine. So instead of opposite over hypotenuse, it is now hypotenuse over opposite, so you get this over that. So all you get is, and don't forget the negative sign out front, of course, but you get a negative square root of x squared plus 1, then, of course, over x. And then, right, that's it for this one, because we're back in the x world, and there's not much more simplification that can be made. Now, I'm pretty sure with this you're able to do, probably, there might be a shortcut you're able to take, but this is the traditional pathway that most people will think of first. Right, so that's number 22. Number 23 is the integral of, and it's pretty funny when you initially see it, but do some simplification and it really isn't. So, sine x, secant x, tangent x. What do you do here? Well, can't do DI method, right? Even though obviously you can integrate this and you're able to differentiate that, right? Because it's not going to lead you anywhere any more helpful. Well, you know what? there's two ways to solve this. You can do the DI method for this. And if that's what you think of first, let's give it a shot. Because I'm pretty sure most of you are able to see that these are just trig functions and you're able to reduce them. But for now, let's try the DI method. Because my interest got piqued. I just came up with that. I don't know why, but let's differentiate sine, integrate secant, tangent, right? Of course, differentiating sine, you get cosine. Integrating secant x, tangent x, you just get normal secant x. So multiply the diagonals, you get sine x secant x. And then, of course, integrate the row. But, in the row, cosine x times secant x, of course, they're reciprocals of each other. That means they're going to cancel to make 1. So we just minus the integral of dx, right? All right, now for this, you're going to need to figure out what this is either way you do it, right? So let's do this. So secant x is just 1 over cosine. So if you just replace this with 1 over cosine, you get sine x over cosine x, which is just tangent. So let's put that down. We get a tangent x. And of course, very simply, integral of dx and the x. Well, yeah, integral of dx is just x. All right, add c, and this is the first way to do it. The other way is not nearly as complicated because what you can do is you can just apply this sine x secant x equals to tangent x directly into there. So you see that there's still a sine x secant x you have to deal with. So, of course, replacing that with our tangent, you also have to notice that there's another tangent being multiplied in. So let's raise this to the second power. So that's really the equivalent form. Now, it may look kind of weird. You might get kind of stopped, but use trig identities, right? This is just secant squared minus 1. And, of course, you're able to integrate secant squared, and that'll just give you tangent. And then integrating negative 1, you just get a negative x, right? And then add c, and that is the way most people will do it. But, of course, integration by parts, it's silly, but, it works. All right, number 23, that's it. All right, what's the next one look like? Number 24. Number 24 is one that is very important. And it may not seem it at first. It just seems like a random trig integral, but this one is a property that in the process, whatever. Just keep this in mind, since integrating this will take a lot longer than it might initially seem. And also, it doesn't appear that uncommonly, so the result, you should probably keep it memorized, unless you want to do all this again for a lot of future integrals. Right. Let's start off using the DI method, right? Since you see that for this one, you're able to split this into secant times secant squared, right? And the reason why you want to do this, why you might think of doing this, is because you're able to integrate secant squared and differentiate secant, and it gives you nice trig functions. So let's just do that. It looks like a subtraction sign. Okay, so differentiate our secant, right? And then we integrate our secant squared. Differentiating secant, you get secant tangent, and then integrating secant squared, you just get normal tangent. Multiply the diagonals and integrate the rows, and you get that this is equal to secant x tangent x and subtract off this times that, right? And the integral of it. So you get secant x, and then there's two tangent x's, so I'm going to write it as a tangent squared x dx. Okay, so we're getting there. It looks like progress has been made, but do a few more steps. We see that only thing we can do with this one right here, you can't integrate it quite yet. So let's just split the tangent up again into a secant squared minus 1. Since you're able to take out the 1, right, and then you can just deal with the rest later. But what you may notice is that after you do take out the 1, you're left with your original integrand. And this is actually a convoluted, but it's a repeating case of the DI method for integration by parts. Okay, so let's put down this then, right? Integral of secant cubed, which is where we originally got all this from, is equal to this thing on the right-hand side. So we just have secant x tangent x. And then you want to subtract off. Let's distribute this in and then split the integral. So first, let's do the minus 1 because it's easier, right? Double negative, it gives you a positive. Integral of secant times 1 is just still integral of normal secant. Okay, and then secondly, you subtract off integral of, here you get secant times secant squared, so all in all, that gives you a secant cubed. Okay, so this and that are both on both sides, right? So what you can do is you can, you just add this on that side for it to cancel, so you no longer have our original integral, and this side you can actually combine like terms. So adding an integral of secant cubed on both sides, one integral plus another integral makes 2 integrals, right? And then you get just the integral of secant cubed. Other side, this remains the same. And then this is different, right? But it is still standard result. We have the natural log of the absolute value of secant x plus tangent x. Okay. And then, of course, adding this to adding the positive part of this term right here to itself, it just cancels. So all of our integrals are now isolated on the left-hand side. And to be able to get the original integral back, right, we're trying to integrate secant cubed. There's just a 2 here, so we just divide everything by 2. Therefore, our original integral, secant cubed x dx, is equal to everything on the right-hand side divided by 2, right? So you get 1/2 secant x tangent x, and then, of course, 1/2 times the natural log of all this, secant x plus tangent x. Okay, and there you have it. We see that we've now isolated our integral, and there's no more integrals on the right-hand side, so this is our final result right here. So add c to this, and then we got it. Okay, now I strongly suggest you to remember this because this actually appears in quite a few cases of trig sub, right? And it's actually more common than you'd think. So, and because deriving this result is kind of lengthy, and by the time you're doing trig sub, you're probably already pretty tired. Call this a standard result and just keep this in mind, right? It'll help you a lot with many trig sub cases. So yeah, that's it for number 24. Okay, and number 25. Number 25 is, we've got the integral of 1 over, we have x times the square root of 9x squared minus 1. And then here I'm just going to put 1 on top and a dx on the side. So yeah, this is what we're trying to do. And let's get straight into it. Because you see that we have a quadratic that is not a perfect square inside of a root. So yeah, trig sub. But how do we do it when we have a 9x here, right? Well, you're either able to factor the 9 out from both of these terms on the inside and then just use the a times trig function method, right? Or, on the other hand, you're also able to just rewrite this real quick. Let's treat this as it's so instead of 9x squared, let's treat this as 3x all squared, right? since distributing the square, you find that it still works. Okay, so right now, all we need to do is, this is difference of squares, where our variable, call it 3x, is in the first term. So we want the entirety of 3x to be secant, because secant squared minus 1 is tangent squared, and the root and the square cancel in the tangent. So, here we go. We want 3x to be equal to secant theta, right? And then differentiating both sides, you get 3 dx is equal to, well, you know what, let's isolate x first, since we're also going to need that right up here, right? Isolating x, you get that. X is equal to 1/3 secant. And of course, then we differentiate both sides, we get dx is equal to 1/3. And the derivative of secant is secant theta, tangent theta d theta by chain rule. Okay, and yeah, so let's write it all in. So first of all, let's write whatever's in the denominator. This x is just equal to 1/3 secant theta. And then the top, there's a 1/3 secant theta, tangent theta. And then, of course, this root, as we said earlier, if we just plug secant theta into where 3x is, then we get a normal tangent, right? So let's put down a tangent here. And then, of course, we have our d theta. Now, what you may notice is that the entire top cancels with the entire bottom. So what you're left with is nothing but the integral of d theta. And, of course, integral of d theta is simply theta. And theta, if we just isolate it real quick by taking inverse secant on both sides, you get inverse secant of 3x is equal to theta, right? So this is equal to the inverse secant of 3x. And then add c and you're done. Right? Pretty fun, because it's satisfying. And in fact, without the 9, if you just get rid of the 9, 1 over the x times the square root of x squared minus 1 is actually a standard integral. And it is actually, this is actually just the derivative of inverse secant. And it should be standard, but it's kind of convoluted since it's rarely used, right? This form is kind of hard to come by. Yeah, but, I mean, that's it for this one. Number 25. Okay. Next we have number 26. We have the integral of cosine root x dx. Now, earlier what we did was, when we work with roots, is that if we let u equal to the root with the linear term on the inside, and in this case it's really nice, it's just x, then the differential is nice, and also it's also nice to find just x by itself. So, yeah. And of course, it's on the inside of the cosine, so there's not much else you can do with this. So yeah, let's just let u equal to root x. And then squaring both sides, you get u squared equals x. Differentiating both sides, you get 2u du is equal to dx. Alright, and then here we just get, since the 2u du is multiplicative across the entire thing, I'm going to take the 2 outside, since it's a constant, and the u, put it up here. Next we have our cosine of root x, and in fact, root x is just u, right? And then, of course, we already counted for the 2 and the u, so we just left with a du we need to put down. Okay. Next, we do integration by parts, because you see that there's a polynomial here, and it's multiplied by a trig function that is nice to integrate. So let's differentiate u, and then this will get us 1, and then down to 0, and then integrating cosine u, very nice, you just get sine, and eventually negative cosine. So we multiply diagonals, and since we hit a 0, no need to multiply the row, integrate the row, sorry. And don't forget the 2 that's sitting on the very outside. U times sine u. And then negative 1 times negative cosine u, which is just a positive cosine u. Alright, and then what you want to do is you want to distribute the 2 towards the inside, so you get 2 times the first term, and of course I'm going to write this in terms of x again. U is just root x. And we have our sine function, and then the argument of sine is a u, which is also root x, right? Alright, and then don't forget we're distributing the 2 inside, so we get a 2 times cosine of u is just root x. And actually, that's it. Just add c, because we are done. Right? Yeah. Okay. So that is number 26. Okay, and number 27 is one that you might come across kind of frequently, but it's relatively standard. You should be able to memorize it because no one wants to do all the work. Again, to be able to derive this, but now everyone knows. Well, I showed you earlier how we do the integral of secant, right? And cosecant is not all that different. Only difference is that there's a negative that lingers in there somewhere, since cosecant, there's typically some negatives when it comes to calculus, whereas compared to secant, which is all, the polarity remains maintained. So for this one, it's not all that different, right? Than integrating secant. Integrating secant, we just multiplied an a over a, and a was equal to secant x plus tangent x, right? But for cosecant, we're actually going to instead of secant, we're going to use cosecant. And then instead of tangent, we're going to use cotangent, right? And one more thing, instead of adding, let's subtract. Because this will help in our substitution. Distribute this out, you get cosecant squared. And then x, right? Then you want to subtract off minus cosecant x, cotangent x. Here in the bottom, you see that, yeah, okay. So let's put down a negative cosine first. Yeah, let's put down the negative cosine, cotangent, oh my goodness. Shush. Fuck. Okay. I'll just redo it, I guess. There's no point in trying to... Oh my goodness. This is exactly what I'm trying to avoid in these meetings. It's fine. Okay. Fucker. Integrate. Okay. Integral of cosecant x dx. That's number 27. And then, of course, this is very similar to secant, right? But instead we have cosecant, right? So when we're dealing with the u substitution part of the integral, we're actually going to deal with some negatives. So it's slightly different, but very, very similar flavor. So for secant, we multiplied in secant plus tangent, right? But here we're going to multiply in a cosecant and a cotangent. And because of the negative that we're going to deal on later, we're actually going to make this a negative. All right, and then of course we have to divide by the same thing. All right, and then now distribute out the top. You get that the top is just cosecant squared, right? And then minus cosecant x, cotangent x. In the denominator, you see that differentiating negative cotangent, you actually get the first term, right? And then differentiating cosecant, you actually get the second term, including the negative. And that's why we make this negative, so that the opposite polarities would actually sort themselves out. So the bottom is still cosecant minus cotangent. And of course, we just established that the top is just the derivative of the bottom. So we let u equal to the bottom. And then differentiating both sides with respect to, well, their individual variables, we get that du, because that's what you get when differentiating u, is equal to differentiating let's differentiate negative cotangent first. You just get cosecant squared, right? Since the derivative of cotangent is negative cosecant, so negative cotangent would therefore give you normal cosecant. And then differentiating cosecant, you get negative cosecant x, cotangent x. All right, and then dx, right? Because that's chain rule. All right, and then now all we need to do is just rewrite this as du over u, because the top is just the derivative of the bottom for like the 50th time. All right, and then this form is just very recognizable. We just got the natural log of u, and of course u is equal to cosecant x minus cotangent x. So this is the natural log of cosecant x minus cotangent x. Add c, and right, you're done with this one. So cosecant slightly different from secant, but at the very end it looks very similar. Okay, so that's it for this one. Number 28. All right, for number 28, we have, that's a pretty big indicator of what we have. Anything inside of a root looks kind of scary. So we have integral of the square root of x squared plus 4x plus 13. Okay, so anytime you see, and I explained this earlier, but anytime you see a trinomial of degree 2 inside of a square root, then you typically want to do a trig substitution, right? But that can only be done if it's in the form of different squares or sum of squares. And to do that, all you need to do is complete the square. So to complete the square for x squared plus 4x, you just add on it 4, right? So we need to split 13 into a 4 and something else. So here we have the 4, and the other part is going to be 9. And then we can rewrite this perfect square trinomial as a binomial squared, like this, right? And then now you can treat this as one variable by making a u substitution. Let u equal to x plus 2, therefore du is equal to dx, right? So you're just integrating the square root of u squared plus 9. And du is equivalent to dx. I'm going to plot that in right here. Okay, so that was our preliminary work before all the integration. So yeah, now is where the integration actually begins. Because to do this, you see that this is in the form of sum of squares. And you would use inverse tangent for this. Now, you want this variable up here to be a times tangent, right? So what is a? A is just the square root of the other term, right? So a would just be 3. And then, of course, times tangent theta, all that stuff. And then differentiate both sides, you get du is equal to 3 times secant squared theta d theta. Nice, right? Now, we just plug it all in. And in fact, what you get is that after plugging in 3 tangent theta in here, you distribute the square, you get 9 times tangent squared plus 9. So I'm going to put that down. And then, of course, don't forget your differential. And I'm going to, because the 3 is multiplicative, I'm going to move it outside. And then we have the function part. We have secant squared theta d theta. Okay. So now, if we want to keep it short and concise, we can this entire root right here, this is just equal to the root of, you can factor out a 9 on the inside, right? So there's two things you can do here. The root 9 can just become a 3, and then the tangent squared plus 1 is just a secant squared, and then taking the root of that, you get just a secant. Right, so this is just 3 times the integral of, this is 3 times secant theta, so in fact I'm going to bring the 3 outside. So 3 times 3 is a 9, so there's a 9 sitting outside. This thing just becomes secant theta. You multiply by secant squared theta, you get a secant cubed theta. And this is what I meant when I said that the secant cubed shows up everywhere. Let's pretend like we've got this down, right? So this is equal to, and then, so let's distribute in the 9 as well. So this would be not 1/2, but 9 halves times secant theta tangent theta, right? And then we add, distributing the 9 again, you get 9 halves natural log of the absolute value of secant theta plus tangent theta. Okay, so now let's go back to the x world, right? And in fact, to be able to do this, we have another layer of substitution right here, u, right? But here is a case where we're able to go straight back to x by just finding what theta is in terms of x, right? So right here, let's do this down here. X plus 2 is equal to u. And then we also get that u is equal to 3 tangent theta. So therefore, x plus 2 is equal to 3 tangent theta. And therefore, subtract 2 on both sides. But yeah, for now, I'm going to work with this, since you need to be able to find what these trig functions are algebraically after going back to the x world. Okay. So, from here we can get that, if you want to isolate theta, first divide by 3 and then take inverse tangent on both sides, you get that inverse tangent of x plus 2 over 3 is our theta, right? Right, so keep this in mind, because we're going to go straight from these trig functions back to our x world. And to do that, we have to draw a right triangle, right? Since we know what theta is, we know what secant is in terms of our other variables. However, what about tangent, right? So let's find tangent. So this is the ratio that we're working with. The inverse tangent of opposite over hypotenuse gives you the angle of theta, right? So we're going to call this theta right here. And then, of course, inverse tangent, the argument is just the opposite over hypotenuse. Sorry, not hypotenuse, adjacent. So opposite is this. And adjacent is our 3. So to do this, we just take the square root of this squared plus that squared. And in fact, you see that that's actually what we have right here. And this comes directly from this. So instead, let's just write this as the square root of x squared plus 4x plus 13, right? Makes sense. Right. So our triangle is complete. Now we just go right back here, right? So first we need 9 halves of, well, we know what secant theta is equal to, right? We noted down here that, I was speaking incorrectly. We know what tangent theta is equal to. We don't know what secant theta is equal to. So we didn't solve for tangent here. We know what that is. We solve for secant, right? Okay, so 9 halves. What is secant? Secant is reciprocal of cosine. Cosine is adjacent over hypotenuse. Therefore, secant is hypotenuse over adjacent. So we have root e boy over 3. Next, our tangent, we know what this is from, if you just divide both sides by 3, we see that tangent is equal to x plus 2 all over 3. And what you notice in this first term right here is that 3 times 3 is 9. So these two cancel with that. All right, so that's pretty fun. Secondly, right here, this is, 9 halves times natural log of. Notice how secant and tangent both have adjacent in their denominator, right? Secant is hypotenuse over adjacent, and tangent is opposite over adjacent. But regardless, they both have adjacent in their denominator, so I'm going to actually write it like this. And also for another purpose that you'll find out later, but we notice that secant is this over that. I have 3 accounted for, so let's just put down the root, right? X squared plus 4x plus 13. And then, of course, don't forget the tangent part, which is just x plus 2 over 3. However, we accounted for the 3, so let's just put down plus x plus 2. All right, so we might have done this earlier, we might not have, but notice how this is a quotient inside of a natural log. So you're able to break this up, right? So let's rewrite this all. First of all, we see that up here, we have a 1/2 instead of a 9 halves because it cancels with the 3's in the denominator. Let's put down the linear term first. We get x plus 2, and then we put down the root, right? X squared plus 4x plus 13. Secondly, I want you to notice this natural log right here. 9 halves, of course, right? But we can actually break this into 2, right? The numerator is added, and then we just subtract off 9 halves times the natural log of 1 over 3. Well, no, just 3, right? Because we're subtracting already, so we have to just take whatever's in the denominator. Okay, so right here, let's put down our function again. I'm going to write the x plus 2, and then plus root x squared plus, okay, we're running out of room. Let's write this in the row below. And then we add on natural log of x plus 2 plus square root of x squared plus 4x plus 13. Right? And then what we can do is we can put the minus 9 halves natural log of just simply 3, right, into the other row, right? And then, right, before we add c, because this is pretty finalized, you want to note that what we broke off right here is just a constant, right? So this can be incorporated into our c, so we really don't need this right here. Just add c, and that will account for any shifts up and down in our graph. There we go. That is it right there. That's number 28. Okay. Let's do number 29. Number 28 was a big, trig fest, I guess. Not really, but involved a lot of layers, and this is the kind of problem that's really tiring, right? Like working with something that looks as ugly as that, but yeah, and it's doable, but it's still going to take a lot of brain power. However, number 29, not so much, since this is actually not as uncommon as you think. This is integral of e to the 2, e to the 2x cosine x dx. And yeah, this is just 2 separate functions being multiplied together. Let's just use integration by parts, and let's just differentiate the exponential, and doing it a few times. You get 2e to the 2x here by chain rule, and then multiply the 2 down again, you get 4e to the 2x. Integrating, you would integrate cosine, and that would give you sine. Integrating sine, you just get negative cosine. Multiply diagonals, and integrate the rows. Right? Okay, so multiplying diagonals, and in fact, let's rewrite this, since notice how this is a repeating case. Our function part, e to the 2x times cosine x, that's what was there originally. So that's how we're going to find the solution to this integral. So therefore, our original integral of e to the 2x cosine x dx is equal to, first let's multiply the diagonal, so we got this times that, that's e to the 2x sine of x minus, well, double negative, right? So that gives you a positive, and then 2e to the 2x times cosine x. Sorry, okay, it looks, whatever, that's okay. And then finally we have the row that we must integrate. So I'm going to bring the negative outside and the 4 outside because those are both constant. And then we're just left with the function part, which is e to the 2x cosine x dx. Alright, so now we just, because it's a repeating case, we want to get all the integrals on the left-hand side. Let's just add 4 of these integrals on both the right and the left-hand side. Right, so on the left-hand side, what we get is 1 integral plus 4 integrals equals 5 integrals, right? And then on the right-hand side, just as usual for any other repeating case of integration by parts, you just get that the integral disappears because what you did just canceled this out. That's the whole point. All right, right here, all I need to do to isolate our original integral, which is this without the coefficient, is divide by 5, right? So you get the integral, and then divide by 5 on both sides, meaning each of the terms on the right-hand side are now going to be over 5. So we have 1/5 e to the 2x sine x, and then plus 2, but now it's over 5, e to the 2x cosine x, add c, and there we go, that's it. Pretty fun. Okay, so that's number 29. Number 30 is a small break from reality, right? Like, this is all requires some computation. Number 30, not so much. And it appears as if my black pen is starting to run a little bit dry, but that's fine. Number 30 is the integral from, we have a bounded integral, of course, so 3 to 5 of x minus 3 to the 9th. Very, very simple appearing as compared to what we've done before because, well, first of all, don't expand this out using the binomial theorem. It's not going to treat you very, very nicely, right? Because, well, I mean, you get 10 fucking terms out of this thing, and the coefficients are going to be huge. Right, so what's the other option? Well, you already have it nicely written here for you. Just use a u substitution because this inside is linear, right? So let u equal to inside x minus 3, and then differentiate both sides. You know, both your differentials are going to be equal. And of course, this is x bound. You want it in terms of u, so just, well, let's plug it in. Plug it into here, right? 3 minus 3 is just our u value for the lower bound, and that is just 0. For our upper bound, plug in, this is an x value. Once again, you want to solve for the u value, so plug it in. 5 minus 3 just gives you 2. Very, very simple. And then, of course, the inside right here, we set to be u, and it is still to the 9th power. Dx is equal to du, so let's just plot that in here. This is a very simple case of reverse power rule. So, get 1/10 times u to the 10. And don't forget, you're evaluating from 0 to 2. Of course, this is a polynomial. Evaluating at 0 is just going to return the constant term. There's no constant term. This is going to return a 0, right? Just plug in 2 then. So you get 1/10 times 2 to the 10. And, of course, there's a numerical value for this. And so the way you would solve for this manually is probably just to break the exponent up, right? Like, you have 2 to the 10 is equal to 2 to the 7 plus 3, which is equal to 2 to the 7 times 2 to the 3. Most people know, like, what 2 to the 7 is equal to. You can also break it into, like, 2 to the 5th plus 2 to the plus 5, right? Because that gives you 32 times 32. Just work this out arithmetically. 2 to the 7 is just 128. And then 2 to the 3rd is 8. And I chose this combination because 8 is our single-digit number. We're just able to mentally do the math, right? 8 times 8 is 4, carry the 6. 2 times 8 is 16, add the 6, you get 22. Carry the 2, 1 times 8 is 8, and then you add on the carried 2, you get 1,024. And don't forget that this is just this part. You still need the 1/10. Just move the decimal digit in. Final answer, 102.4. Don't add c, since this is, of course, a bounded integral. Okay, so that's it for number 30. Okay, number 31. Is another indefinite integral. We're back to the grind. So in the denominator, you have square root of x minus x to the 3/2 power. Kind of weird, but think about it for a second. How do you make it look better? Factor out an x. There's both an x and an x. So factoring out an x, we get a root x on the side, right? Because keep in mind, it's still inside of this big square root right here. And then inside the square root, this first term divided by what you just factored out gives you 1. And the second term, x to the 3/2 divided by x just gives you x to the 3/2 minus x to the 2/2, which is x to the 1/2, which is just, you can rewrite that as the square root of x. I'm going to put that down like this. Alright, this one, really simple case, since you can see that the derivative of the inside of this black radical right here is very similar to what we have out here, 1 over root x dx, right? So let's just make a u substitution. Let u equal to the inside of the black radical, and then differentiating both sides, you get du is equal to negative 1 over 2 root x dx. And right here we see that we have the 1 over root x dx, but not the negative, and neither do we have the 1/2. So multiply by 2 on both sides and the negative. So negative 2 du is equal to 1 over root x dx. We have the 1 over root x dx, right? So because what we have in here is multiplicative across the entire thing, I'm just going to take the constant outside. In there, the 1 over root x we have taken care of by our differential. How about the radical? Well, the radical, the inside is just our new variable. So it's a lot simpler than substitutions might be sometimes. And then, of course, our negative 2, we accounted for the negative 2 so far. We just put down the du. Okay, and this is a simple case of reverse power rule, because rewriting this, well, this is 1 over u to the 1/2, right? And then because it's in the denominator, if you want to write it like this, u to the something, this would just make the exponent negative, so you get u to the negative 1/2. Add 1 to the exponent, right? And then divide by the new exponent. Dividing by the new exponent, which is 1/2, you're dividing by 1/2. So you're multiplying by its reciprocal, which is just 2. And then you have u to the normal 1/2, as we said earlier. Right, okay. So multiplying these two, you get a negative 4. And then u is our 1 minus root x. However, it's all to the power of 1/2. So we can rewrite this 1/2 as a big radical. And then we have our u in here, which is really just that. So we just put down 1 minus root x. There we go. Add c, and you're done. That's number 31. Alright, what about number 32? And I'm going to put this down right next to it, because number 32 has a very similar flavor. It looks almost the exact same. 1 over the root of x minus x. This time it's to a whole number. And you might anticipate this would be easier because there's a whole number, but give it a second. It might not be as easy as you think. Let's do the same thing, right? See that there's an x and an x in common. Currently, you can't do anything, so let's factor out the root x and see how it goes. So factoring out the root x, this goes here, right? And then in here, you just have the 1 minus normal x. Now what? Well, I mean, doing u substitution wouldn't cancel out as nicely as it did for our first problem right here. However, we're still dealing with a bunch of roots, so, I mean, we can give it a shot, right? It looks kind of unpredictable as to what's going to happen right now, so let's just try letting u equal to that, as we kind of did before. But here it's different because we let it be the inside of the radical. Here, there's no point, because all that does is, like, change where the constant lies. Right. So let's just let u equal to the entire radical and see what happens, right? Let u equal to the square root of 1 minus x. Differentiate both sides. You get du is equal to... and, okay, well, in fact, what you're able to do here is isolate x. So regardless... So, and because of that, two things. You're able to replace this existing x, which you're originally not sure about, with an expression purely in terms of u, and that probably looks nice too. And your differential is also going to be purely in terms of u. So, right here, isolating u, squaring both sides, and then subtracting 1, right, you get this. And then simply reversing the order of subtraction by multiplying both sides by the negative, you get 1 minus u squared is equal to normal x. There we go. Alright, is there anything else? Well, yeah, we have to calculate the differential, right? So differentiating both sides, differentiating the left side, you get negative 2u, and then with a chain rule, you get a du. And then on the right side, you just get dx. Okay, so here we go. This square root right there, the x is just equal to 1 minus u squared, as we can see right there. And then the second radical right here, we just said was going to be our u. So let's put that u down first. All right, and then this was a radical, but now it has a 1 minus u and u squared in it. And of course, our differential is just that. So I'm going to put down the negative 2u on the top and the du on the side. Notice that the u in the denominator cancels with the u in the numerator. Bring the negative 2 outside, and you find that this is a standard integral. And the first time we've seen it today. This is just, the inside of this is just the derivative of inverse sine. And you can prove this using trig sub, right? Just because you see there's another quadratic inside of a root. However, I'm not going to do that since this is actually really standard. We're going to just replace this with the inverse sine, of u. And of course, u is just root over 1 minus x. So I'm going to just put that down. And there we go. That is our answer. Yeah. And that's it for number 32. Okay, so next we have number 33. 33 is pretty hilarious, if you ask me, but I mean it's there, so let's do it. It is the integral of e to the 2 times natural log of x. E and natural log cancel, but there's a 2 there. So, but because the exponent is 2 things multiplying, it's really just e to the natural log of x raised to the 2, right? You can also write it as e squared raised to the natural log of x, but that's no fun. So, e to the ln x first. And this is all raised to the second power, right? And of course, you know that this simplifies down to an x. And the squared stays. So you're just integrating x squared. Yeah, and then integrating x squared reverse power rule 1/3 x cubed plus c. That's it. There's really not much to this question. All right. Okay, number 34. We have another integral. We have an integral of natural log of x over root x. We know how to differentiate natural log, not so much integrate it, and we know how to integrate this root x in the denominator. I propose we use integration by parts. And I'm going to use the DI method again. So we would differentiate what we don't know how to integrate, and this would give us a very nice answer of 1 over x, right? Integrating 1 over root x. Well, if you multiply 2 on the bottom and then a 2 on the top, then what you get is that integrating this is pretty simple. Since this is just another constant, move it outside, forget about it, right? Integrating this inside, this is a standard form of the root of x, right? So you get that. And of course, don't forget about the constant you have on the outside. So now, we find that once we multiply the diagonals and then integrate the rows, we find that our answer is just 2 root x ln x, and then we still have to integrate. Well, first of all, let's bring the 2 to the outside because we can, and it's probably nicer that way. Okay, multiplying a root x over x, right? There's a common factor on both the top and the bottom, and that's just root x. Dividing the numerator by root x gives you 1. And then dividing the denominator by root x, it gives you just normal root x. Alright, and then dx. Same situation as we had up here. We found that the integral of just 1 over root x, since that's what we were originally doing, right, is just 2 times root x. So we can put that down. Since either way, we're going to be using the exact same strategy. So we have 2 root x. Don't forget, constants multiply together. So this is minus 4 root x, add c, and that's it for this one. Alright, I'm going to replace my black pen soon after we finish the next one. Okay, number 35. We have integral of another exponential. We have 1 over e to the x plus e to the negative x. Now, if you want all the exponentials to have like a positive exponent, which is probably a lot of people's gut instinct, right, when encountering a problem like a rational expression in terms of e to the x, then, of course, well, let's just multiply by e to the x on the top and the bottom so that this cancels with that, and we'll see what we're left with. So on the bottom, e to the x times e to the x is e to the 2x, right? And then on the bottom, we have e to the negative x times e to the x. They just cancel, you get 1. On the top, 1 times e to the x is just normal e to the x, and then the dx stays dx. Alright, next, what you notice is that you can rewrite this e to the 2x down here as an e to the x all squared. Right? And here, you find that, well, you can just make a substitution, right? You let u equal e to the x, and then the top is just your du. And then you get, like, a real rational expression. So, let u equal to e to the x. Differentiating both sides, you get du is equal to e to the x dx, which we have right up here, so we can just replace that. So, here we go. This is just 1 times du now, so I'll do that. In the bottom right here, e to the x is just u, and it's still squared, and you're still adding 1. And then, of course, we have to cap it off with our du. Now, this is standard. As we said earlier, this is just the inverse tangent of u. And, of course, u is up here. We said e to the x, so I'm going to write it down straight up like that. Add c, and you're done. Okay. Alright, I'm gonna grab a new black pen. Okay, got a new black pen. Let's keep doing integrals. Number 36. We have the integral of log base 2 of x dx. Now, just like earlier, we don't know how to integrate log, but we sure know how to differentiate it. And before we actually do that, I'm going to split this into something that's nicer to work with using a log property, right? So, a log base b of anything, right, is just a log base anything of, well, here. Here we can break this into log base anything we wanna of the argument, and then divide it by the log base, the same exact thing. Okay, it needs to be the same base here and here, but it doesn't matter what the base here is as long as you put it into the argument of the base in the denominator. And of course, we're going to use log base e, right? Because that's just natural log, and natural log is nice to work with. So first of all, you see that dividing by this, that's just a constant being multiplied in. So we're going to bring that outside, right? And then inside, of course, we just have log base e of x, which is natural log x dx. All right, and we know, and okay, I'm going to get on with what we're going to do. Differentiate this. That means we have to integrate, well, in fact, I'm gonna do something else, right? Okay, so for inverse functions, of course, you're able to differentiate. You're able to use integration by parts, right? Differentiate the inverse function to get something that's nicer, and then integrate another, like just one, right? Because this times one is still this, right? However, another method you are able to use to do this is just a substitution. If you let u or any variable equal to the inverse function, right? Then you're able to isolate x because this is an inverse function. And typically, it's nice to isolate x, so we end up getting x is equal to e to the u, right? By taking e base e on both sides, and then just taking the differential, and also. This method also works if there's any other, like, x is just sitting inside of here being multiplied in or being added on. Or, but yeah, this is just a tip for integrating inverse functions because you're almost always able to isolate x. Then you just want to find your differential. Not so bad, right? And of course, we see that e to the u is, well, it's x, so I'm not going to do much about it, but yeah. So we are still trying to integrate 1 over natural log of 2 times the integral of, now we just have this is our u, right? And then we multiply by e to the u du, which is our dx. And I'm pretty sure we might have done this earlier, but regardless, we see a polynomial and something that's very, very easy to integrate. You just set up the di method. So I'm going to explain this again later, since I'm going to do it both ways as we go on with this video, but you're still going to end up using integration by parts either way. So differentiating u, you get u, then 1 and then 0. Integrating e to the u, that you just keep getting e to the u. Alright, multiply, and then there's no row to integrate since you're all done. So I'm going to write this. Let's go up here since it's more accessible. So our first diagonal, since you can't really see it, you get u e to the u. Second diagonal, you get minus, and then 1 times e to the u, which is just e to the u. All right. Here earlier we set u to be natural log of x. So first of all, e to the natural log of x, that's just x. So I'm going to put down an x, and then u is just natural log of x. Subtract off an e to the u, which is e to the natural log of x, you just get x again. And in fact, right in this case, it might actually be easier to use integration by parts first. Oh, and sorry, that's not right since we need to multiply in the 1 over natural log of 2, so. Okay, but, so we have our 1 over natural log of 2, and also that's the case here, but I'm going to just put it like that, right? So this times that term, which earlier we determined was x natural log of x, and then subtract off, well, we distribute in the natural log of 2, right? So we do that, and then we just have an x. And I'm going to add c yet, because you see this is an ln x in the numerator over the ln 2 in the denominator, so this returns, well, the x factor is still going to be there, but then ln x over ln 2 is going to give you log base whatever's in the denominator 2 of whatever's in the numerator x, right? And then here we can rewrite this as x over ln 2. All right, now we can add c because this is fully simplified. Yeah, that's number 36. What's our next one? 37. We have the integral of x cubed times, sine of 2x dx. Very, very similar to what we just did. We can do integration by parts because there's a factor that's a polynomial, easy to differentiate, and it goes to 0. And we also have a factor that is very easy to integrate, right? So we differentiate that. And then, let's just do it like this, right? Differentiating x cubed, you get 3x squared. Differentiating 3x squared, you get 6x. Differentiating 6x, you get 6. Doing that one last time, you get 0. Sine of 2x. So you would integrate sine of 2x. First of all, notice on the inside, there's a 2x. You have to use reverse chain rule, right? Divide by 2. Integral of sine is negative. Out here, cosine. And then the argument remains the same. And then reverse chain rule again. Now this becomes 1 over 4. Integral of cosine is just sine. So, and the negative stays outside. All right, integral of negative sine, you get normal cosine, and don't forget reverse chain rule. 1/8 cosine. And then the process repeats. Integral of, first divide by 2, right? 1 over 16. And then integral of cosine is, as we said earlier, it's just sine. Okay, so it's a pretty big integration by parts problem, but it also demonstrates how UDV is slow, right, for a lot of applications of this. So we can just multiply the diagonals and no rows to integrate since it went to 0. All right, so this we can just write it all out. And I'm going to write it slightly smaller since I'm going to try to fit it all in one line. First, we have x cubed times negative 1/2 cosine of 2x. Oh, we actually have a like term in here? No, we don't. Okay, we're fine. So, this times that, I'm going to write the coefficient out front, and then our polynomial, and then our trig function. Okay, then negative gives you a positive. 3 times 1/4 gives you 3 times 1/4 is just 3/4. All right, and then our polynomial is x squared, and then our trig function is sine of 2x. All right, next diagonal, we have 6 over 8. 6 over 8 is just 2 over 3. Sorry, no, not 2 over 3, 3 over 4. And then we have x, our polynomial. I'm going to put that down first, and then our cosine of 2x is the trig function. Finally, we have a minus sign. 6 over 1 over 16, you divide by the top. Well, you know what, it just reduces straight down to 3 over 8. I'm not even going to try do it the complicated way. And then we just have only our function, so we just have sine of 2x. And then plus c. I wrote it kind of small, but I'm not sure if you're able to see it very well, but just integration by parts using the DI method. Okay, and I think that is the correct answer. I just need to check the coefficients through once, and it seems like it's right. So, that's number 37. It's literally a 1-2-liner with some work in the middle. Just ignore it. You know? Say it's a 2-liner, 1-liner. All right, number 38. Number 38, we have the integral of x squared times root of 1 plus x cubed. And in fact, it's not a normal root, it's a cube root. Okay, so take a look at the more complex function that's being multiplied in. On the inside, you see a 1 plus x cubed, and you see the derivative of that is actually very close to x squared. Right? It's just a constant times x squared. So let's just do a u substitution. Let u equal to the argument of the cube root, 1 plus x cubed. And then let's differentiate both sides. So we have du is equal to 3x squared dx by chain rule. And then here we have our x squared dx, right? But we don't have the 3, so let's isolate the x squared dx by dividing 3 on both sides. Alright, so here, because the 1/3 du is multiplicative across the entire thing, I'm going to just take the 1/3 and move it outside. And then in here, the x squared dx just became our differential, so we still have our cube root, however. And then the 1 plus x cubed is our u. And then, of course, everything else is just the du. Alright. Okay, so we can rewrite this exponent, right? We can rewrite this as an exponent, sorry. We get u to the 1/3 du. And then now it's just a case of reverse chain, power rule. Add 1 to that, and then divide by it, right? So dividing by 4/3, you get 3/4. You multiply by u, which is now to the 4/3. First thing, you see that these 3's cancel. So you just get 1/4. And then the u is, well, first, let's rewrite the exponent, right? So the 3 in the denominator of the exponent is really just a cube root of the u squared, of u to the 4th, right? But then we know that u is just 1 plus x cubed. But now it's to the 4th power. And then we add c and we are done. Alright, that is number 38. Number 39. Number 39 is one that I have a fond emotional bond with because of how much it confused me initially. But, okay. So, it may not, well, it looks nice. However, it's not in a square root. The quadratic isn't in a square root, it's in a square. So you might try to expand it out and do some stuff, treating this as a rational expression, maybe partial fraction decomposition. Well, you can't really do that since it's already factored, but you might try something like that. But you gotta notice that the squared is just another factor on top of the sum of squares in here. And we can still do a trig substitution like we do for, say, tangent, right? Where you have a sum of squares in the denominator, right? Like, if you think about inverse tangent case, where we get that from is 1 over just the sum of squares. There's no root even. And we're still able to do trig sub to find that. So that doesn't stop us from doing trig sub here. So let's do that. Right? Okay, so you would use tangent because this is a sum of squares case, and also we need our a value, which is the square root of the second number, which is 2. Alright, now we just differentiate both sides. And then we plug it all in, right? So 1 over, well, let's distribute the square. We get 4 times tangent squared theta, right? Plus 4. And then, more importantly, it's all squared. And on top, you get 1 times dx is equal to 2 secant squared theta times d theta. Okay. So for the inside here, let's factor out the 4 first. Factoring out a 4, you just get a 4 times all that other crap, all squared, right? So you can actually distribute the square onto the 4 and the other crap. So you get 4 squared, which is 1 over 16, right? And that's, yeah. So you have 2 secant squared theta. And the bottom, you just have a 16. That comes from factoring the 4 out, right? Secondly, tangent squared plus 1 gives you secant squared. And then remember, there's another square on the outside here. So that gives you secant to the 4th power. And still with respect to theta. Top shouldn't be in red, but I'm going to ignore it for now. Alright, 2 over 16 reduced down to 1 over 8, which is just a constant, so I'm going to move that outside. Secant squared over secant to the 4th is just 1 over secant squared, right? However, 1 over secant is just cosine. So this is really cosine squared. And cosine squared is just Very simple. We know what the formula is, right? So I'm going to take the 1/2 outside first. And then integrate. On the inside, we just have 1 plus cosine of 2 theta. Which, of course, now you're just able to integrate. And 1/2 times 1/8 is 1/16. So integrating a 1 in the theta world, you get a theta. And then integrating a cosine of 2 theta in the theta world, you have to divide by 2 first, right? Because of reverse chain rule. And the integral of cosine is just normal sine. Argument remains the same. Right, so distributing out the 1/16 now, you get this is equal to 1/16 theta plus 1/32 sine of 2 theta. Okay, so we came from the x world. Let's go back there. And before we do the the triangle stuff, notice that we can't really plug it straight into here since there's a 2 times all that crap. Let's use a double angle identity to split this into normal trig functions with the argument is just a single variable. So the 1/32 stays, but you have a 2 times sine times cosine. Alright, so now we know what tangent is, but we don't know any of this crap, right? And what about theta? So isolating theta here, divide by 2 on both sides. And then taking the inverse tangent, you get inverse tangent of x over 2 is equal to your theta. Okay, that's part 1. So next up we have these two. So let's just set up a triangle again, right? Our angle, we're going to call it theta. We have a right angle here. Tangent is opposite over adjacent, so opposite over adjacent. And then here we just have Pythagorean theorem, you get that. Okay, so let's write this down. 1/16 times theta, right? And we said here that theta is just inverse tangent of x over 2. So we got that part down. What about the second part? Well, first of all, 2/32, we can reduce that absolutely down to 1/16. All right, sine theta is opposite over hypotenuse. So we have x over that. X over the square root of x squared plus 4. And then our cosine is very similar, however, the adjacent is in our numerator instead. So we have 2 times the square root of x squared plus 4. All right, almost done. So the first term, not much simplification can be done. We just keep it the same. This is already fully simplified. However, the second term, 2/16, we can write that as 1/8, right? And then so all that leaves on the numerator is just a single x. So let's just write next in the numerator right now. Okay, in the denominator, we have this square root multiplied by itself, meaning the square root is squared, meaning it just, well, this time that just leaves the inside. Because that's how square roots work. So you're just left with the good old x squared plus 4. Add c, and that is what you get. All right, pretty fun. That's number 39. Okay. Number 40 is a rare bounded integral. However, it doesn't, well, I mean, it's a pretty complex question because we have another case where we just have a random root. Sitting there looking pretty in our integram. But we have number 40 being integral from 1 to 2 of the square root of x squared minus 1 dx. Tricks up, because this is a difference of squares, it's not a perfect square, so and because the variable is in the first term, we would use secant for this. So let x equals to secant, and we don't have an a value, our a value is 1 because this is also just 1. Differentiating both sides, you get dx is equal to secant tangent d theta. Okay. Secondly, you need to calculate the bounds. So we have 2 is equal to secant theta, and that means, and also 1 is equal to secant theta, right? Since these guys are in terms of x, so we just plug it into x, and we want to find their theta equivalent. And you can see we can take inverse secant on both sides. And it might not seem very nice, but let's work out the trig on a unit circle. So secant is 1 over cosine, and what you get after cross multiplying, multiply cosine both sides and divide by 2, you get that you're trying to look for where cosine is equal to 1/2, right? And that exists in 2 places. However, if you're working on the domain of our cosine right here, then you're really looking at only the upper half of the unit circle, since this is all places and each x value is only represented 1 time. And of course, we're trying to figure out what the x value is based on cosine. And our x value is 1/2. So, cosine is our x, right? So where on this unit circle, what angle do we have to draw to get to the point on the unit circle where our x is equal to 1/2, right? Because it's obviously just up here. So the angle would look like this. And because it's a larger angle, okay, well, first of all, the angle is either pi over 3 or pi over 6, right? Or pi over 4, but that's only when it's like diagonal, right? And that value is is not a rational number. So you know that this is a larger angle, meaning it has to be our pi over 3, right? Therefore, our theta, well, I'll call it A because, theta B, right? Because this is our upper bound, and typically upper bound is represented with B, since A to B. We're going to call it pi over 3, because that's the angle that is formed to be able to get to where x is equal to 1/2 on the unit circle. So it's not actually that bad. And similar thing with, here you would just get, with the same steps as we got to there, we would get that we're looking for cosine is equal to 1, right? And that is even easier because where cosine is equal to 1, well, you're just finding where on the unit circle x is equal to 1. And that is right there where a unit circle hits the x-axis, meaning you don't have an angle at all, right? It's just 0. So our lower bound is 0. So, okay, let's implement all of the stuff that we worked out. So our lower bound is 0 and our upper bound is pi over 3. This is, alright, plug in inverse secant. Secant squared minus 1 is just tangent squared. Square root of tangent squared, you just get normal tangent, right? So in fact, because this is just equal to tangent, I'm going to write our differential down first. Secant theta, tangent theta, d theta. And remember, we still need another tangent, but we already have a tangent here, so we just make it squared, right? Okay, and this is very, very similar to secant cubed, so we're going to be employing that result right here. And the only difference is that we use the trig identity on our tangent squared guy right there, and we get this is secant squared minus 1 distributed in the secant. You get secant cubed and then minus 1, right? So we get minus secant times 1, which is just secant. And because, well, these would be standard results if you've done integration for a while. Remember we did this earlier. I told you to remember it since it's going to pop out like every once in a while. And then we just have that, which is also another standard result. So integrating secant cubed, you get 1/2. And I'm going to draw an open bracket here to be able to draw a closed bracket with our bounds, right? We have 1/2 secant tangent minus, plus 1/2 natural log of secant plus tangent. And our second term is this integral of minus secant, and that is just minus natural log of secant tangent. Right, okay, and then we are going to close our black bracket, and of course our bounds are from 0 to pi over 3. So let's plug those in right here. All right, now before we do anything, notice how this and that, the function part, are similar. So these are like terms. So we just have 1/2 of this minus one of those. You get negative 1/2 of those. So this stays the same. But then this part changes. You get negative 1/2 of your function, which is natural log of the absolute value of secant theta plus tangent theta. Right, and then you would plug in your bounds, which is 0 to pi over 3. Real quick, let's plug in 0. In this first term, tangent of 0 is 0, and that zeroes out the entire term. Right? And then in the second one, secant of 0 returns 1, right? Because 1 over cosine of 0, right? 1, and then cosine of 0 is 1, so it's really just 1 over 1, which is 1, right? So this returns a 1. And then tangent of 0 is 0. So you just have natural log of 1, which is 0, so that zeroes out this term too, meaning this 0 is an empty 0. So now we just need to evaluate everything at pi over 3. And because there's two trig functions here, which we're not as used to dealing with as sine and cosine, well, me personally at least. So let's write out what each of these are evaluated at pi over 3. Okay. So secant, we know, is just 1 over cosine, right? And then cosine of pi over 3 is, well, if we go back to this unit circle, right? Cosine of pi over 3, that's exactly what we drew out here. You get 1/2. So, yeah, that's secant of pi over 3. No, you get 1/2 in the denominator. So you get 1 over 1/2. And then multiplying by 2 on both the top and the bottom, you just get a 2 over 1. So it's just a 2. Tangent of pi over 3, very similar. Also want to break it up into sine and cosine so it's easier to work with. Sine of pi over 3 is, well, you see the y value here is relatively great, and you know that the only other number that can correspond to a nice trig angle, either one of these, is root 3 over 2. So we just have root 3 over 2 on the top. The bottom, cosine of pi over 3, is just, as we mentioned earlier, 1/2. Multiply 2 on both the top and the bottom. That cancels out both of them on top, so you just get root 3 over 1, which is just root 3. Okay, so now let's just plug them all in. So 1/2 times secant of pi over 3, which is 2. Tangent of pi over 3 is root 3. All right, and then subtract off 1/2 times the natural log of secant of pi over 3 is, once again, 2. And then tangent of pi over 3 is root 3. All right, so two things you're able to do. First of all, this cancels to make a 1, so you get root 3 here. Next up, you're subtracting off 1/2 times this natural log right here, but you don't need the absolute values anymore since you know that this is always positive. And are we subtracting? Yeah, I mean, no. Are we subtracting or are we adding? Did I miss something? Yeah, sorry, no. This is a positive. Because, sorry, what? Wait, secant, no, this isn't positive. No. This is negative, as I said earlier, right? So, where did we miss something? It doesn't look like we missed anything. Yeah, actually, I'm pretty sure this is correct, but what I wrote down might have been wrong, huh? Maybe. Boy, yeah, I mean, it looks correct. I'm not sure. I'm going to have to trust that this is correct. Cause yeah, but we have minus 1/2 natural log of, and we can turn these into parentheses, of course, 2 plus root 3. I'm gonna look up whether this is actually correct or not. I'll be right back. Yeah. So yeah, what I got seems to be the right answer. Yep. Okay, so that's number 40. All right. Okay, number 41. We have our first instance of hyperbolic trig, and we're using the hyperbolic sine function. So we're just trying to integrate hyperbolic sine, right? So if you've seen this before, then cool. But if you haven't, then know that hyperbolic, well, I'll write these down. I'll write like important things down over here. But as a quick introduction, I guess, this function, hyperbolic sine with an h, you can quickly write it as this function right here, e to the x minus e to the negative x all over 2, right? It also has a counterpart, which is cosh, so hyperbolic cosine, right? And that thing can be expressed in a very similar manner, but with the plus sign here. Okay, now, so this is more similar to normal sine, the normal trigonometric sine, than we think. And that's why it's just called sine, but hyperbolic, right? Sinh or shine. So, sorry, no, this isn't normal e to the x, this is e to the negative x. So, if we're trying to integrate this, then all we're trying to integrate is really this function right here. And you can see you can do it mentally. The divided by 2 is just a coefficient, a common factor between both of them. You can bring that outside. Integrating e to the x, you get e to the x. Integrating negative e to the negative x, you get normal e to the negative x, right? So what you see is you just get cosh if you try to integrate sinh. So I'm going to write that down right here. So just know that the integral of sinh is actually cosh, right? And this is very similar for sine and cosine. Integral of sine is negative cosine. However, here, in fact, I'm going to write some more stuff down here. So, first of all, we know what the derivative of cosh is, right? Since it's just the reverse of integration, and you get this integrand right here. So, therefore, we know that the derivative of cosh x is equal to sinh, right? However, we also know that if we just differentiate it twice, then the negative sign, right, with chain rule, it goes back down here, and all the other functions stay the same. So therefore, differentiating sinh, right, gives you cosh. Since differentiating this guy also gets you here, because integrating negative e to the negative x and differentiating it does the same thing, right? With reverse chain rule or normal chain rule, the negative up in the exponent is going to bring itself down either way. So this is like a loop where they're the derivatives of each other, right? Similar to e to the negative x and negative e to the negative x. So yeah, these are just 4 very preliminary facts that you need to know in order to work with these. Alright, so that's it for number 41. It's not that bad, but we have more hyperbolic trig to come. Number 42 is very similar, right? We were dealing with sinh just a moment earlier. So let's do the same thing here, but now it's squared, right? Seems like the only reasonable next step. Now, it might be kind of difficult to think about what to do. Maybe you can do integration by parts, but don't, because it's not going to work. Maybe it would, but I'm not sure exactly how you would get that to work. Notice here, Well, we don't have anything here that could help us out. Actually, maybe you can derive it from here, right? Squaring this kid right there. So, what happens if you do that? Well, let's put this down here. If we take this, which is the definition of sinh, and then square it, then you can distribute the square among the numerator and the denominator. So you end up getting the numerator squared, which you can expand out, right? You get e to the 2x minus 2 times this times that, right? Which is, they cancel, so it's just a 2. And then you add back e to the negative 2x. Maybe I should do that, right? Alright, so that's the first part. And then the denominator, of course, becomes 4. Okay, so now what you can do is you just take these two, move it over. At least I'm like, how would you sort this out? Well, yeah, let's do that first, right? So you have e to the 2x plus e to the negative 2x all over 4, and then minus 1/2. Right, okay. So notice how we can rewrite both of these with the denominator of 2, right? And for this one, it's just by splitting the denominator. So it would look like this. E to the 2x plus e to the negative 2x over 2, all over 2, right? So I'm going to put parentheses there so it's more clear. And here we're able to just put a negative 1 because they now have a common denominator. And notice how you've seen this before, right here, in cosh, right? This is the same thing as cosh, except here our argument is 2x. So this is actually equal to cosh of 2x minus 1 over 2. Now, in this way, it is very similar to sine squared, right? Okay, well, I'll write it down over here on this newly derived identity. Right, so we have that, but we also know that this looks very similar to sine, right? And actually, that's a cool connection we were able to make. Even though it's not really helpful in this case, see that sine squared x is equal to 1 minus cosine of 2x all over 2, right? And this and that look really, really similar. So it just goes to show that this function right here and sine are more related than you might think. So we can use the exact same idea, right? The exact same strategy to integrate sinh squared as we can do to integrate sine squared. Just replace it with this, right? Now notice the over 2, we can bring that outside. And then inside is just cosh of 2x minus 1 dx. Okay. Now we're able to integrate since we know that the integral of cosh is sinh, right? Okay, so the 1/2 stays outside. All right, integrating cosh, we get a sinh. Don't forget that in the argument we have a 2, so we want to divide by 2, right? And then the second term is a lot easier. We would just, integrating 1 in the x will just gives us x, right? Okay, now just distribute this 1/2 in, and you get your final answer, which is 1/4 sinh of 2x minus 1/2 x, right? So yeah, we added one more to our list of things we know about this function right here. Add C, and we're done with number 42. Okay, yeah, number 43 is, we're gonna just raise the power by 1, and also raise the question number by 1. So now think about how you deal with sinh cubed, How would you deal with sine cubed, typically? Well, if you were dealing with sine cubed, then the way most people would do it would be to break off a cosine, right? So you have a sine x here, and then you take a sine squared out, and then you rewrite the sine squared as 1 minus cosine squared. Because here, sine x dx, that's your differential if you were to be cosine. If your new variable were to be cosine. So that's how you do this. Why don't we employ a very similar method for this? Since we have a very similar identity, right? So in the normal case, we can do this because sine squared plus cosine squared is equal to 1. What about here? What can we do here? Because there is a property, and in fact, why don't we just derive it? Or we can prove it at least. And I'll tell you that right here, since these hyperbolic functions come from a hyperbola, right? And the equation for this hyperbola is x squared minus y squared is equal to 1. And similar to normal trig, the x is represented by your cosh and the y is represented by your sinh. And this implies that cosh squared, I'm going to write this inside of the list of identities or formulas we have. So this implies that cosh squared minus sinh squared should give us 1, right? Since x squared minus y squared equals 1, x squared minus y squared equals 1. Got it? Okay, so how do we use this? Now, here we pull out a sine squared and then turned it into 1 minus cosine squared. So here, I guess what we can do is pull out a sinh squared, right? So we have a normal sinh here, and then we pulled out a sinh squared here, right? Now we got to find what this thing is equal to, and if we just add sinh on both sides and then subtract 1, you get cosh squared minus 1 is equal to sinh squared. So you can replace this with cosh squared minus 1. Also, if you'd like to, you can prove this by using these two right here and squaring each of them respectively and then doing the arithmetic required. But I'm not going to do that since this is pretty standardized. And also that's like almost trivial at this point. Anyways, here, we can remember here what we did was we could let our new variable equal to cosine, right? So, and then sine x dx could be part of our differential. Here, very similar story. We can just let our new variable be the cosh. So we would let u equal to cosh x. Differentiating both sides, du is equal to, and then the derivative of cosh we see here is just sinh. Remember, it's like a back and forth loop. Keep differentiating it, you go backwards and forwards from cosh to sinh to cosh. All right, and then x, and then by chain rule, you have to multiply by the differential of x. Okay, so we have the sinh x dx here. So we're going to just write that as du at the very end. So now we only need to focus on this part. Cosh squared minus 1, well, cosh is u, so it's really just u squared minus 1. And then the sinh x dx that we ignored later is really just our du. Right, so yeah, same idea. Now all we need to do is integrate this. And integrating that, we got 1/3. I'm going to write this in red. Sorry. I'm going to write this 1/3 u cubed, and u is our cosh. Right. And the integral of 1 is just u, and then u is cosh. So just minus cosh x, and then add c, because now we are done. All right, take a look at how similar these are. Okay, so that's number 43. Now, we're not done with our hyperbolic trig yet, but hopefully you develop a kind of intuition on how hyperbolic trig works. Keep in mind that there's not just cosine and sine, there's also hyperbolic tangent, secant, cosecant, and cotangent. And they work very similar. Like, the ratios are actually the exact same, right? Like, hyperbolic tangent is still sinh over cosh. So, keep that in mind so that you might be able to use that in the future, and we will. So, that's number 43. Let's move on. We're going to keep dealing with some hyperbolic trig because, I find it pretty fun. But next up, it might not seem like it at first. So, we have 1 over square root of x squared plus 1 dx. Now, this one, it might not seem like you could employ much hyperbolic trig, and you'd be right if you used what people would typically do. So let's do the normal way first, because that would give us something important that we would actually be able to work with. But no spoilers, just do this. So notice we have a quadratic inside of a square root. We have to do a trig sub. This is sum of squares, so we would let x equal to tangent. Okay, and then now we need to find the differential, take the derivative on both sides. Derivative tangent is secant, and then chain rule d theta. Okay, so now what you have on top is, 1 times dx is just secant squared times d theta. So on the top, I'm going to write a secant squared, right? Okay, on the bottom, if we just plug in tangent here, tangent squared plus 1 is secant squared, and then the root and the square cancel to leave you with just 1 secant on the bottom. And of course, you have your d theta here. Now, very simple. See that here, this and that cancel, so you're just left with the integral of normal secant theta d theta. And this is a standard result. You get natural log of absolute value of secant theta plus tangent theta. Okay, so we know what tangent theta is. That's just x. What about secant theta? Well, for this, there's no other way around it. We just kind of got to draw out a right triangle, right? Call this our theta, call this our angle. We know what tangent is. Tangent is opposite over adjacent. And here, x represents the ratio. So that's x over 1. X is opposite, right? And then 1 is adjacent. Now to find this side, very simple. It's just the square root of the sum of the squares of each of these legs. And you just get that. So our secant, keep in mind, is just a reciprocal of sine. Cosine. Cosine is adjacent over hypotenuse, meaning secant is hypotenuse over adjacent. So this is a natural log of. So here I'm actually going to write the tangent first, since I think it looks better that way. Tangent here, of course, is just x, right? And then we add. And then secant, earlier we established just this over that, so we just get a simple expression. That's the square root of x squared plus 1. Okay, so that is our first answer. Looks pretty good. And in fact, if you want to calculate the range of this, you actually don't need your absolute value bars, since, you can try to do this calculation by yourself, but keep in mind that there's a plus 1 here and you're adding these, right? And this is always going to be positive, but a little bit greater than just normal x, since you have this plus 1 inside of the root. That's why it's always positive, but yeah. Go ahead and try to prove that for yourself, but for now, we're going to do this in a different method. Here we can use trig sub, but another way we can do it is use hyperbolic trig sub, because here what you notice is that what we did here, what we employed was a sum of squares, right? This is because tangent squared plus 1 squared, right, is equal to secant squared. Right, so there's a sum of squares, and that gives you another square. Now, take a look at over here. We can do something very similar by just adding sinh on both sides. We could also, note here that if you just add sinh on both sides, you get that cosh squared, and then plus 1, well, no, sorry, not plus. Cosh squared equals, you have the 1 there, or no, I'm going to write the sinh first. And then plus the 1, right? So you get another form that a sum of squares gives you another square. So you don't need to use tangent here. Let's just use sinh, because sinh squared plus 1 gives you cosh squared, and that will also be able to cancel with the root pretty nicely. So, yeah, let's do that. Let's do another substitution. We would let x equal to, and we already use theta, so let's use phi here, because phi also represents an angle in most applied cases. So let x equal to sinh phi, right? Since if you plug in a sinh there, as I said earlier, you'll be able to get that. Okay, and then now all you need to do is find the differential, and in fact here, I'd argue it's easier, because all you get is a cosh phi. Yeah? Okay, now just plug it all in. Still have the integral of, and on top you get and this is chain rule, right? On the top, you have 1 times dx, which is really just cosh phi times d phi. So I'm going to put down a cosh phi on top and then a d phi on the side, or phi, right? In the bottom, plug in a sinh. We see that you get a sinh squared phi plus 1. And then that's exactly what you have here. You can replace it with cosh squared phi. Square root of cosh squared phi is just cosh. So the bottom is also just a cosh. Okay, and now notice that the top and the bottom completely cancel out, and you're just left with your differential, right? And of course, integrating d phi just gives you phi. No? Okay, and then finally, we just want to rewrite this in terms of x, right? And here we see that if we just take the inverse sinh on both sides, you get inverse sinh of x is equal to phi. So we can write this as inverse sinh of x. Right. As see, and you're done. So that's 2 ways of doing this. Why do they look different? And what the hell is this even like? Well, to explain this, I mean, it's not really difficult, right? Now you know that this is equal to that, because, well, they just are, right? They're not even off by a constant. If you graph both of these functions out, they're the exact same function, right? So therefore, we just found ourselves another identity, is that inverse sinh is equal to that thing right there. So why don't we just write it now? We get that the natural log of x plus root of x squared plus 1 is equal to inverse sinh, right? Yeah, this and that are the exact same thing, not even shifted off by constant. They just are equal. All right, that's number 44. And number 45, let's apply some of the stuff that we figured out. All right, number 45, have the integral of the natural log of x plus square root of x squared plus 1 dx. Now, you're integrating a natural log. Your first instinct might be to just use integration by parts, right? And you absolutely could. But look at the inside. It looks not the most fun to mess around with. So I'd advise you to notice that this was our previous result. And remember what we said about our previous result is equal to inverse sinh. So just replace the integrand with inverse sinh. You're integrating inverse sinh of x, and then with respect to x. So now you could do integration by parts, and it's not so difficult, right? Also earlier, I forgot to write this down, but we established that, well, the derivative of inverse sinh is just the integrand of our previous question, which is, if you refer back, you get 1 over the square root of x squared plus 1, right? Yeah, so this will help us with our DI method, because we're going to be using that for integration by parts. All right, we would differentiate inverse sinh, right? And then we are going to get that. 1 over x squared plus 1. And then we're integrating just 1, since this times that gives you that, right? And this just gives you x. Multiply the diagonals, integrate the rows. Okay, so you get x times inverse sinh of x, and then you want to subtract off the integral with this times that inside of it. So you have x over the square root of x squared plus 1 dx. This is a very simple u substitution case. I'm pretty sure you can tell why at this point. So we would just let x squared plus 1 equal to u, and then differentiating both sides, you get 2x, and then chain rule dx is equal to du. No? Right. So here we have our x dx, right? But we don't have a 2. So isolate the x dx by dividing 2 on both sides. You get x dx is equal to 1/2 du. All right, really simple. This first term is already outside of our integral sign, so we don't need to mess with it. The second term, however, notice how our 1/2 du is equal to x dx, right? And it's multiplicative across the entire integral, so let's bring the 1/2 outside. Okay, in the denominator, you just have a simple root. And inside, the entire inside, you already set to be u. And you know what, in fact, we're not going to do that. We're gonna keep the 1/2 inside, right? But because you're dividing by it, it's in the denominator, right? And then you still have the root, and then inside the root, you had the u, as I was saying. You have the 1/2 taken care of, so now the x dx, all that's left is the du. So I'm going to write this as a 1 times du right here. And this form is, of course, standard, right? Very nice. It's just the square root of u. So you get x times inverse sinh of x minus square root of u, right? And then u is just x squared plus 1. Add c and you are done. This is really nice. And of course, you could have just worked with that. You would have gotten the exact same answer either way. Just replace the inverse sinh with that. But I mean, I feel like it's a lot better to work with stuff that we already got introduced to, not for no reason to, right? Okay. That's number 45. Alright. We still have more hyperbolic trig. Do I want to erase this? Sure. I don't think we need much of this later on. Just from now on, the two most important things to keep in mind is that first of all, the derivative of sinh is cosh, and the derivative of a cosh is sinh. And if we need to, we can also use the exponential forms of our hyperbolic trig functions. However, I don't think that'll be necessary. So yeah, okay, number 46, integral of hyperbolic tangent x dx. Keep in mind, as I told you earlier, similar to how tangent is sine over cosine, this tang is, I'm going to call it tang. I'm not sure how you would pronounce it, but it's just sinh over cosh, right? So let's rewrite it as such. And in fact, integrating this guy is also basically the same thing as integrating our normal tangent function, because you get sine over cosine there, and you can do a u substitution there, and same thing here. So let's do a u substitution. Let u equal to the denominator, because the numerator, sinh x dx, is just your differential. So u equals cosh. That means du must equal sinh dx, right? Alright, so really, sinh dx, that's our du. And then cosh is our u. So this should give you natural log of, sorry, this should be in red, of the absolute value of u, right? And then, of course, u is cosh. So this gives us the natural log of the absolute value of cosh. And one more thing. If you think about it, right, well, I'll just show you the graph, but you're able to derive this from your exponential equivalent as well. But this right here, cosh x, is always positive. It's a catenary curve, to be exact, and its minimum is at y is equal to 1, right? So this is 0, 1, right there. That's cosh, right? And it's always positive. So in fact, you can just get rid of the absolute value signs. All right, and then that's it for this one. Add C and you're done. So hyperbolic tangent is still relatively easy. Just for these, don't confuse yourself too much as I did the first time I worked with these. Just like treat them as look at them, compare what you would do with the normal functions with these, right? Because it actually is very similar. Not for the next one, however. Let's take a look at this next integral right here. The integral is number 47, and it's the integral of hyperbolic secant. Now this is 1 over cosine, right? But however, that's not what you would do typically. Typically, what you would do is you would multiply in secant x plus tangent x on the top and the bottom. So it would cancel out. However, I'm pretty sure that is not the case with this one. Because of some weird properties with the derivative of hyperbolic tangent. Right? And to be exact, right, the derivative of secant, everyone knows, is just secant tangent, right? And then the derivative of tangent is just secant squared, right? However, the derivative of hyperbolic secant is almost what we need to be able to use the same method. However, it is negative. Negative hyperbolic secant x, hyperbolic tangent x, right? And then the derivative of tangent, however, if this would be negative, that would still enable us to use the same method. However, this one's positive. So give it a shot for yourself. But notice how like the change in sign, it makes it so that doing that is basically impossible, right? So we can't do that. Instead, here's what we're gonna do. So very similar to integrating normal secant, we're going to be using a step that seems kind of convoluted. However, we're going to be first putting it in terms of cosh and sinh, because those are the most basic forms we get to work with, right? Okay, so for this one, well, what do you do here, right? Like if you had normal cosine, you would typically just turn it into a secant integrator from there, but we can't do that because we don't know what the integral of hyperbolic secant is. So I'm going to do something that might seem out of the blue, but you'll see that it actually helps a lot. I'm going to make it so that we have a cosh squared on the bottom, so we're able to use some trig identities, right? And to do that, you need to multiply cosh squared on top too, so it maintains equality. Right, okay, now let's do some experimenting and turn the bottom into the equivalent of this, 1 plus sinh squared. Sorry, and then the top isn't 1, the top is cosh still. And would you look at that? We now have a u substitution set up for us because cosh x dx is the differential of our sinh x. Very nice. So we would let u equal to hyperbolic sine x, and then differentiate both sides. You get 1 times chain rule du, and then cosh x multiplied by the derivative of x, right? All right, and yeah, let's just go ahead and replace everything. On the bottom, you still have a 1 plus sinh squared, but sinh is u, so you have u squared instead of sinh squared. Cosh x dx is just du times, it's just du, right? So you just 1 times du Now this is a standard form. It is just inverse tangent of u. And of course, I'm not going to waste your time. U is just sinh, so yep. And this is actually what we get. Nothing with natural logs, unlike what you might have anticipated, but this still works. Right. Okay, well, one interesting thing is that another way you can do the integral of secant x, it will form very, 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 very similar to this, right? However, if you were to do it this way, like break it into 1 over cosine and then multiply cosine on the top and the bottom, instead of inverse tangent, you would get inverse hyperbolic tangent. Instead of sinh, you get sine. So there's another connection there, and I think that's pretty interesting. However, this doesn't have an equivalent that you can write in terms of natural log, at least not as far as I know. You might be able to, but yeah. And one more thing of note, if you went back to this step right here, right? See this? What if you were to replace cosh with its equivalent in terms of exponential functions, right? You would get that this is equal to, well, cosh is just e to the x plus e to the negative x over 2, right? So there's a complex fraction. There's the exponential thing and then the over 2. So I'm going to multiply 2 on both the top and the bottom first, right? Multiplying a 2 on top, let's just bring that outside, right? On the bottom, we're just left with the exponential part since that's the whole point, right? And for this one, I'm gonna ask you to look back to integral number, I think it's integral number 35. Yeah, we said that this thing is actually equal to, and we still have the 2 here, but we figured out that this is equal to 2 times the inverse tangent of e to the x. So I'm like 75% certain that this and that are equivalent functions. However, that's just shifted by a constant. Unless it's not, then that's pretty cool. But yeah, that's just something to note. Right. Yeah, right. I'm not completely sure. Might graph these, but for now it's just an observation. That's number 47. I need to flip back now. Okay, are we almost done with these guys? Not even close. Okay, number 48, we have more hyperbolic trig. And what you have is in fact another inverse function. So more integration by parts, but for the fun of it. Number 48, integral of inverse hyperbolic tangent x. Jesus Christ, that looks, well, not the worst, because what we can do is just simply use the DI method, right? Now, this is, how should I do this? How would you typically differentiate that, right? Because we don't know the derivative of it yet. Because we haven't done anything to solve for it. I'm treating this as if it's like an introduction. So I think the way you would typically do it is you would let y equal to this and then solve it using implicit differentiation. So let's first find the derivative. So we let y equal to inverse hyperbolic tangent. And then we would take the normal guy on both sides. Right. Okay, and then from here we differentiate both sides. We'd get this here, right? And then, of course, we're differentiating with respect to x, not just any implicit differentiation. And then differentiating x with respect to x, you just get 1. Yeah? Okay. And then from here, what you would do is you could, let's rewrite this as its equivalent. Sorry, no. Wait. So from here, there's another step that we need to take that we need more information about these hyperbolic trig functions on. And recall that we had an identity that, secant squared, right, minus tangent squared is equal to 1. And that means in the hyperbolic world, since they're so very similar to each other, it should be something very related. Now, yeah, so let's look for, what happens if you, let's say add these two, right? So, right, for hyperbolic secant, I'm going to break it into 1 over cosh squared, right? And then I'm going to add on hyperbolic tangent, right, just to show you that this actually works. And, of course, hyperbolic tangent is sinh squared over cosh squared. Combine the two fractions, we see on the top we have a 1 plus sinh squared, and that is equal to cosh squared, so you get cosh squared over cosh squared, which is just 1. So you see that here, what we're really trying to say is that hyperbolic secant squared plus hyperbolic tangent squared is equal to 1. So from here, what you can do is you're able to isolate the hyperbolic secant of y, and then you just have 1 minus hyperbolic tangent squared. Right? So from here, we turn this into 1 minus hyperbolic tangent squared of y dy dx. This is still equal to 1. Okay, and then notice that y is just the inverse, right? So plugging an inverse into its primitive or original function, right? Hyperbolic tangent of inverse hyperbolic tangent just gives you whatever the argument of the inverse hyperbolic tangent was, which is an x. And since this is squared, the x is going to be squared on the outside. So therefore, 1 minus this becomes an x, and this squares here, so we have to square that, is equal to times dy dx is equal to 1. Finally, to isolate the derivative of y with respect to x, since that's what we were trying to find either way, we just divide this on both sides. So this gives you dy over dx is equal to 1 over 1 minus x squared. So yeah, we're going to be using this because, as I said earlier, going back to our original integral now, we're going to be using integration by parts. Right. Differentiate this, since it's easier to differentiate. Well, actually, no. If we were to put this into the integration column, that just defeats the whole point. So integrating, we would just do this, because this times that is equal to this. All right. Differentiating this, we just got that if y was equal to that, then dy over dx is equal to 1 over 1 minus x squared. Therefore, the derivative of inverse hyperbolic tangent x with respect to x is just 1 over 1 minus x squared. Jesus Christ. Okay, integrating 1, you get x. Multiply diagonals and integrate the rows. And of course, another way to do this, as I mentioned with all of these inverse guys, was just to make a u substitution at first and then do what would arguably be a little bit more, easier integration by parts. But for now, I want to show you that the derivative of this is that. So that's why this is important. Okay, regardless, let's write down the diagonals being multiplied. All right. And then we subtract off the integral of this times that. So we get x over 1 minus x squared. And lucky for us, this is relatively easy since notice that you just need a u substitution, right? Let u equal to that. So you would let u equal to 1 minus x squared. Taking the derivative of both sides, you get that. You get this, basically, right? You have our x dx here, no negative 2, so you're going to divide negative 2 on both sides. All right, and then now we can just implement the substitution. Of course, the negative 1/2 du is multiplicative across the entire thing. So I'm going to bring it to the outside. And of course, you have a minus negative 1/2. So this becomes a plus negative 1/2 times the integral of x dx is just, we already took care of the negative 1/2. So there's going to be a du at the end. And of course, we have the integral of the bottom is just our u. So this is just du over u. That gives us natural log of u. So x inverse hyperbolic tangent of x plus 1/2 times the natural log of the absolute value of u, which is just 1 minus x squared. Okay, so yeah, that is the derivative of this guy. Pretty fun. Sorry, not the derivative, the integral. That is the antiderivative of this guy, of course. Okay, that's it for number 48. Okay. And we have just one more. One with hyperbolic trig, and I'm not going to lie, it looks kind of intimidating. So bear with me. Number 49 is the integral of the square root. Yeah, whenever you see a square root there, it's always a sign of bad things to come, especially if there's nothing outside of the square root being multiplied in. In here, you just have hyperbolic tangent x. How the hell do you do this? Well, for this, I would just recommend doing u substitution for the entire thing. Since, yeah. Let's just do a u substitution. Square root of hyperbolic tangent x. This implies that taking the derivative... No, actually, no. You know what? It's actually much easier if you were to isolate the hyperbolic tangent x first. So, not even that. Let's just isolate x completely, right? So, you would square both sides. You get u squared equals hyperbolic tangent x. And then you take the inverse on both sides. You get inverse hyperbolic tangent x. Sorry, not x, just u squared. And this is equal to x. So now the x is isolated, take the derivative on both sides. Dx is equal to the derivative of this, right? So, of course, the derivative of inverse hyperbolic tangent is just 1 over 1 minus the argument squared, right? And u squared is the argument. Square that, you get u to the 4th. And then also remember to take, reverse chain rule. No, normal chain rule, because you're taking the derivative here. So you would take the derivative of u squared and put it on top. Finally, the very inner function is u, so you put down the derivative of u. Yeah, that's what you get. Alright, so we set the integrand to be u. Right, and then we have the differential, which is 2u over 1 minus u to the 4th du. Okay, so, there's so many ways to do this, actually. But, you know what I'm going to do? I'm going to just combine the u's to make it u squared. Yeah, I'm going to do that right here. Notice the bottom is factorable. This is the difference of squares. And I'm not going to fully factor it, as you'll see in a second. So, factoring the bottom, you get 1 plus u squared times 1 minus u squared. And then on the top, you would get just your old numerator, because we're not doing anything about that. We just factor the bottom. Okay. Here, believe it or not, you're actually in a position to do partial fraction decomposition, because you can just use, instead of u squared, right, you can just treat your variable as a v, because that's the case with all of these, right? So let's do the partial fractions up here. So you get 2u squared over the factored bottom, 1 plus u squared times 1 minus u squared. And you want this to be equal to, well, a over 1 plus u squared plus b over 1 minus u squared. Now, the reason why you can just have a linear term on top, even though they're both quadratic, is because all of the variables are u squared. So theoretically, if you just let this be v, then you would get 2v over 1 plus v times 1 minus v, right? So there's no problem with having the top be constant, because if you just made that substitution, now the bottom would be linear. And you might think this messes with the integration. Well, no, it doesn't, because after you finish it, you can just replace v with your old u squared. Since we're not working with differentials when we're doing partial fractions, this is pure algebra. So you're able to make the substitution, right? But either way, I'm not going to do that. For here, I'm just going to work with what we have, all right? And here, what you can really do is just the cover-up method. So for a, you'd want to cover up this factor, which is right here. And for this for this denominator to be equal to 0, u squared would need to be equal to -1. And I'm not going to solve for u, because remember, we're working in terms of u squared, not u. So a would be equal to 2 times, and then remember, u squared is -1, right? And then we're covering this up, so we just have this one left. We have 1 minus, and then u squared is -1. The top becomes -2. The bottom becomes 1 plus 1, which is 2. You just get -1. All right, how about with b? Here, u squared would need to equal to 1, right? For this denominator to be equal to 0. So we cover this up, right? And then we just plug in u squared equals 1 for the rest of these. So you get 2 times 1 over 1 plus 1, which is just the top gives you 2, bottom gives you 2. That means b is equal to 1. So yeah, let's just write it down here then. Yeah, let's go over here, since this is actually a very quick case of partial fractions. So our a is -1, and then we have it over 1 plus u squared. And then our b is +1, and we have it over 1 minus u squared. Okay. These are both standard, since we worked out that this earlier would, the integral of this is just inverse hyperbolic tangent. So let's just do all the integration now. This first term here, notice that it is just tangent. So the negative sign is linear, so stay outside, but then the function part, you get just inverse tangent, of u. Secondly, notice that out here, this gives you just a normal hyperbolic tangent. There's no negative sign or anything. So I'm going to actually swap the order of these, because it looks nicer for this to be subtracted from that. And of course, with the very last step, in addition to swapping the order, because it looks better, remember what we said it equal to square root of hyperbolic tangent. So let's put that back in, right? And then we would subtract off the inverse tangent of u. And of course, u is just square root of hyperbolic tangent x. Add c. That's it for this one. The result looks quite pretty. Yeah, that's nice. And with that concludes the hyperbolic trig segment of our 100 integrals. Okay, so now let's move on to something that I think is a lot more fun than this. Yeah. Whatever. How fun it is, that's completely subjective, so it might not be fun for you, or it might be more fun for you to do hyperbolic trig, since, it's a new concept for a lot of people. I know some people in calc don't even learn hyperbolic trig. I'm not sure if it's part of the curriculum or not, since I haven't actually taken calc formally yet. Okay, we have the integral from, and this is number 50, by the way, we're halfway through 0 to 5 of a floor function of x, right, dx. You could try to find the antiderivative of this, the floor function. But, it's not nice to do so, right? So I would just I would just do this completely graphically, since it actually looks really nice graphically. Now, in case you're wondering what the floor function even is in the first place, well, basically, if you have like just any number, right, then what you're doing is you're just taking the integer part of it. You're just taking this part. So therefore, the floor of this guy would just be equal to 32, since 32 is your integer part, the integral part of the number. Right. So with that in mind, if we just segment this off into 5, right, 1, 2, 3, 4, 5, and then do the same thing with the y-axis, 1, 2, 3, 4, 5, right? Then, well, we can graph this out, because, it's nice. So, from 0 to 1, the floor of 0, the integer part of 0, is just 0, right? And then, actually, all the way through up until 1, since, picture it, right? All the way up until 1, the integer part is 0. It's always 0 point something, 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 until you hit 1. Then it flips over to 1. So, actually, from here to here, this is what the graph would look like. It's an open circle at 1. Okay, it looks kind of messy, but you get the idea. All right, now for 1, starting at 1, the floor of 1 is this 1. And picture all the numbers that you want to up until 2, right? They all have an integer part 1. It's always 1 point something, something, something. Until 2, and that's why we have an open circle at 2. Because 1.99999 is, this floor of that is still equal to 1. However, once you reach 2, once you flip over to 2, it's going to hop up to 2. And then the cycle repeats, right? And what you notice is that you can actually break this into little squares that are all 1 unit large, right? Since each of these is a 1 by 1, yeah, this is 2 to 3, right? That's 1. This is 3 to 4, that's also 1 unit wide. So, and because these are all squares with area 1, just tally it up, right? You have 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, 7 square, 8 square, 9 square, 10 square. So the area under this function right here, from this point right here, 0, all the way up to 5, is just 10. It's a very nice geometric intuition. So let's just put down 10 and box our final answer, right? Not much work involved with doing this. Okay, that's number 50. Okay, let's do some more. Number 51. Well, first I'm going to check if my phone is still recording or not. Alright, yeah. Okay, number 51. We have integral of secant to the 6th power x. dx. Okay, it looks kind of intimidating, but it really isn't, right? Because what you have is a very simple case of just splitting the secant up, right? So if you just leave the secant squared here, and then split the secant to the 4th out, then you can turn the secant to the 4th, you can rewrite it all in terms of tangent. So secant to the 4th is just secant squared squared, right? And of course, you know that secant squared in here is just tangent squared plus 1. So I'm going to write that in. Square this, dx. Okay, now it's just u substitution, because the derivative of tangent is secant squared dx. So let u equal to just tangent, right? And then find the derivative of both sides. You get du is equal to secant squared x dx. I'm going to open up a whipper real quick. Okay, and then now what you see is that, first of all, the secant squared you see up front times the dx, we can just put that to the very back and call it du. Here we get that tangent squared plus 1 all squared, right? But then tangent is u. So you get u squared plus 1 all squared. And of course, the secant squared dx is just du. Nice. Don't overthink it. Just expand this out. It's a simple polynomial case. Expanding this out, you get u to the fourth plus 2u squared plus 1. I'm not going to go through all the details for this one. As we go on, I'm going to just start skipping more and more work because I've introduced all of this stuff earlier. Maybe you can treat it as a reviewer for people who maybe haven't seen this before, haven't done calculus in a while, but, you know, I'm going to assume that a lot of this stuff is also prior knowledge. Okay, integral, we can just integrate all of these because these are polynomials. Integral of u to the fourth, you just 1/5 u to the fifth. However, u is tangent, so I'm going to replace all of these with tangent. Okay, and then add 2, right? The 2 is still there. However, integral of u squared is 1/3 u cubed, right? So there's now a over 3 component, and then u is tangent, and don't forget that it is cubed. Lastly, you just have an integral of 1 in the u world, which just gives you u, which is tangent. Okay. Very nice. That's just number 51. You are done. Yeah. Pretty fun. Okay, so number 52. Number 52, we have kind of a rational expression. You'll see it's 5x minus 2 or plus 2 all to the fourth power. Might be plus 2. No, it's minus 2. Okay, and then with respect to x. Now, it's the bottom's factored for you, so there's really no point in expanding it out, right? No one wants to deal with a full-blown freaking rational expression to integrate. So here, what I'd recommend you do is just make a u substitution. Because notice the inside is linear, and that means the differential is just going to be a constant times the d new variable, I guess. That's how you would describe it. So yeah, we would just let u equal to the whole inside. Right, and then take the derivative of both sides, you get du is equal to 5 dx. We only have a dx up here, so let's just isolate it. 1/5 du is equal to dx. Nice, okay. And of course, the 1/5 is multiplicative across everything, so I'm going to take it outside, just like we did before. On the bottom, we just have a u, right? The entire thing is u. And then you raise it to the fourth power, and of course, 1/5 du is equal to just what you had before, which is only dx. And it looks kind of like a v. Okay, there we go. So now, this is just a case of using reverse power rule, right? I'm going to quickly rewrite it in a way where we're able to better interpret this. There we go. So now using reverse power rule, add 1 to it, so you get -3, and then divide by -3, right? So, and of course, 1 over 5 times 1 over -3 just gives you -1 over 15, right? And then you get u to the -3, right? And of course, u is just that, so I'm just going to write 5x minus 2 to the -3. Almost done. But, you know, it's a lot simpler to just rewrite this in the denominator. It gets rid of that ugly negative exponent. So you get a negative, and then, of course, the 15 is already in the denominator. Now you get your 5x minus 2. Now it's just to the positive 3 power, because it is now in the denominator. And then at the top you just have a 1. And add c and you're done, because that is basically fully simplified. Although you can expand it out and then distribute in the 15, that's going to look really ugly. So I personally would not do that. Like 4 terms in the denominator, all with high coefficients. But yeah, that's number 52. Okay. Number 53. we have the natural log of 1 plus x squared. And at this point, I expect that you know what we do with natural logs. We do integration by parts. So you differentiate one column, and of course that would just be the natural log function. And then integrate the other one, 1. So this is now, in the denominator, you have the argument of the natural log, which is 1 plus x squared. Don't forget chain rule, so you have to take the derivative of the inside and multiply it in. That's just 2x. Integrating 1, you get x. Easy. So first I'm going to multiply the diagonals and then integrate the rows. So multiplying the diagonals, you get x times natural log of 1 plus x squared. Right. And then secondly, you have to subtract off. And because the 2 is multiplicative across the entire integral, I'm going to take it outside. Inside you just have a 1 plus x squared, and then an x squared, right? Because you have an x times an x, that gives you x squared. Okay, for this, you can do long division if you'd like to, but I think we've done this already sometime earlier in this video. So we know the strategy already is just add 1 and subtract 1, right? Because that makes this a big 1, and then you just have a negative 1 over that. So let's do with this. So here what it does is this becomes a 1, and then you have the minus, and then 1 over the same denominator, because all you did was split the fraction. And of course, this is a standard form. We've done this infinitely many times in the past, even in just this video alone at this point, so you know that you just get inverse tangent. However, first, you know what, yeah, distribute the 2 in, integral of 1, you get an x, so distributing the 2 in, you get 2x, right? And then next, the double negative makes a positive. Still want to distribute the 2 in, right? And then take the integral of that, which is just inverse tangent of x. There you go. It looked kind of horrible at first, but, you know, it's not all that bad at the very end. It's pretty satisfying, I'd say so. Yeah, add C. And that's it. That's it. Okay. Alright, that's it for number 53. Number 54. Actually, before I do, I'm going to grab a drink. Oh my God. Okay. Keep going. Keep going. All right, now number 54. There's 2 ways of doing this integral. First of all, let me write it down first. So we have x to the 4th plus x dx. Now, you might not know the shortcut, so let's just do it the way any normal person would, right? And this is going to take us forever. However, let's just give it a shot and find where they come together at the very end. First of all, know that there's a common factor of x in the bottom, so factor out the x. And here you are left with an x cubed plus 1. I'm just going to give it to you straight, right? There's a sum of cubes here. You're able to factor it more. Factoring a sum of cubes, you would get x plus 1 times x squared minus x plus 1. 1 dx. This is no longer factorable. You know what that means. It's time for partial fraction decomposition. The nightmare of every single calculus student, including mine. But you know what? Let's just do it. So, we want this to be equal to, well, let's put that down first. Alright, so you want this to be equal to 3 fractions, each with one factor as their denominator. Okay, yeah. And okay, well, there's no 1 on top. We don't know that yet. Okay. And of course, this one's a linear, so on the top is going to be 1 degree less, meaning it's constant. Same with this guy. This one's quadratic on the bottom, and it's irreducible, so the top needs to be linear. Okay. And I don't want to do this. Alright, so this one, let's just do cover up for these first 2 linear terms, because we're able to do that, and also because I don't want to solve a system of 4 variables. So, for this first denominator to be 0, we just set it equal to 0, right? X is equal to 0. So, we cover this up and set all of these other x's equal to 0. So, a would be equal to, of course, we have this covered up, right? So, now you just set all the other ones equal to 0. 0 plus 1 times 0 squared minus 0 plus 1. This is just 1 times 1. So, this just gives you 1 over 1, which is 1. Simple. And then for b, a little bit more difficult. Set x to be equal to negative 1, right? Since that's what makes this denominator 0. Cover up this middle guy right here. So you have this one right here, a negative 1, multiplied by, and plug negative 1 into that. Alright, and in here, negative 1 squared is 1. Negative 1 is 1. And then you have another plus 1. And that gives you 1 plus 1 plus 1, which is 3. So you have 1 over 3, and don't forget this negative 1 out here, so that makes it negative 1 over 3. Alright. And now we gotta solve for those 2. Ooh, okay. Right, so now's the time when we can replace these 2, right, with what we got. And we just multiply everything by the least common denominator, which is this thing. So, multiplying this left-hand side by its own denominator, it just cancels, and it leaves you with whatever's on top, which is just a 1. Okay? Multiplying this 1 over x by this whole thing, the x and the x cancel, so you're just left with an x plus 1. And then x squared minus x plus 1. And I'm not ignoring the 1, it's just that there's no need to put down a coefficient of 1. Next up, let's put on the negative 1 over 3 first. And then notice how the x plus 1 and the x plus 1 cancel. So you have an x times all that shit. Finally, cx plus d. We just gotta put that down as cx plus d. And then the quadratic cancels with the quadratic, you're left with an x times x plus 1. Alright, now let's do some more simplification. I'm going to start doing this in black because, anyways, x plus 1 times x squared minus x plus 1. We saw earlier that we turned x cubed plus 1 into this thing right here. So we can turn it back into x cubed, but plus 1. Yeah? For this one, we had to just multiply everything by negative 1/3 x. So, negative 1/3 x times x squared, you get negative 1/3 x cubed. For this next term, negative, they cancel to make positive. 1/3 x times x is just 1/3 x. But now it's squared. And then this times 1 is just itself, so negative 1/3 x. Alright, next, I'm going to make this simpler for us by rewriting x times x plus 1 as x squared plus x. Cx times x squared is cx cubed. And then cx times x is cx squared. D times x squared is dx squared. And then d times x is just dx. Not dx as in the differential, capital dx. That's important. Okay. Cool thing about this partial fractions is that if we just put the 1 down here, notice that we're able to cancel. There's only one constant term on the right-hand side and one constant term on the left-hand side, right? And that's this one and this one. If you just subtract one from both sides, then this and that completely disappear. And on the left-hand side, you're left with 0. So this whole thing has to equal to 0. And that means, because x can be equal to anything, we now have to zero out their coefficients. So before we do that, let's not get ahead of ourselves, actually. Let's just group all the coefficients first, right? So you have a 1x cubed here. And then a minus 1/3 here. And the only one remaining is this plus c out here. So that's it for the cubic terms. Next, you have the quadratic terms. Quadratic terms, you have normal 1/3. And then plus c plus d. Alright, so from here, I'm going to tell you two things. First of all, we don't need the last equation, right? The linear one. Actually, you know what? I think it'd be more convenient to have the linear one than the quadratic one. So instead of writing the quadratic, I'm going to write the linear. Now, typically what you would do is you would write the quadratic. However, in this case, I feel like it's unnecessary. So, yeah. So the linear one is d. And then you just have a 1/3, negative 1/3. So you just have a d minus 1/3 x. Now I draw this because it doesn't continue forever. We still have our x squared term. However, we don't need it because we only have two variables and we only have a system. We already have our two expressions here that we're going to be setting equal to a number. And that number, here comes my second point, is going to be 0 because the left-hand side is entirely 0. So the coefficients of the polynomial also must equal 0 because that way, no matter what you set x to be, it's going to be equal 0. 0 equals 0. That's how we make it true. So this must be equal to 0. That must be equal to 0. So we have 1 minus 1/3 plus c equals 0. I'm going to write this as c plus 2/3 is equal to 0. And then also d minus 1/3 is equal to 0. For this one, subtract 2/3 on both sides. So you get c equals to negative 2/3. And for the d, just add 1/3 on both sides. You get d is equal to 1/3. Right. Okay. So, yeah, I'm going to write this over here. Right. And I'll also split up the integral. So, this first term is just 1 over x. dx, right? Because I'm splitting up the integral. Next term, we can take the negative 1/3 outside using the linearity. This goes outside, minus 1/3. And then on the inside, you're just left with the integral of 1 over x plus 1 dx. Lastly, this thing, we can write it all as one integral, right? So our c is negative 2 over 3. Our d is positive 1 over 3. And what we can do is we can actually factor out a negative 1/3 out of both of these and take it to the outside of the integral. So you have a negative 1/3 times the integral of c is just negative 2/3. How we moved the negative 1/3 outside, so you're just left with a good old 2. And then, of course, we have our x. And then the d used to be 1/3, but we moved the negative 1/3 out, so you're left with a negative 1. And then the denominator is x squared minus x plus 1 dx. Okay. And now we can just get rid of all of our work because we don't need it anymore. We have the equivalent form. Alright. So, now we're actually able to integrate this. Notice at the top here is the derivative of the bottom. Same with this, and same with this. So it's just a bunch of natural logs, right? Alright. And of course, we can just integrate this. We don't need to do any substitutions here, because the top is just the derivative of the bottom. There's no, constant multiple that needs to be included after you make the substitution. This one, so let's just go from left to right. The left side, you have a natural log of the absolute value of x. Next one, remember the coefficient still stays, but then inside becomes a natural log of x plus 1. And remember that's the value. Finally, you have 1/3, and then you have the natural log of the bottom, right? Since we established that the top is the derivative of the bottom, and we could just do a u substitution. Right. So that is actually just it for our first way. And as I mentioned earlier, there's two ways of doing this. And the second way of doing this, we don't factor it traditionally, and we don't do traditional partial fractions. Instead, what we do is, if you look at this, we can take an x to the 4th power out. So we do this. On the inside, dividing x to the 4th by x to the 4th, you just end up with the 1. And then dividing in x by x to the 4th, you end up with the x to the -3. Right? So it's already kind of convoluted from the beginning. Second step is even more convoluted, and that is to take this and put it in the numerator with the negative exponent. Alright, and here, you might not notice it because the exponents are negative, but you can do a u substitution. If you just let u equal to the bottom, and then find the differential, you'll see that take the -3 to the front, and then subtract 1 from it, and then multiply by the chain rule. Alright, and then up here we have the x to the -4 dx. We also have the x to the -4 dx here. However, we have a -3. Divide everything by -3. Very nice. Almost done. Now we just implement the substitution. Right, and you see that our -1/3 is multiplicative. I'm going to take it outside. And then the top, x to the -4 dx, is just du. And the bottom, earlier we said, was just going to be our u. So, finally, this is just natural log of u. And don't forget the -1/3 that's hanging out outside. And of course, don't forget that u is 1 plus x to the -3. And add c, and you're done. And next, I'm going to show you how these two are equal. So, alright, I'm going to go from here to here, right? Since this is like what you would typically expect, and this is like all of these that someone found a way to crunch down. So I'm going to be expanding this out since that is easier for me, right? So let's start with -1/3 natural log of as the value of 1 over, and in fact what I'm going to do is write this as 1 over x cubed. Notice that to combine the fractions, 1 is just x cubed over x cubed, right? So you can rewrite this as x cubed plus 1 over x cubed, right? Still the same thing. Now we can split the fractions since we noticed that we made the entire denominator a separate thing. So we just have the numerator, and then we subtract off our denominator. And don't forget, we still have to have the coefficient in our second log. And of course, we subtracted it, so now we just have an x cubed in here. And this double negative makes a positive, so I'll just write that down here. I'm just making it more better. All right. So first of all, for this first term, notice at the inside you can still factor it and break it up using more log properties. So x cubed plus 1 is x plus 1 times x squared minus x plus 1, right? And then the second one, you can take the 3 up here outside using the log property. So you just get 3 times 1 over 3, which cancels. So you just get a 1 as a coefficient, and the natural log of x is all you're left with since you took the cube outside. So yeah, that's where you get this term from. And after you just split these up, because this is a log of 2 factors again, you just get these 2 remaining guys, but I'll do it right here. So you get -1/3, natural log of absolute value of x plus 1. And then, all right, and in fact, because this right here is always positive, then you can just do that. So, and then remember to move the coefficient here. And then you put the parentheses because this is always positive. Right. And then finally, you have your last term of natural log of x. So, yeah, that's it. That's these two completely done, right? Okay, so, right, I'm not even gonna box this because you see that this is equal to that and then this is equal to that. So, right, that's number 54. That's two ways of doing this. And in fact, for this one, for any integrals that look like this, where 4 can be any number, this method will always work, and you can give it a shot for yourself and check and see. But I'll just tell you that it'll always work. So yeah, that's number 54. Okay. Yeah. Okay, number 55, we have, let me see. We have the integral of 1 minus tangent on top, 1 plus tangent on the bottom. Okay, so if you see a 1 plus or a 1 minus and then a trig function, my first thought would have been to simply multiply by the conjugate on the bottom, but that actually would get you 1 minus tangent squared, which isn't really all that helpful, and on the top you square it, expand it out, it still isn't really helpful. So just like any other trig problem, let's rewrite this in terms of sine and cosine. It might help us out a lot. So tangent is just sine over cosine, no? And then the bottom, we also have the top is subtraction, and then the bottom is addition, and we have sine over cosine. And since this is a complex fraction, we want to get rid of the complex fraction. And to do that, we just multiply cosine on the top and the bottom, since it cancels with the cosines in the denominators of these complex guys. And 1 times cosine, of course, is just cosine. And then your second term, you're left with the sine. Same thing with the bottom. 1 times cosine, you get a cosine. And the bottom, the second term, you end up with just the sine. And don't overthink it. The top is the derivative of the bottom. It might be kind of hard to notice that at first, especially if you're used to like just simply not being able to look for that kind of stuff, because if we had a negative sign from the cosine, that would not work at all. In fact, no, you could just factor out a 1, but typically it's not as easy if you have a rational expression in terms of cosine and sine. However, here the top is just the derivative of the bottom, right? Differentiating sine, you get cosine. Differentiating cosine, you get negative sine. So let's just make a u substitution. Let u equal to the bottom, right? We have cosine x plus sine x. And then du just gives us whatever's on top, right? As we determined earlier. And then, of course, we can't forget chain rule, so multiply by dx. Okay, so that makes our job very easy, because the top is our du, and then the bottom is our u, and this makes it equal to, well, no more integral. We have a natural log of the absolute value of u, and then u is just right here, sine x plus cosine x. Yep. Okay. And that's actually our final answer. This is as simple as it can get. And yeah, there's other ways to do it from this form without using sine and cosine. Maybe there are. Well, but this is the fastest way you can do it. Okay, that's number 55. Number 56. You have the integral of x times secant x times tangent x. Well, there's a polynomial and a very easy to integrate trig function, right? It looks like it was set up for us, so let's use integration by parts. We want to differentiate the polynomial and integrate the easy to integrate trig function. Differentiating x, we get 1. Differentiating again, we get 0. Integrating secant x, tangent x, we get secant x. And then integrating one more time is another standard result. We get natural log of secant x plus tangent x. And now we just simply do that. Multiply the diagonals, no more integrating rows. Yeah. Okay, so this leaves us with x secant x minus 1 times that, so it's just minus that. Natural log of secant x plus tangent x. Alright, and that's it. There's not much to it. Add c, and you're done. Very cool. Yeah. Okay, that's number 56. Alright, number 57. We have integral of inverse secant. So we have the trig function. It might be kind of frustrating, but let's just do this the good old-fashioned way, where we differentiate it. Now, this might not be immediately... The derivative of inverse secant might not be immediately obvious. So let's work that out too. Okay, so to differentiate inverse secant, let's employ the use of implicit differentiation since there's not much what we can do about it. So we let y equal to inverse secant, right? Taking the secant of both sides, so that now you're dealing with normal trig functions, you get secant y is equal to x. And here you're in a state where you're able to take the derivative. Taking the derivative of the left-hand side with respect to x, of course, where y is a function of x, you get secant y tangent y dy over dx is equal to 1, right? You can also just use normal implicit differentiation. At the end of the day, it really doesn't matter. And I'm pretty sure what you can do here is just plug x straight back into here. Plug y is equal to inverse secant straight back into here. And you get that the secant and the inverse cancel out. You just get an x times tangent y. And then dy dx. Alright, so now we want to find tangent of y, where y is inverse secant, so we want to find tangent of inverse secant. And of course, like we do for a trig sub, the trig function of any inverse trig function gives you an algebraic expression. So let's draw a right triangle to figure this out. So here's our right triangle. Let's call this our angle y, because in the argument of a normal trig function, you would input an angle, and of course the output of an inverse trig function also gives you an angle, and that angle is y. Our ratio is, y is equal to inverse secant, right? And then the input here is just the ratio of secant. X over 1 is the ratio of secant is hypotenuse over adjacent. So x is hypotenuse, and then 1 is adjacent. And of course you want to find what this side is, which is just the square root of that squared minus this squared. So it's just the square root of x squared minus 1. Tangent is just this, the opposite over the hypotenuse. sorry, no, not hypotenuse, the adjacent. So it's just this, basically. So we get that x. And then tangent y, as we said earlier, is just square root of x squared minus 1. And then don't forget the dy dx. And this is equal to 1. Now all we need to do is isolate the derivative of y with respect to x, since the derivative of y with respect to x is just the derivative of inverse secant with respect to x. And to do that, we just divide this on both sides. We get that dy dx is equal to 1 over x times square root of x squared minus 1. Yeah, so that's the derivative of inverse secant. We can just write this right in here. Yeah? So, let's put that down. And then, of course, we're integrating 1. And then we get x. Multiply the diagonals. You get inverse secant x. And then integrate the row. So, subtract off integral of this times that, right? However, the x and the x cancel, so you're just left with 1 over that. So 1 over root of x squared minus 1 dx. Alright, now all we need to do is integrate this. And of course, we can use a trig substitution, where we just let x equal to secant, right? And I think that would actually work out very nicely. So let's give that a shot. Okay, so let x equal to secant theta, right? Differentiating gets you secant tangent, and then your differential. Okay, so we're not going to touch the first term at all, because it's already outside of an integral sign. However, on the inside, plug in a secant theta into there. Secant theta minus 1, secant squared theta minus 1 is just tangent squared. Square root of tangent squared is just tangent in the denominator. On top, you have 1 times dx, which is just this. So I'm going to write secant theta tangent theta d theta. Notice how the tangent and the tangent absolutely cancel each other out, and just left with a very standard integral, that is the integral of secant x. So I'm just going to do it all in one step. Integral of secant theta, not x, theta, with respect to theta is natural log of absolute value of secant theta minus tangent theta. And then now what we want to do is we want to go back to the x world, right? So let's isolate theta here, because we want to plug in a value of theta, but in terms of x, right? So this gives us inverse secant of x is equal to theta. Now, plug in inverse secant straight into here, you get a very nice answer immediately. Also, you don't need to do that. In fact, here you see that secant theta is immediately equal to x. So we can just put down an x. And then we have to subtract off tangent. Now what we can do is plug in an inverse secant x into here. And what you notice is that we already did all of the work earlier, right? We deemed that tangent of inverse secant, since earlier in this case, we were using y as inverse secant. Here, we're using theta, but the idea is the same. We've solved for what tangent of inverse secant is, and it is just this over that, right? It's just the square root of x squared minus 1. So we can just plug that in for here too, since it's the exact same math either way. There you go. And that is the integral of inverse secant x. Yeah, that's number 57. Alright, number 58. Oh, this looks very familiar, doesn't it? Number 58, we have integral of 1 minus cosine over 1 plus cosine. Okay, this time, what should we do? Well, earlier we had a very similar case, but with tangent instead of cosine, right? However, here it's not possible to get any more primitive, so let's use the conjugate. Multiplying a conjugate into 1 plus cosine, you get 1 minus cosine squared, and then, yeah. It's probably easier to work from there. So on top, you get, the top is squared, since the top is really just the conjugate of the bottom. And then you have to multiply it onto the bottom too, and you end up getting 1 squared, of course, and then minus cosine. But now it's squared. Right, and here we can replace it with a sine squared. And the top, why don't we just expand it out, right? So 1 squared is just 1. 2 times that, you get minus 2 cosine. And then, of course, you just have a cosine squared. On the bottom, we just replace it with a sine squared. All right, and then now, well, let's just split up the fraction and then integrate these all. Yeah. So the first one, 1 over sine squared, 1 over sine is cosecant, but remember it's squared, so we also want cosecant squared. Okay, and the other one that's also, well, you know what, let's just go in order here. For this minus 2 cosine x over sine squared, let's bring the minus 2 outside. And then you just have cosine over sine squared, yeah? And then finally for this last term right here, cosine squared over sine squared, cosine over sine is just cotangent, right? And then remember they're both squared, so this is now cotangent squared. Okay, this one is immediately doable, so let's just integrate it right now. Integral of this, we've done this, at least I'm pretty sure we have, but if you just multiply a negative sign in here and then negative sign on the outside, the derivative of cotangent is negative cosecant squared. So we just replace it with a normal cotangent, but don't forget the negative sign on the outside. So we have the first term down. What about the second term? Second term, we require a u substitution. So, in fact, let's write this down later. Let's do our u substitution first. Because the top, cosine x dx, is just the derivative of sine. So, let sine equal to u, and then differentiating both sides, you get cosine x dx is equal to du, right? Okay, so that's this middle term taken care of. We're able to integrate. What about this one? Well, can we make a substitution? No, not really. Well, okay, remember how we integrate tangent squared? We just rewrite it using, well, secant, right? So, same idea here. We can rewrite this as cosecant squared minus 1. So, yeah, let's put this all down here. Earlier, we determined that this is negative cotangent x. This middle term right here, the minus 2 stays outside. In fact, I'm going to bring the negative sign inside. So now this on the outside is a positive. And then we have negative cosine x dx is just our du now. So we have a du over sine, which is u, but squared, right? So that's term number 2. Term number 3, we said we rewrite it using cosecant. So yeah, short, here it is. We just did that. And that is really easy. So let's just keep working. First term stays the same. It's already fully integrated. Notice that the second term, integrating 1 over u squared, is a standard integral. It's just 1 over u, right? So, and then of course 1 over u. U is sine, so it's 1 over sine. But remember, 1 over sine is cosecant. So this is 2 cosecant. And yeah, cosecant x, right? Since we rewrote 1 over u in terms of x. Lastly, we already deemed here that the integral of cosecant squared, as we did here, is just negative cotangent. So let's put down a minus sign and then a cotangent. Finally, integrating a negative 1, we get a minus x. We're not done quite yet, since notice how there's a like term here. So let's put down the 2 cosecant first. And then minus minus gives you a minus 2. And then the cotangent. And then minus x. Add c, and you are done. That's number 58. Okay. Finally, we have number 59. Well, not finally. We still have like a lot more to go. Number 59. We have integral of x squared times the square root of x plus 4, and then dx. How should we do this? Well, one thing I know is that I'd rather just have one variable inside of the root, right? And then I'm fine with whatever else happens outside. So, well, isn't it really necessary? You know what? It's fine. Let's differentiate this polynomial and integrate the root, right? Since both cases are power rule, however, if we differentiate this, then it's going to go to 0. And integrating this is easy since it's still power rule. Okay, so differentiate x squared goes to 2x. That becomes 2, and that becomes 0, right? Integrating, well, let's rewrite this as x plus 4 to the 1/2. Now notice that this x plus 4 isn't just one variable, however, it is linear and the coefficient is 1. Right? So you can really just treat it as a shift in the graph, and there's no change in differential. If you integrate 1 plus 4 to the 1/2 dx, it's the same idea as integrating u to the 1/2 du, where u is equal to x plus 4. So just treat this as just one variable, since either way it's going to work the exact same. All right, power rule. So add 1/2 to this, you get 3/2, and then dividing by 3/2, you get 2/3. This stays the same, and then you now have the 3/2 on top. Okay, add 1 to this again, you get 5/2, divide by 5/2. How should we do that? Well, it's just multiplying a 2 over 5 times 2 over 3, right? And then you still have this, but now it's to the 5/2. One last time, before you reach 0 here, add 1 to the power, you get 7 over 2. Divide by 7 over 2, you get multiplied by 2 over 7. So 2 over 7 times 2 over 5 times 2 over 3, x plus 4 to the 7 over 2. And of course, just like any other integration by parts, we would multiply the diagonals. Yeah, okay, so let's do the simplification of these coefficients as we go. So first of all, this part I would say is relatively easy. Just have 2/3 our coefficient, our x squared, and then we can just write this down. X plus 4 to the 3 halves, yeah? Next, we have this diagonal. Remember to subtract. And then we have 2 times these coefficients. So 2 times 2 times 2 is 8, and then 5 times 3 is 15. So we have 8 over 15. And then we have our polynomial term, which is an x, and then, well, factor, and then we have this factor out the back, which is x plus 4 to the 5 halves. And then finally, one last diagonal to multiply is this. 2 times 2 times 2 times 2 is 16. So the top becomes 16. On the bottom, 7 times 5 times 3 is 105. So that's the coefficient. We don't have the polynomial here. Then we just have this function part. So we have x plus 4 to the 7 halves. And it may look kind of ugly, but that's it. This is our final result for this integral. Of course, you can rewrite it using radicals and powers, but I don't know. This works too. And honestly, it probably looks a lot cleaner. Okay, yeah. We're currently on number 60. Okay, let's just go ahead and give it a shot. Why not? I'm gonna go straight into it. We have integral from -1 to 1 of the square root of 4 minus x squared dx. Okay. Now the thing with this is that it's actually a semicircle. So if you were to graph it, then it would have a radius of 2, right? Since 4 squared is 2 squared is 4. So it would look something like this, from -2 to 2. However, since your integration bounds are from -1 to 1, then you're going to be going under this area right here. From here to here, still going to be under a semicircle, just not the entire thing. So, and I'm not sure of any great formulas to use for this. I'm pretty sure there are, but right now, what I want to do is just use normal integration. And yeah, so to integrate this is a trig subcase. You have difference of squares inside of a square root. So what you do is, because the x is in the second term, right, is being subtracted off, then you would let it either equal to sine or cosine. And your a value would be the square root of this first number, which is just 2. So you would let x equal to, I'm going to use sine for this, and our a is 2. So x is equal to 2 sine theta. Right. Now we differentiate both sides to find our differential. The 2 is a coefficient, constant multiple, it stays. Then differentiating sine theta, really simple. You get cosine theta d theta. Okay, so now we can just replace whatever we have in here. Also, another thing to keep in mind is that we have integration bounds, which I almost forgot about. So here what we're going to do is we're going to, so first let's plug in the lower bound, right? And remember that, keep in mind that this is an x value. You want this lower bound in terms of theta. So -1 would be equal to 2 sine theta, right? Divide both sides by 2 and then take inverse sine. You get that inverse sine of -1 half would be equal to our theta. Okay. Now, yeah, so that's our lower bound. We're going to simplify this a little bit more later. Now let's go up to the upper bound. Very similar case where you have x is equal to 1, right? And you want it in terms of theta, and the relationship between x and theta is x is equal to 2 sine theta. So you just isolate theta, and you end up getting that inverse sine of 1 half is equal to theta. Okay, now, in fact, what you might remember is that these two values have nice representations on the unit circle. So if we were to draw out a unit circle over here, in fact, inverse sine the domain on the unit circle looks like this, right? Sorry, that's a really bad circle. But the domain goes from, the input can range anywhere from 1 to negative 1 to 1, right? So it would look like this. The reason why it looks like this, it's sideways, right, is because sine represents the y value. And you can see, in terms of y value, each point on each y value only corresponds with one point on this semicircle, right? So it makes sense for that to represent our domain of inverse sine. Okay, next up, we want to find out what these two values are on this unit circle. And to do that, all you have to do is go to, because inverse sine takes in values of, well, if you want to look at it on a unit circle, this would be the y value, right? So you'd go 1/2 is up here, and then negative 1/2 is down here, right? So what you want to do is you want to go to the unit circle, right? And then draw out a little angle. Same with this side. And see, this is a ratio, 1/2, right? We have our y value, well, this is a ratio. And then, so that represents the ratio of these side lengths, right? We have a 1:2 ratio here. Sorry, no, we have a 1:2 ratio. That's y value to hypotenuse, right? Because this is opposite over hypotenuse. So this would be our opposite, right? And this would be, of course, just 1. And same with this side right here. But I'm pretty sure you all know that. I'm not sure why exactly I'm explaining this. So the idea is to find the angle that these two ratios represent. And you can see that they're symmetrical from each other because the arguments are just negatives, right? And in fact, if you go to y equals 1/2, you can see that this angle is actually 30 degrees. And you have to remember this. So therefore, theta would be equal to 30 degrees, which is also equal to pi/6 when the argument is positive 1/2, right? And then if you just go the other way, you get the negative argument, which is just rotating in a negative direction. So you just get negative pi/6. So in fact, what you're doing here is you're integrating from -1 in the x world, which is negative pi/6 in the theta world, to positive pi/6, right? And then in your argument, let's take the 2 outside first, right? Since dx is just this, and then we can take the 2 outside using the linearity of the integral, since it's multiplicative. We can write down the cosine next. And then we have the root expression. So in the root here, what you notice is that if you plug in 2 sine theta into x, you get 4 sine squared theta, factor out a 4, and then you get a 1 in the first term. The subtraction is still there, and then you have the sine squared theta. Okay, and then I'm going to put down d theta finally. Okay, one more thing. Notice how this is an odd integral, even though we're working in integrand, no, not odd, even. Because if you look at this, we're integrating over a graph that is symmetrical across the y-axis. So what you can actually do is you can just find the area from 0 to 1, right? Ignore the other half, but since it's symmetrical, just double it. So what that equates to in our notation is doubling it, right, 2 times, and then taking the bound and going from 0 to pi/6 instead of, a symmetrical boundary on both sides. So we have 0 to pi/6. Okay, meanwhile, what we can do is we can just take the square root of each of these, since you can still simplify it further. So square root of 4 is 2, right? And I'm going to put down the cosine theta. Okay, and then notice that 1 minus sine squared theta is cosine squared theta. The root and the square cancel out, so you just have cosine theta, well, the 2 times cosine theta, and then this is just another cosine theta. So I'm going to write down a squared. integrating cosine squared theta, we can use our identity. So what this is, you can replace it with, and I've done this multiple times before, but I'm writing it out now for some reason, but it's just this, right? So if you put this in where you have this, then you see the 2 on the inside and the 2 on the outside, they cancel. And the 2's on the outside multiply to make 4. So you have 4 times integral from 0 to pi over 6 of 2 times that, right? But the 2's cancel out, as I said, so you're just left with whatever's in the numerator there, which is 1 plus cosine of 2 theta, close parentheses, d theta. Okay, now all we need to do is integrate, since you can integrate both of these. We have a 4 on the very outside, and I'm going to draw in brackets now, because we're going to do the integration. Integrating 1 d theta gives you theta. Integrating cosine of 2 theta d theta gives you, with the reverse chain rule, you have to divide by 2. Integrating cosine, you get a sine. And then, of course, the argument would stay the same. And then now all you need to do is plug in your bounds from 0 to pi over 6. Notice that if you plug in 0 here, this term goes to 0. And plug in 0 here, sine of 2 times 0 gives you sine of 0, which is just 0. That means the second term also goes to 0, meaning this 0 evaluates to completely 0, right? So all you need to do is really just plug in pi over 6, since there's nothing to subtract, it's just a 0. So you have 4 times pi over 6, then you would add 1/2 times sine of, and of course 2 times pi over 6 is just pi over 3. Alright, finally, first let's distribute the 4 into the pi over 6, and we get 2 pi over 3. And then, secondly, what we can do is distribute the 4 into there. We get a 2. So keep in mind, we're going to replace that with the 2. However, sine of pi over 3, go back to the unit circle. This earlier was 60 degrees. Now we want sine of, earlier this was 30 degrees, right? Which is pi over 6. We want pi over 3 now. So this would be 60 degrees. And you can see that the sine up here is not 1/2, it's above 1/2, meaning it's going to be root 3 over 2. All right, so this value evaluates to root 3 over 2. And of course, we had a 2 multiplying in here earlier. 2 times root 3 over 2, the 2's cancel, you're just left with a root 3. And that's it. I'm pretty sure there are formulas that will get you this exact number for the area under a semicircle, completely geometrically, but this is the integration behind all that. Yep, that's number 60. All right, next we have number 61. Number 61. Number 61 is the integral. This one's indefinite again. We have square root of x squared plus 4x. So you can see again that this is another case of trig sub, because we have a quadratic that's not a perfect square inside of our root. So we just got to get to work. First of all, first step is always to complete the square. So completing the square for x squared plus 4x, you would have to, that would just give you positive 4. Right, and of course, if you added 4, you also have to subtract 4 to make sure it stays the same. This is now a perfect square trinomial. You are able to rewrite it as a binomial squared. And of course, the binomial is x plus 2 squared, right? And then still have the minus 4. Next, to make this completely sum of squares or difference of squares, all you need to do is rewrite this, make a change of variables, right? So you would let u equal to x plus 2, right? And then this implies that, very simply, du is equal to dx. So here you get integral of x plus 2 is now just a u, it is still squared, and you're subtracting 4. And then dx is equal to du, so we're just going to replace it. Now you can see that this is a difference of squares case inside of a square root. What we want to do now is just make a substitution, make a trig sub, right? And since the u is in the first term, you want to use secant. In fact, you can use cosecant, because the cosecant identity looks the exact same as the secant one, but I think secant is a lot nicer to work with. Everyone's more used to it. So, our a value would need to be 2, right? Since the square root of the second value right here is 2. So a times secant theta. And then differentiating both sides, you would get du is equal to 2, and then differentiating secant gives you secant tangent. And then d theta, of course. Okay, so now just plug everything back in. You get that. First of all, I'm going to write down the du. So we have 2 times the integral of secant theta tangent theta, right? And then we have the root. So plug in 2 secant theta into u, distribute the square, you get 4 secant squared theta. Factor out of 4 root of 4 times. After factoring it out, you're left with a secant squared theta, and then factoring out of 4 from 4, you get minus 1, right? And then that's equal to tangent squared, so we're going to put that down. Of course, and then we still have our d theta to cap it all off. Okay. This root 4 is just 2. We're going to bring that outside. Multiply it with this 2, you get a 4. And then root of tangent squared, it's just normal tangent, so you get secant, and then tangent, but now it's squared since there's 2 of them, d theta. All right, so there's not much you can do with this yet, right? So what we're going to do is we're going to break this tangent squared guy into a secant squared minus 1. So the secant theta stays, but then now this tangent squared is going to become secant squared theta minus 1 d theta. Distribute this, and then also break up the integral, right? So the coefficient also distributes as well. Secant times secant squared gives you secant cubed, right? And then we're going to close this first integral. And remember, the coefficient distributes, and we have a negative sign here. So we have a minus 4 times the integral of secant theta times 1 is simply secant theta d theta. In fact, what I'm going to do is I'm actually going to keep the 4 factored out, because I think it might be a lot more efficient that way. So yeah, I'm going to just draw in parentheses. So that is breaking this middle guy up. So we still have a 4 as our coefficient on the outside, right? This is standard, or at least I hope it is at this point. We did it earlier. It is just 1/2 times secant theta tangent theta. And then you add 1/2 natural log of the absolute value of secant theta plus tangent theta. Okay. Second term, you would subtract off the integral of that, which is just natural log of secant theta plus tangent theta. Okay, so that's it. Notice that for this and that, they're like terms. So you want to do 1/2 minus 1, you just get negative 1/2. And meanwhile, I'm going to distribute in the 4. Yeah. I'm going to distribute in the 4 as well. So here we get 4 times 1/2 is 2. And then the secant theta, tangent theta stays. Right? And then, of course, here, 1/2 minus 1, you get negative 1/2. 4 times negative 1/2 gives you a negative 2. And then, of course, you have the function part, which is natural log of the absolute value of secant theta plus tangent theta. Okay, So you're almost done. Now you got to go back to our x world, which is what we were originally in. So to do that, we need to be able, let's hop straight back from theta all the way to x, because this u stage, there's only been one line. Let's just make it more efficient, right? So we know that u is equal to x plus 2, so therefore x plus 2 is equal to u, right? But notice how u is also equal to 2 secant theta. So x plus 2 equals to 2 secant theta. Now, to be able to plug in whatever we want for theta, we need to be able to isolate theta. So what we do is divide both sides by 2 first, and then take inverse secant on both sides. So we get that the inverse secant of x plus 2, but now divide by 2, which was originally the outside right here, is equal to just theta by itself. Okay, so what good does this do us? Well, you know what? In fact, let's also isolate secant over here, because it will be helpful for us in the future. And to do that, just divide both sides by 2, right? I'm gonna write this in black. So we have x plus 2 over 2, and then this is equal to secant theta. Okay, so that's that. Now we just need to draw a right triangle, because our final answer right here, in terms of theta, at least, contains a tangent, and we don't know what secant, what tangent is in terms of that. So we're going to draw out a right triangle. Now remember, the argument of inverse secant is a ratio of side lengths, right? And the side lengths are just the ratio of secant, which is hypotenuse over adjacent. So this would be x plus 2, and adjacent would be 2. Solve for the other side, you just get the difference of this squared and then that squared, right? And in fact, what you see is that this squared is right here, subtracting off that squared is right here, and this comes directly from our integrand, our original integrand. So this just gives us x squared plus 4x. Ah, nice. So now we can just solve for tangent, and tangent is opposite over hypotenuse. So, no, sorry, not hypotenuse, adjacent. So we have this over that for our tangent. All right, easy. Let's plug it back in now. So we have, this is equal to 2 times, right? And we have a secant theta there, and we see that secant theta is equal to x plus 2 over 2. And then we have a tangent theta, which is equal to opposite over adjacent, which is just root of x squared plus 4x over adjacent, right? Similar story here, we just replace each of the trig functions with our algebraic expressions. Secant is just this. And notice how secant and tangent actually have a common denominator, right? They're both 2. They both have adjacent in their denominator. So what we do is we can combine these two. And since we're just adding, we can just add on whatever's in the numerator of tangent, which is just this. And divide everything by 2 because we combine the fractions. All right, first order of business, notice that we're able to cancel this and, well, that out, right? So, and so we got that. Second thing, and this is pretty important, I'd say, but it really depends on you whether or not you would like to consider this, but notice how we have a quotient inside of our natural log. This means we're able to split the natural log up as -2 natural log of, and then the numerator, right, which I'll just call f of x, and then you'd want to subtract off, and I'm drawing a parentheses here since we're really just splitting from natural log. The coefficient we can just keep on the outside for now, but we're subtracting off whatever is in there, whatever's in here. So we have natural log of 2, right? So because the 2 is in the denominator, so distribute the 2 in now, we get -2 natural log of absolute value of f of x. That's still there. However, Yeah, okay, anyways, distributing the -2 here, you get negative times negative, which is positive 2, and then ln 2, right? And what do you notice? This is just a constant, right? So we're going to call this top half f of x, right? That's what we just did. But I'll just label that to point it out a little bit more explicitly. Notice that this is just a constant. So in reality, we can just include this in our plus c at the very end. So we can actually completely just get rid of that for now, right? Since there's no function inside of that, unless it's a constant function, but that's why the plus c exists. So very end, we get that this is equal to, see how there's still 1/2 here? We can bring that out as a coefficient because I think it looks nicer that way. We have an x plus 2. And then we have a rooty boy right there, which is square root of x squared plus 4x. Next up, you see that all we're left with is -2 times the natural log of the absolute value of f of x. And f of x is just whatever's in the numerator there, as you can see. So you have x plus 2 plus square root of x squared plus 4x. Close the absolute value. That's your final integrand. Sorry, that's your final result for this integral right here. And just box it. An alternate option you have would to be to distribute this, right? Because you see how we have a binomial here. You can make this first term into 2 terms, but it's completely optional. I wouldn't do that. Yeah, that's number 61. Okay, next we have number 62. Number 62 is something pretty fun. X squared times e to the x cubed dx. Well, without the x squared, this would be completely non-elementary since there's no way you can integrate that by itself. But with the x squared, notice how inside the argument of the exponential function, which is just whatever's in the exponent, you have an x cubed in the exponent, right? You can make a substitution since x squared dx is just a constant times whatever's in the argument of the exponential function. So let's just make a substitution. We would let u equal to whatever's in the argument of the x function. So that would be x cubed, right? And then calculate du. This would just be equal to 3x squared dx. Notice how we have an x squared dx here, we have an x squared dx here. However, there's a 3. So to isolate the x squared dx, we just have to divide both sides by 3. So we get 1/3 du is equal to x squared dx. Simple. And so this dx is equal to 1/3 du, this dx, right? So I'm going to bring the 1/3 outside, and then I'm going to put down, and then our x squared dx is just that, right? So all we need to really consider later is the du. Now we just have e to the x cubed, and of course x cubed is our u. So e to the u du. Very simple. We just get constant multiple outside stays and then exponential function of our u, which is x cubed. Right. Add c and you're done. Because the integral of e to the u is just e to the u. So just directly substitute back. I'm kind of lazy to write this out in more than just a couple steps. So that's very simple. What about the next one? Next one we have something that looks extremely similar. But this one's number 63. We have integral of x cubed e to the x squared dx. Well, you can think about this systematically or not, whether you want to or not, because this looks very similar to the previous one. You can do this in 2 ways. Either just do the same thing as last time and see how it works out for you, or you can do this very systematically. And we'll just do a wild guess and do what we did last time. But you can also deduce this just by thinking about what's going on in the integrand. So we're going to do the same thing. We're going to let u be there, even though x cubed isn't necessarily our du. Let's still try it, right? So we would let u equal to x squared. This would mean du is equal to 2x dx. And so yeah, let's just plug in well, you know what? Right now I'm going to do the traditional way students are taught and just isolate dx, right? So we have du over 2x is equal to dx, right? So we're going to put down integral of x cubed. We can't do much with x cubed, right? But we have e to the x squared. X squared is just u. We have du over 2x, sorry. Notice how an x here and an x here is able to cancel out, right? So you're left with, and in addition, I'm going to bring this multiplicative 1/2 outside. And then you're multiplying by the integral of, now this becomes x squared times e to the u du. One more thing, and this is the cool part. Notice how x squared is just u in of itself, right? So this is really just equal to 1/2 times the integral of u times e to the u du. All right, this is a simple case of a polynomial times an exponential function. We're able to integrate the exponential function very well. So, and we're able to differentiate the polynomial and eventually get to 0. So we're going to use integration by parts. We're going to differentiate u and then integrate e to the u. Differentiating u, you get 1. Differentiating 1, you get 0. Integrating e to the u, you get e to the u and then e to the u again. Here, you would multiply the diagonals, right, and then integrate the rows. However, you can see there's a 0 in the column, so you don't need to integrate this last row. So the constant multiple outside is still going to stay, and then whatever this integral is, not including the constant, is just whatever we have in there. So this becomes, the first diagonal is e to the u. Second diagonal is, remember this minus 1 times e to the u is just normal e to the u. Okay, so next what we do is plug in whatever u was, right, x squared. And in addition, let's also distribute the 1/2. So this becomes 1/2 times the first term, which is u is just x squared, e to the x squared. And then the subtraction sign still stays, and then you would distribute into 1/2 again, e to the u, which is just x squared. Okay, and that's it for this one. As C, and you are done. Yeah. Okay, number 64. Number 64, I think it looks pretty cool. We have integral of tangent x times the natural log of cosine x dx. Integration by parts, right? Because you can differentiate this. You're able to integrate that, right? So we're gonna use the DI method for this once again. Differentiate. No, sorry, not tangent. You would differentiate the natural log, right? And you would integrate tangent. So differentiating this, mental math, right? Whatever is in here goes in the, whatever the argument is, it goes in the denominator. Chain rule, the derivative of the argument needs to go in the numerator. So because you're multiplying by the derivative of the inside. So you get negative sine, right, over cosine. Sine over cosine is just tangent, so you get negative tangent. What about here? Here you just get natural log of, I'm not going to put absolute value down for the sake of integration, right, of secant. Okay, now notice how if you were to just rewrite secant as 1 over cosine, or in other words, cosine x to the negative 1th power, you're able to bring the negative 1 to the front and just get negative natural log of cosine. Cool. So next, what we do, normal integration by parts, we would multiply the diagonals and then integrate the rows. So multiplying the diagonals, we just get, and in fact what I'm going to do is I'm going to write an implication symbol, since this is going to be a repeating case, since multiplying these two, you get very similar to what's up there. So we have the integral of tangent x times the natural log of cosine x is dx, of course, is equivalent to, first of all, let's multiply the diagonal, right? So we have the negative, and then natural log of cosine x is multiplied together twice, so we can use this notation. Negative natural log squared of cosine x, and apparently this is actually valid. Next, we have to do the row that we integrate. Negative times negative times negative, triple negative makes a negative, so we have a minus sign out in front. Then we have the integral of whatever these functions are, right? So we have tangent x times the natural log of cosine x dx. Okay, so now what you do is, you see you have one of these integrals on this side, one and negative one of them on this side. To be able to isolate the integral, let's isolate it on the left side. We would add one of these integrals on each side, right? Adding 1 to 1, you get 2. Very cool. And then, of course, the integrand still stays the same. And then, of course, we don't do much with this quite yet. And then adding 1 to negative 1, you get 0. So there's no more integrals on the right-hand side of the equal sign. And then to be able to isolate the integral by itself, you see, you just have a coefficient of 2. Just divide by 2, right? So you get that integral of tangent x times, not cosine x, the natural log of cosine x. Dx is really just equal to, after dividing both sides by 2, you get negative 1/2, then the natural log squared of cosine x. Yeah, so that's your final result. And in fact, what you can do is you can also rewrite, another result would actually just be secant on the inside. Since what you can do with this is, well, let's start from this step right here. We see that this is equal to negative natural log of cosine x times natural log of cosine x, right? And of course, what you can do is you can use another property where you can take this guy, right, and then write this as secant to the negative 1, right? Since cosine is the reciprocal of secant. For this first natural log, take this negative sign, move it up into there, and then you have a negative 1, right? So now what you can do is, see this first one now, you have a secant, right? Natural log of secant. And for the second one, what you can do is you can use a log property to take the negative 1 of the exponent and put it down at the front. So you can do that. And then, of course, you just have whatever's on the inside left, natural log of secant x. And you can see that this is officially just natural log, negative natural log. And since there's 2 natural log of secant x's, just square it. And then inside the argument, there's still secant x. And of course, from this step, you still have to divide by 2 on both sides. So therefore, this is also equal to that, but divided by 2. So you get negative 1/2 times natural log squared of secant x plus c. And yeah, that's it. You are done. So there's 2 results. I'm not sure if they're shifted by a constant, but you can see that they're equal through log properties. Yeah. Right. And another way you can do it, of course, is just to take both of these exponents down to the front. They cancel, so you just have natural log of cosine x times natural log of secant x, right? But I think it looks cooler to write it in either of these ways. But also write down the third result. After dividing by 2, right, you have natural log of cosine x times the natural log of secant x. And then add c. So that's your third result. Okay, so pretty interesting, but yeah. That's number 64. Okay. Number 65 is the integral of a rational expression. We have 1 over x cubed minus 4x squared dx. Alright, I'll give you a second to think about what to do with this one. Right, it shouldn't be very difficult at all. Factor it and do partial fractions. Yeah. So on the bottom, you're able to factor out a common factor of x squared. So let's put the x squared on the outside. Dividing x cubed by x squared, you just get x. Dividing negative 4x squared by x squared, you just get negative 4. Alright, now you can't do much except for partial fraction decomposition. Yeah. So for this one, what you want to do is... Okay, you know what? I'm going to try something. And if it doesn't work, that's okay. But what we're going to do is going to take the reciprocal of both. So we can do partial fractions. I think another way that might work to do it is we're going to... This is really just x minus 4 to the negative 1th power, right? Negative 1 to the negative 1 since it's in the denominator. And so is this x squared. This is now x to the negative 2, right? Oh yeah, this wouldn't work because if you differentiate this entire thing, you wouldn't get that, right? You would actually get something with x minus 4 on the inside, so that wouldn't work. But that was my original thought of doing this, similar to the shortcut that I introduced in a few questions prior to this. Namely, which one was it? It was number 54. But for this one, we're gonna have to do partial fraction decomposition. It's okay. So the way we do it, if you have a perfect square in the denominator, is, of course, you still have this setup, right? And then, in fact, for any perfect square factor, what you want to do is you want to have a linear term on top of just it by itself, no square, right? And then you would add on a linear factor by the squared version of it. And then, of course, you have our third factor, which is just x minus 4. And since it's linear, we can have a constant on top. Now, the reason why this works is this: if you just do it the normal way, right? Ax plus b over our x squared on the bottom. Notice how if you just split up the fraction, ax over x squared is just equal to a over x. And then b over x squared can't do much, right? So that's a very elementary explanation for the reason why this is how you do it. Now, you can do cover-up method for both b and c because they exist right here. But for a, we're going to need to do something slightly different, but you'll see that it makes a lot of sense. So, to do cover-up method for b, this is equal to, if you just set the denominator equal to 0, then that means x would need to be equal to 0. Cover up the x squared and then set x equal to 0. 0 minus, so you'd get 1 over 0 minus 4, right? And this one is very simple. It is equal to negative 1 over 4. And of course, c, very similar case. You just want to set this denominator equal to 0. X would need to be equal to 4. Cover up the x minus 4, right? And then you just plug in a 4 to x. So you get this is equal to 1 over 4, right, squared. And then this is equal to 1 over 16. So that's it for those two. Now let's rewrite this, right? But Of course, we still have a over x. We haven't solved for that yet, but b we now know is equal to negative 1 over 4. All right, I'm going to write this as like a coefficient, but just keep in mind that it's equivalent to what we have above. And then, of course, I'm also going to write this 1 over 16 times 1 over x minus 4 as a coefficient. Right. So now what you notice is, regardless of what x is, right, since we're doing an integral, x can be anything that's within this, the domain of this function right here. So that means if you just set x equal to anything, that leaves you with an answer, right? Then you're able to solve for a, because x can be anything that's within the domain. So therefore, that leaves us with a, which is the only variable that we need to look for. So just set x equal to a very nice number, right? Say 1. Let's x set 1, right? Because we're looking for an easy way to get through this. This implies that 1 over 1 squared, which returns 1, times 1 minus 4 is equal to a over 1 minus 1/4 times 1 over 1 squared, and then plus 1 over 16 times 1 over 1 minus 4. Okay, let's simplify this down. This left-hand side, you can just ignore this 1 squared since it's equal to 1. And then 1 minus 4 is equal to negative 3. So this is just negative 1 over 3, right? How about the right-hand side? A over 1 is just a. And then this entire thing, 1 over 1 squared is just 1. So we still have a minus 1/4. And then even further right of that, we have 1 over 1 minus 4, which is, of course, as we said here, is negative 1 over 3. And then multiply this with 1 over 16, you get a negative 1 over 48. Okay, so now we just isolate a, right? So we just need to look for negative 1/3, and then add both of these on the left-hand side, plus 1/4 plus 1 over 48 is equal to a stays. And to do this, we just find a common denominator, which is just 48. So multiplying both top and the bottom by 16 to get to 48, you would get 16. And then, of course, I'm going to combine all the fractions, so I'm going to actually write this negative up here with the 16. Multiply the top and the bottom by 12 to get 48, you get a plus 12. And then, of course, this is already 48, so we just plus 1. And over 48. The top, and of course, this evaluates to a, right? So the top evaluates to negative 4 plus 1 is negative 3, right? Negative 3 over 48 is just negative 1 over 16. So this isn't witchcraft, right? I didn't just choose the right number to plug in. Of course, x can be anything, right? Because you're just finding that this is a whole line. X is defined infinitely many places. So just choose any x. It'll always work, right? Since you're just left with the a, right? And it'll always return the right value since you have only one variable in here, which is really just a, right? Since x can be equal to anything you want. So just set x to be equal to anything. That might be easy to work with, and then you'll be able to solve for a. So yeah. So here I'm going to write down on this side, we're going to replace it with the thing we broke up into. So we have negative 1 over 16 times 1 over x. Makes sense. Plus, well, b is actually negative, right? B is negative 1 over 4, so negative 1 over 4 times 1 over x squared. And c is 1 over 16, so you're adding coefficient of 1 over 16, and then times 1 minus x, 1 over 4 minus x minus 4 dx. Okay, now you're able to integrate. Since this is natural log, this is natural log, and negative 1 over x squared is standard. So this returns coefficient of negative 1 over 16 stays for the first term, And then integrating 1 over x, you just get natural log of x. Absolute value, of course, don't forget that. And then integrating negative 1 over x squared gives you positive 1 over x. And of course, the coefficient of 1/4 stays there. And in fact, what I'm going to do is, since 4 and the x are still both in the denominator, I'm going to multiply the fractions together and just write this as 1 over 4x, because it still works. Okay, this one. This is just natural log of, again, right? Coefficient stays, 1 over 16, and then we just have the natural log of the absolute value of the denominator. Since the denominator here is linear, and x's coefficient is just 1. So this is our final result. We just add c, and we are done. Simple. That's number 65. And that's how this kind of partial fraction decomposition would work. Number 66 is the integral of sine x times cosine of 2x dx. Now, don't overthink this and try to expand out the cosine of 2x, right? Instead, a much easier way to do this is to recognize that you don't need the arguments to be the same, right? Because what you can do here is, since it's just two factors multiplying together, you can differentiate one and integrate the other, integration by parts. And of course, it's going to repeat since it's sine and cosine, so you'll get a repeating case of the DI method. I would personally differentiate cosine of 2x, since chain rule is easier to mentally process than reverse chain rule for most of us. So differentiating cosine, you get negative sine, and of course chain rule says multiply the 2 outside, right? Integrating sine, you get negative cosine. And then it's not repeating yet, so let's do it one more time. Differentiating sine of 2x, right, gives you 2 cosine of 2x, and the negative outside stays. And the negative 2 outside stays. So negative 2 times 2 cosine of 2x gives you negative 4 cosine of 2x. And then integrating a normal cosine just gives you a normal sine. Multiply the diagonals, and you see we're stopping here because it repeats. We have a sine x and a cosine of 2x, right? We just have the coefficient on the outside, which we can mess around with later. So let's write this out. The original integral, which is the integral of sine x times cosine of 2x dx is equal to this times that, so we have negative cosine x times cosine of 2x. And then we have a triple negative, which makes a negative, right? We have a coefficient of 2, and then sine x times sine of 2x. And of course, don't forget, you have to integrate this row right here. So we're going to write this in an integral. Double negative makes a positive, so you're going to add the integral. Let's bring the 4 outside first, right? And then the integral of sine x times cosine of 2x. Subtract, now notice that this integral and that integral are the same. So to be able to isolate the integrals, just subtract 4 of them on both sides. 1 minus 4 gives you negative 3. Right? Okay, and then this part still stays because you're not messing around with it. And then minus 2 sine x sine of 2x, right? And then, of course, subtracting 4 times that integral on the right-hand side just simply returns 0. And don't forget the dx. Yeah, and then now all we need to do to isolate our original integral, which is in black here, is just divide both sides by negative 3. So this means integral of sine x cosine of 2x is, dx is just, and I forgot the dx here. You know what, let's erase this and see if we can jam it in. Yeah, there we go. And for this one, first of all, you're dividing both sides by negative 3, so then a negative divided by negative makes positive, and you just have 1/3. Then the function part, cosine x times cosine of 2x stays. And then, of course, you have a negative here, dividing by negative there, just returns a positive. 2 divided by 3, right? And then the function part, sine x, sine of 2x. And that's it. See, this and that are equal, right? So, and it's equal to this thing, which is just your finished product. So, yeah, box your final answer, and you're done with this one. That is number 66, and that is also page 3, I think. Yeah, so that's number 66. Let's keep on going. Then we have number 67. 67 is the integral of another funny looking one, 2 to the ln x dx. So, a very unknown log property is that a to the log of log base b of c is actually equal to c to the log base b of a, right? And I'll prove it to you in this case, but you can use a similar method to just be able to quickly prove any, like this general form right here. And in fact, you're able to just apply this straight to that, but I'm gonna still prove it either way because it's more intuitive if I do it that way. So, what is 2? 2 is e to the natural log of 2, right? So we have e to the natural log of 2 times the natural log of x, right? And notice how e to the natural log of x makes an x. So we just have an x in the base. And of course, we still have a natural log of 2 up in the numerator. But yeah. And it looks kind of weird, but recognize that this is just a power rule, a reverse power rule case. Add 1 to the numerator and then divide by it. So you're dividing by an ln 2 plus 1, which doesn't have a nice form except for just that, right? Multiplying by x to the power of ln 2 plus 1. Add c and you're done, because there's no better way to simplify this. At least that's what I think. Okay. Yep. So next we have a weird looking trigonometric one. Number 68 is integral of 1 plus cosine of 2x dx. This one is pretty interesting. But I have an idea. So we know that How do we do this? Sine squared plus cosine squared. Let me try a couple things because I'm not completely sure how to do this one. So, first of all, I have an idea. We can just expand the 1 to be a cosine squared x plus sine squared x, right? And of course, we're adding on the cosine of 2x, which means we also have to add the equivalent form, which is cosine squared x minus sine squared x. Here we notice how the sine x, right, positive sine x and negative sine x, they additively cancel. So you're left with integral of square root, and then there's 2 cosine squareds, so we're just going to write it as 2 cosine squared, right? And then, of course, the square root of 2, you can't really reduce that, so, and that's just a constant multiple, so we're going to bring that outside of the integral. And then the square root of cosine squared just gives you square root of normal cosine. And of course, everyone knows what the integral of normal cosine is, so we're just going to write it down. It's just sine x. That's it. Add C, and you are done. This one may look kind of intimidating at first, but I mean, if you just recognize that this and that both have really nice expressions in terms of like cosine squared and sine squared, then you might be able to make some progress and eventually end up with an answer. Okay. Next one. I think this is where the integrals get kind of difficult because these are not immediately obvious at first what you need to do. Okay, number 69, of course, is number 69. We have integral of 1 over 1 plus tangent x. What you can do is multiply everything by cosine. So I think I'm gonna try it because it never hurts, right? So multiplying both the top and the bottom by cosine, multiplying the top by cosine, very simple, you just get cosine x. On the bottom, distribute the cosine x, you get cosine x times 1, which is cosine x. Then cosine x times sine x over cosine, right? So the cosine and the cosine, they would cancel, you're just left with a sine. Dx. And of course, it doesn't look nice, but what we can do is rewrite everything with arguments of 2x. If you ever see something that looks like this, I would always consider what would happen if you just multiplied in a conjugate at the bottom, right? Because then what happens then is you might be able to get something nice or not, you know. But for now, if we multiply in the conjugate, you get the difference of squares of the two terms in the bottom. And then multiplying the conjugate, you get, so the top is cosine x, right? And then you multiply in a cosine minus sine over, in the bottom, cosine squared plus sine, minus sine squared, right? This is taking a while. I should probably find a better way to switch markers, but this feels like the most cohesive to me because you're just cycling through the markers one by one, right? Okay. Let's just distribute out the top for now because what you find is something pretty cool. Cosine x times cosine x is cosine squared x, and then minus, and then just I'm gonna write sine x cosine x. Okay, in the bottom, it stays. So now I want you to notice that if you just pay attention and think about it, then cosine squared, we have an identity for that in terms of something times with an argument of 2x on the inside. Same with this. This is actually the direct form of cosine of 2x, right? This thing, it looks very similar to the sine of 2x, right? You just have to multiply in some coefficients. So in fact, let's rewrite all of these as sines and cosines, but with 2x inside of the argument. So let's give it a shot. So this right here is just 1 plus cosine of 2x over 2, right? This right here, so sine of 2x is equal to 2 sine x cosine x. So to be able to pull that out, we want 1/2 times 2 times sine x times cosine x. So the 2 sine x cosine x, together it makes a sine of 2x. Okay, and the bottom is extremely simply just cosine of 2x dx. Okay. Now, notice in the numerator you have a common factor of 1/2. Let's take that to the outside. Right, and now you have the integral of, So now you're just left with the numerator. In the numerator, you have 1 plus cosine of 2x minus 1, just normal sine of 2x divided by cosine of 2x, never changed. Now, don't get confused by the 2x in the argument. Just split up the integral, right? You know what? Before we do that, let's make a u substitution. Right. So because all the x's now are paired with 2, so it doesn't hurt to make a u substitution because it's linear. So we would let u equal to 2x. Therefore, du is equal to 2 times dx, right? And we just want to isolate dx since there's nothing we can pair dx up with. So this implies that dividing both sides by 2 gives you 1/2 du is equal to dx. So here, because 1/2 is multiplicative among the entire fraction, I'm going to take it to the outside of the integral, multiply it in with that, you just get 1/4. And then times the integral of, in the top, you just have 1 plus cosine of 2x, which is u, and then minus sine of 2x, which is sine of u, right? And then the bottom, you have another cosine of 2x, so it's just u. All right, now just plug a du here, and what you're able to do is just to break it up. So, yep. So you now want to integrate, and I'm going to multiply into 1/4 on the outside. So we have a few integrals, right? So first one is 1 over cosine u, which is just integral of reciprocal of cosine is just secant u. Next up, we have cosine over cosine, which is even easier. We just have plus the integral of cosine over cosine just gives you 1, and then du, right? And then lastly, we have negative sine over cosine. You can bring the minus sign outside, and then the integral of sine over cosine is just tangent. And of course, the arguments are the same, so we just put a u in the tangent, du. Okay, and all of these are standard. So let's just do it then. 1/4 times integral of that is natural log of secant x plus tangent x. That is just very, very simply u. Sorry, and this would be u and u. And then that you would subtract off natural log of the absolute value of secant u. And then that, okay. Now distribute the 1/4 and then also plug in whatever the hell u used to be, 2x, right? And you get 1/4 times the natural log of secant of u is equal to 2x plus tangent of 2x, right? And then here you have plus, and then distribute the 1/4, of course, right? Then u is equal to 2x, and then you would subtract off, distribute the 1/4 again, natural log of secant u, which is just secant of 2x. Okay, so we're not done yet, since what you realize is that if the coefficients of the logs are the same, then you're just able to combine them. So combining the logs, you get, and since this is subtraction, this ends up in the denominator. So you get the natural log of absolute value of this, which is positive, right? So we have secant of 2x plus tangent of 2x, and then the negative one in the denominator, which is just secant of 2x. Absolute value bar. Of course, 1/4 times 2 is just 1/2. And then the x is still there. Alright, next, I want you to notice, if you split the fraction on the inside, secant of 2x over secant of 2x is just 1. So we have 1/4 times the natural log of 1. tangent of 2x over secant of 2x, well, if you think about it, tangent is sine over cosine, and secant is 1 over cosine, right? So if I just write it out for you, I think we did this earlier, but sine x over cosine, and in fact the argument can be anything, right? Over 1 over cosine. And I mentioned that because our argument here is 2x. But notice that if you just multiply in a cosine at the top, this cancels with that. Multiply in a cosine on the top and the bottom, so it maintains equality. So you just get sine x over 1, which is just sine x. And in this case, our argument is actually 2x, so we get sine, but of 2x. And then close the absolute value bar. And then, in fact, you don't need the absolute value here anymore either, because notice, sine of 2x is just a sine wave, but like you compressed it on the like x-axis, right? Right. So this is what sine of 2x looks like. This down here is -1. If you just shift everything up by 1, then notice that this has now become the absolute minimum of the sine function becomes y equals 0. And because it's never negative anymore, we don't need the absolute value. Right. So, in fact, I'm going to just go ahead and replace those with parentheses. And then plus 1/2 x doesn't change, add c, and that's it for this one. Yep, there you have it. Okay, that was number 69. Really, really funny, you know. Up next we have another funny boy, but that's because I think it looks pretty cool. We have the integral from 1 over e to e, I think, of integral of square root of 1 minus natural log squared of x all over just x dx. First thing you might be able to notice is that everything is over x, and we also have a natural log of x everywhere else inside this integrand, so we could just make a substitution. We would let u equal to natural log of x, because our du is just 1 over x dx, right? So do that, we get du is equal to 1 over x dx. And that's exactly what we have here, 1 over x dx. Now, remember, we have bounds now, so, and these are in terms of x. So now we want these in terms of u. So u of bound A, I'm just going to write it like that. I'm not sure how typically you would do that, but A is this one down here. You have the natural log of 1 over e, which is, do whatever you want with this, but it should be pretty easy. It just gives you -1. And then u of b, which is our second bound, upper bound, right? This is natural log of e, which gives you +1, right? So do this, we have integral from our first bound now in the u world is now -1, and the upper bound is 1. Then we have 1 over x dx is just our du, so we don't need to consider the denominator. We just have square root of 1 minus ln x squared, right? But ln x is just u, and of course, don't forget that it's squared. And then, of course, 1 over x dx is just du. I think this looks much better now, because what you're able to do is just a trig substitution, right? We have a difference of squares where our variable is in the second term inside of a square root. So here, of course, just like earlier, we're going to be using sine. Additionally, this first number right here is just 1, so we don't even need an a value. Our a is just equal to 1. So let u equal to sine theta, right? And then that would mean our differential would be equal to cosine theta. Don't forget the d theta, of course. All right, we swapped the bounds once. We need to swap them again because we're doing another change in variable. So this is in the u world, so -1 would need to be equal to sine theta, right? And then this implies that inverse sine of -1 just returns our theta. Similarly, for the upper bound in the u world, right, u is equal to sine of theta. And this implies that taking the inverse sine of both sides once again returns your lower bound, right? And of course, inverse sine of -1, if you just, let's draw a unit circle, right? Now, remember earlier I mentioned the inverse sine's domain looks like this in terms of the unit circle, right? This is -1, and this is 1. So this is just ratio of, this is just a ratio in here of your y value over the hypotenuse, right? So your y value here is -1, and your hypotenuse length is just 1. So this would actually represent the angle for your first theta, which of course is just -pi/2, since you're rotating in the negative direction 90 degrees. So this would be -pi/2. And of course, take a look at the other bound. It's symmetrical. It's just doing the same thing, but instead you're rotating normal pi/2 because you're rotating up. So our new bounds are going to be the integral from lower bound -1 in the theta world is just -pi/2. Upper bound 1 in the theta world is just normal pi/2. So the square root of 1 minus u, plug in sine for u, right? 1 minus sine squared is just cosine squared. Square root of cosine squared is just normal cosine. So this is really just cosine. Our du is cosine theta d theta, right? So we have a cosine theta times the cosine theta d theta. Two cosines, we have a cosine squared theta and then d theta, of course, all that garbage. But now I think it is easier to notice that this right here is actually even, right? Cosine is even. An even times an even function, right? Same idea of squaring it, gives you another even function. And because it's even and the bounds are just negative versions of each other, as I explained earlier, what you're able to do is just multiply the entire thing by 2, right? And then only integrate half of this, half of the way from -pi/2 to pi/2, which is 0 to pi/2. And of course, integrand has to stay the same. Cosine squared theta is, as we said earlier, equal to 1 plus cosine of 2 theta over 2. Now, typically we'd bring the over 2 outside, and we can do that here too, but that would just cancel with the 2 on the outside. So we're left with no more coefficient, it's just 1 now. And our bounds are still from 0 to pi/2, but now it's of the numerator of the equivalent of the sky, which is 1 plus cosine of 2 theta d theta. Okay, so integrate. Let's move this up here because I don't want to bend down to keep writing, right? So it's pretty cool how we went from e's and natural logs to pies and trig, right? But it was really set up this way, so I think that's really, really cool. Anyways, I'm going to draw in brackets now since we're going to integrate this. But integrating 1 in the theta world, you get theta. Integrating cosine of 2 theta in the theta world, well, integrating cosine, you would get sine, and then you have to do reverse chain rule, so you would have to divide by 2, so you get 1/2 times sine, and the argument remains the same, 2 theta. Evaluating from the lower bound to the upper bound, notice how plugging in 0, it just returns 0, right? So we don't need to consider this since it just returns 0. And that means this is equal to pi over 2, right? Plug in pi over 2 for theta plus 1/2 times the sine of 2 times pi over 2 is just normal pi. Sine of pi, if you're confused, let's draw out the rest of the unit circle. It looks ugly, but pi is just 180 degrees and sine is just our y value. And you see the y value at 180 degrees is just 0. So this is 0, meaning this entire term on the right at least is 0. So that means you end up with a very nice answer of just pi over 2. Cool, right? It looks very nice. So therefore this is equal to pi over 2. That's pretty interesting, I guess. Okay, number 71. Number 71 is integral, and this time it's indefinite again, of 1 over the cube root of x plus 1. But here the 1 is not inside the cube root. What the hell? How do we do this? Okay, so let's let u equal to the cube root of x and just see, right? Because this is really ugly right now, and this is really where our the only place where x exists in our integrand. So let's just try u substitution. Not sure whether to let u equal to just the cube root itself or a cube root plus 1. In fact, let's just do the cube root itself, right? So we have a u substitution. Let u equal to the cube root of x. This implies that du is equal to, well, this is this x to the 1/3 powered minus, subtract 1 from, well, first bring down the 1/3, right? So you're now working with a 3 in the denominator. Then subtract 1 from 1/3, you get negative 2/3. So what you end up with is x to the 2/3 in the denominator, right? Since this is a negative 2/3 in the numerator, it's equal to that. And in fact, you can rewrite this as cube root of x squared, right? And then don't forget to multiply by dx. So the cool thing about this is multiplying this on both sides, you're able to just simply isolate dx. In fact, we want 3 cube root of x squared here, and then du is equal to dx. Alright, now we want this in terms of u, since this is going to go straight into our dx. But that's pretty simple, since you're able to reverse the order of the radical and the exponentiation. We just have u, right, which is our cube root of x squared. So very simply, we have 3 times u squared du. That's dx. Okay, so we just calculated what our differential would be. I'm not quite done, not even close actually. But from now on, it looks a lot more simple than it would have otherwise looked. So cube root of x is just u plus 1, right? And because dx is just in the numerator, kinda, we can just rewrite the equivalent in the numerator too. So we have 3u squared, and then let's just write the du off to the side, because that's more or less convention. Let's bring the 3 outside. And then u squared over u plus 1 du. Okay, let's do some polynomial division, right? Because the degree on top is actually higher than the degree on the bottom. So if you just use synthetic division, this is very, very quick and easy. This is the quadratic coefficient, this is the linear coefficient, this is the constant coefficient, and then drop this down. We have a 1 down here, multiply these, bring it over, drop this down again, multiply these, bring it over, drop this down, and then this is just your remainder, right? So this becomes 1 times x, right? And then this becomes 1 times x to the 0th. X to 0th is just 1, so that represents a constant term, and this represents our linear term. So 3 on the outside stays. But after doing the polynomial division, right, we end up with an x, and then times a -1. No, and then a -1, right? Because -1 times is our constant term right here. And then we have 1 as a remainder. And as a remainder, you want to have the remainder on top of whatever you're originally dividing by. So you would add 1 over u plus 1. And this would not be x, this would be u because we're in the u world. But this is just for the sake of polynomial division. Okay, so integrating this now, since this is all doable, this is just reverse power rule, and then this is just the natural log, right? If 3 times all this crap, so integrating u, we get u 1/2 u squared. Integrating 1, we get normal u, and then integrating 1 over u plus 1, we get the natural log of u plus 1, right? Okay, now let's return back to the x world. Also, let's distribute the 3 in. So distributing the 3 in, you get 3/2, and then u squared is just cube root of x squared, right? Minus, and then distributing the 3, remember, 3 times u is just cube root of x. Sorry, no, I'm going to write this in red. Right, and then finally we have our natural log, and then u is just cube root of x. And then add 1. Boom. Done. That is your final result. Yeah, okay. So that's number 71. Number 72 looks extremely similar, and in fact, I'm pretty sure it's so similar that I can just do it up here. Number 72 is the integral of 1 over the cube root of x plus 1. Let's play spot the difference. This one, the 1 isn't under the cube root, this one it is. So I think this one's a lot more simple because you're just able to make a substitution. And then just use the reverse power rule, because cube root is nothing but an exponential, right? Kind of. So we would let u equal to the radicand of the cube root, so x plus 1. And then that means du is equal to dx. Pretty easy. Okay, so let's rewrite this as, we have 1 over cube root of u now, right? And then cube root of u is just u to the 1/3, and since it's in the denominator, we can rewrite it as u to the negative 1/3. And dx is equal to du, so I'm going to put that down. Alright, next, we just use reverse power rule now, since it looks very nice. Add 1 to the power, we get u to the 2/3, and then divide by 2/3. We just get 3/2. And of course, u is equal to x plus 1, right? So we have the cube root of, because the denominator inside of the exponent is just the nth root of your base, right? So, and the base is x plus 1. But don't forget to square it, because we still have the 2 over 3. And it looks kind of ugly, but it's really simple. That's it for number 72. Okay, yep, that's those two. Let's do a few more. We have number 73 up next. Number 73 is the integral of sine x plus cosine x dx, right? Okay, we know how to do this, right? This is just normal, very simple tricks that, and I'm pretty sure we might have done something that looked like this earlier on. So in fact, what we're going to do now is just to square this. So squaring this, you would need to now expand it out. So expanding this, first term squared is, sorry, I'm going to actually write it, color code it as I usually do. I'm getting kind of lazy. But sine squared x, right? And then plus 2 times the first term times the second term, and then the second term squared. Cosine squared x dx. Notice how this sine squared and adding it to this cosine squared returns a 1. So that we can write down as our first term. And notice how this becomes sine of 2x. It is just the identity, right? So it may not be as simple, but it is close enough. It's very, very elementary. Integrating 1 in the x world, you just get x. Integrating sine of 2x in the x world, you get a negative cosine, and then of course reverse chain rule, you have to divide by 2. That's it. It's a lot simpler than anything else we've done in like the past hour or so. Okay, that's it for this one. Yeah, okay. Very simple, very easy. Next up, let's do number 74. Number 74 is the integral of 2x times the natural log of 1 plus x. Okay, so I think because of the natural log, we don't know how to integrate that. Just like any other case where you find a natural log multiplied in, you would want to differentiate that. However, typically you also want to differentiate the polynomial so it goes to 0. But it's very difficult to integrate natural log of x. So we're going to stick with our original plan and do integration by parts, where we differentiate the log 1 plus x. And integrate 2x. Differentiating this, we get 1 plus x in the denominator and just 1 in the numerator because the derivative of the argument is just 1. Integrating 2x, you get x squared. So now we are actually able to do this because this integral becomes a rational expression and you can just multiply that. So this is equal to, multiplying the diagonals, you get x squared times natural log of 1 plus x. And then here you would want to subtract off integral of x squared times 1 over 1 plus x, which is just x squared over 1 plus x. So this one, same thing as earlier, because the top is a higher degree than the bottom. Let's do some polynomial division. Let's use long division here. Let's do x plus 1, then divided by x squared plus 0x plus 0. There's one x that goes into x squared. No, okay, x plus 1 times x is equal to x squared. This is kind of difficult to explain, but just multiply this and that and then subtract it from here. So x times x is x squared, x times 1 is just x. So this and that kind of just cancel, right? So you just have a negative x left. And then how many x plus 1s goes into negative x? Well, I would say negative 1, right? And then multiply this and that, and then subtract it from here. Negative 1 times x is negative x. Negative 1 times 1 is just negative 1, right? So then this and that cancel, and then you just have negative and negative 1, which is equal to positive 1. Okay, so let's go over here. Let's rewrite whatever the hell we had in the first term, and then subtract off the integral of, we did the polynomial division, we just have an x minus 1, right? And we have a remainder of 1, which we would just put in the numerator of this. And by that, I mean like 1 over whatever we were dividing by. And then dx. Now, just integrate. Because, and this is actually, I'm pretty sure it is the exact same as the one we just had to do. But this one, the first term stays the same. Remember to distribute the negative sign, of course. Integral of x is just 1/2 x squared. Integral of -1 is just negative x, but remember to distribute the negative, so you end up getting a positive x. And then integral of 1 over 1 plus x just gives you natural log of 1 plus x, but distribute the negative, and you get a natural log, a minus natural log of 1 plus x, and there you go. There you have it. Add c, and you're done. Okay, that's number 74. Okay, yep. Next one is number 75. It's a lot I've done in one session, but it's nothing compared to the scale of the entire worksheet. We have integral of, in the denominator we have x times the sine squared, times 1 plus sine squared of natural log of x, right? And then the numerator we just have a boring old 1. Now notice how, besides this, the only place where x appears is the natural log, and because this is a 1 over x, that's just the derivative of the natural log. So let's make a substitution, right? We would let u equal to the natural log of x, and then this would imply that our du would just be equal to 1 over x dx, right? Which earlier, as we mentioned, we have that right here. So let us put this down again and then rewrite it. 1 over x dx will just come at the very end with our du. So we're just left with, in our denominator, a 1 plus sine squared, and then ln x is just u. So it might look like it helped a lot, but take a look at this. It's not much better to do. So, how'd you do this? Dividing everyone by cosine squared. 1 over cosine squared, you just get secant squared, right? And then, of course, argument is u. This, once again, is dividing 1 by cosine squared, gives you secant squared, and then dividing sine squared by secant squared gives you tangent squared of u. Okay, and now notice how we have a secant squared u du in the numerator. You can almost make a u substitution, however, we have a secant squared u down here. So, when we write this in terms of tangent, and then we'll be able to make that substitution happen. So, down here, secant squared is just 1 plus tangent squared, right? So we have a 1, and then we have a plus. But because we have another tangent squared down here already, we just write this as 2 times tangent squared u, right? And then, of course, we still have our secant, I'm going to write this in black, secant squared u du multiplied in. Let's make a substitution. So we would let, and we already used u, so let's let t equal to this tangent guy in the bottom, right? And then differentiating both sides, we get dt is equal to secant squared u du. Right, so very simple. We just get integral of secant squared u du, so the top will just be 1 times du. In the bottom, we have the 1 stays and the 2 stays. However, tangent is now just t, and then it's squared. So, also, by the way, this is not du. My apologies. This is actually dt, since 1 times dt is equal to secant squared u du. So, okay. Now, you have something that looks kind of odd, but this is still in the form of sum of squares. All you need to do is just isolate the t squared in the second term, and you don't care what number goes here, since the square root of that is always just going to be your a if you're making a trig sub, but in this case, some squares in the denominator and a 1 on top. That's just inverse tangent, right? But let's just get rid of the 2 inside of this term. And to do that, we divide both the top and the bottom. Or no, instead we can factor out a 2 in the bottom. So how do we do that? Let's do this over here. This will give you the integral of factoring out a 2 in the denominator. You would need to divide both terms by 2 and then write it on the outside, right? So you have a 1/2 here. And then dividing 1 by... dividing 1 by 2, you just get 1/2. So this becomes 1 over 1/2 plus t squared dt. Yeah, and then there's not much else you can do with this, because if you were to simplify this, it would just go back to being that, right? So that's the whole reason why we have this. Now, remember, it's been a while since we used this, but so that's why I'm gonna write it down again. But remember the integral of 1 over a squared plus x squared dx is equal to 1 over a times the inverse tangent of x over a. In this case, our x is our t, and our a is just the square root of that. And we know that the square root of 1/2 is, you can just simplify it and it looks like that. So, as a result, and because this is already in that form, let's just write it using that like formula, I guess. So the 1/2, remember, it still stays outside. Now you have on the outside you have 1 over a. 1 over this fraction just gives you the reciprocal of this fraction, and that's just a root 2. Then you have the inverse tangent, and then you have your variable, which is just t, over a, which is once again dividing by this, which is just multiplying by its reciprocal. So it's, in fact, you have to multiply by the reciprocal here, which is just root 2. And then, of course, your variable still stays multiplied in. Almost done. Here, notice if you... Let's simplify it, not in like... well, okay, you know what? Let's deal with the argument of the inverse tangent first. So, notice that t is just tangent u, right? And then u is just natural log of x. So therefore, t, it would be equal to the tangent of u. U is our natural log, so instead of u, we write a natural log. Yeah. Okay, so on the outside, we have root 2 over 2 times the inverse tangent of root 2 times t, which is just the tangent of the natural log of x. There. And then add c, and you are done. That it looks weird, doesn't it? But, I mean, at the end of the day, it worked. So, that is it for number 75. Okay, number 76, we have an integral of the square root of 1 minus x over 1 plus x dx. It looks kind of intimidating to solve at first, so I would recommend breaking up the root and then multiplying a conjugate, right? So what you get is integral of breaking up the root. Notice that the top is just root of 1 minus x, bottom is root of 1 plus x. If you want to multiply in a conjugate into the bottom, you would multiply a root of 1 minus x, right? And that would end up getting you a square root of, 1 squared, which is just 1, and then minus x squared. My hands are kind of cold, so it's slow. But anyways, for the top, you multiplying in the conjugate, the square root of 1 minus x at the bottom is the same thing as squaring the top, since the top is already the root of 1 minus x. So the square root and the square cancel. And on the top, you're just left with the original expression without the root. Nice. Okay, and this should be pretty easy from now. You see, you can just break up the fraction. And what you get is 1 over root of 1 minus x squared dx. And then you want to subtract off integral of x over root of 1 minus x squared dx. Okay, so notice for this first one, you get a really nice answer immediately because this is standard. This is just inverse sine x, right? You could do this using a trig substitution where x is equal to sine theta, but I don't think that's necessary. This is pretty standard. This one, you just do u substitution where the inside is u because the top is very close to the derivative of the radicand. So we would let u equal to the inside, which is 1 minus x squared, and then taking the derivative of both the left and the right side to maintain equality, you get du is equal to negative 2x dx. And here we have a negative x, right? However, we don't have a 2, so we want to isolate the negative x dx. So we just divide 2 on both sides. So you get 1/2 du is equal to negative x dx. Okay, so from here, we can just replace the negative x dx with the positive 1/2 du. So I'm going to move the plus 1/2 to the outside. And then on the top, you're just left with the 1. On the bottom, you're left with root of u, yeah? And then, of course, du. Notice that if you were to just move the 2 to the inside, 1 over 2 root u is a very standard form. It just gives you root of u. So you end up getting root of u. And of course, u is just 1 minus x squared. And then, yeah, that's it. Plus c, and you're done with number 76. Okay. Alright, that's it for number 76. Next, we have number 77. Number 77 is integral of x to the x over natural log of x. May look non-elementary, however, it is. And we'll do some algebraic manipulations just to make it put it in a more usable form. Let's have an e as a base instead of a variable. So to do that, we make this x an e to the ln x, right? And then the exponent, we just multiply in an x over ln x, right? And then dx. Notice that this natural log of x right here cancels with this one. And all you're left with is actually just e to the x. Yeah. And here, integrating e to the x, you just get e to the x. Now, one thing to note is that here, because you have an x in the base, and also a natural log of x here, x can only be greater than 0, right? Because if it were 0, then you would get a 0 to the 0 case, which is undefined. And if it were below, then natural log wouldn't accept that either. So let's rewrite this in that form, because that's like more conformant to the domain that we have. But it's just a extra touch on top, right? Yeah, there we go. This is x to the x over ln x plus c, and you're done. Yeah, this one is pretty fun. All right. Number 78. We have integral of inverse sine of root x dx. I'm pretty sure we did inverse tangent of root x earlier. And this one isn't so much different. Let's make a u substitution where u is equal to root x first. So it gives us a nice argument to work with. Let u equal to root x taking the derivative on both sides gives you du is equal to 1 over 2 root x. Well, you know what? Let's solve for x by itself first. Because I think that makes it a lot more nicer to find the differential, right? U squared is equal to x. Then take the derivative of both sides, you immediately get 2u du is equal to dx, right? Really nice. And then just plug it in. So you have a 2u that's multiplicative, so I'm going to move the 2 outside. I'm going to put the u down first. And then here we have an inverse sine of u. Yeah. And yeah, we're now in the u world, so we'll put down the du. For this one, pretty easy, I'd say, integration by parts. You would need to differentiate the inverse sine and integrate the polynomial. And in fact, I'm going to drag the 2 inside because integrating 2u is actually cleaner than integrating normal u. 2u, okay. So we want to differentiate inverse sine. Right, and then, well, let's do this first. Differentiating inverse sine, you just get this. 1 over 1 minus, root of 1 minus x squared. And then integrating 2u, you get u squared. Yeah? Multiply the diagonals, and then integrate the row. Multiplying the diagonals, you get u squared times inverse sine of root u. Yeah? Sorry, not root u, just normal u. Inverse sine of normal u, yeah? And this isn't an x either. This is a u. We're in the u world right now. And then it's just this over that. Inside of an integral, of course. Okay, and what now? What do we do with this now? Well, we could do a trig substitution. I feel like that's the only proper course. I don't see anything right now. Maybe my brain is slow, but I don't see any better way to sort this one out right here. So, yeah. Yeah, let's just do a trig sub and see how it goes. So, we would let u equal to sine, right? Because 1 minus sine squared is cosine squared, and that cancels with the root. And then we want to find the differential. This implies that du is equal to cosine theta, d theta. Yeah. All right, so now, first of all, let's put this first term back into the x world since we're done integrating, right? So u squared right here we see is x. And then inverse sine, and then the u is just root x. So that's the first term sorted out. Second term, we have to implement the substitution. All right, the top, u is sine, and then it is squared. And then if you plug in a cosine into the bottom, well, sorry, no. We need a cosine multiplied in, yeah. All right, and then, of course, our d theta. Don't forget that we have a bottom root of 1 minus sine theta squared, right? 1 minus sine squared theta is just cosine squared theta, and then the cosine squared, the squared cancels with the radical right here, so you just get a cosine in the denominator, like that. And then this cosine cancels with that cosine, and then you're left with integral of sine squared theta d theta. Okay, and we're going to do this as we usually do. Let's rewrite this in terms of cosine 2 theta. Bring the 1/2 outside first. And on the inside, you have a 1 minus cosine of 2 theta. Yeah, and then finally, you're able to integrate this final bit right here. So, at least I'm pretty sure this is correct right now. Yeah, let's integrate. So this first term, of course, is still going to stay the same. Nothing's changing. And let's distribute the 1/2 as well. negative 1/2 times the integral of 1 in the theta world is just negative 1/2 theta. So we distribute the negative 1/2 and then we integrate the 1. Yeah. Distributing the negative and the negative cancels to make a positive. Drama. That's crazy. Anyways, cancels to make a positive. Well, yeah, and then integrating cosine 2 theta, you get 1/2 sine of 2 theta. And then don't forget that the 1/2, we haven't considered this yet. On the outside, we have to multiply it into the 1/2 that we got from integrating. We get a 1/4 sine 2 theta. Yeah? And of course, we're trying to get back to the u world first, right? And that means we have to have each of these trig functions having an argument of just simply theta, so we're able to apply the trig. So let's do that. Sine of 2 theta has an equivalent form, and that equivalent form is 2 sine theta cosine theta. And yeah, let's just do all the backward stuff in one step. So this becomes 2 sine theta cosine theta. The 2 and the 1/4, when you multiply them, it cancels to make a 1/2. Well, they multiply to make a 1/2. And then you get sine theta cos theta. Alright. So now let's go back to the u world. And then we'll go back to the x world after that. However, let's go to the u world first. We want to find what theta is equal to. And if you just take the inverse sine on both sides, you see that inverse sine of u is equal to theta. So let's keep going. X inverse sine of root x minus 1/2 and then sine u. Oh, sorry, inverse sine u. Okay, and then this final term right here, we just have to do the right triangle stuff. So here's a right triangle. Right, here's your angle theta. And then of course you see here that u is equal to sine theta. U over 1 is therefore also sine theta. And sine is opposite over hypotenuse, so u is opposite, 1 is hypotenuse, like this. Now to solve for that side, we just have to, this is just 1 minus u squared. Okay, and so for this last term right here, we can put down the 1/2. We know that we know what sine theta is equal to, it's just u. Then we just want cosine theta in terms of u, right? And cosine is adjacent over hypotenuse, so it's just this number. It's just this value right here. Root of 1 minus u squared. Alright, we're almost done. Now let's go straight back to the x world. And we see that this is already in terms of u, or u squared, so we can go straight back into the x world. First term stayed the same. No shit. And then the second term right here, inverse sine, and then our u is just root x. Right. Okay, and then the second term right here, 1/2. U is root x. And then we have this root of 1 minus. And then u squared, you see here, is normal x. Of course, feel free to multiply these two together. I personally feel like it looks better like this. Yeah, add c, and then you're done. Alright, that's number 78. Okay. Number 79, we have one more inverse trig question. And that is integral of inverse tangent x dx. Alright, this one, let's just use integration by parts. Because this is an inverse trig function, once again, we would differentiate inverse tangent And this would get us 1 over 1 plus x squared. And then integrating, you would just integrate 1, since inverse tangent has 1, it's just that. Integrating 1, you get x. Multiply diagonals, integrate rows. Okay. Multiplying the diagonals, you get x inverse tangent x. Okay, that's pretty simple. And the second term right here is just x over 1 plus x squared. Still with respect to x. Okay. Let's do a substitution, right? Because the top is very close to being the derivative of the bottom. Yeah. So we would let u equal to the bottom. And then differentiating, you get du is equal to 2x dx. Up here you have a x dx, you don't have the 2, so let's isolate the x dx. Dividing by 2 on both sides, you get 1/2 du is equal to x dx. Okay, so you just replace the x dx with 1/2 du and you're done with the substitution part. And then subtract off. Alright, first of all, 1/2 is multiplicative across the entire thing. I'm going to take that outside. And then x dx is just du, so I'm going to leave that on top. And then the bottom, 1 plus x squared is our u, so this is just du over u, which gives us natural log of u. Yeah. Notice that u is always positive, x squared plus 1, always positive. So we don't actually need to use absolute value. We can just use normal parentheses. So natural log of u, and u is always positive. So we use parentheses, then just write it in terms of x, like I just did here. And yeah, that's it. That's it for this one. That looks like an E. I'm gonna write that again, but better. Yeah, there we go. Number 79. Okay, yeah, that's it for this. Let's move on to number 80. Number 80 is an interesting one. We have something to break the monotony. Number 80 is an integral bounded, so you know this is about to be good. 0 to 5 of f of x dx. Right? And we have to define f of x to be able to actually compute this integral. And f of x is a piecewise function. So let's put this down over here. F of x is equal to, and there are two domains that it is defined on. First is x is less than or equal to 2. It is 10, right? Alright, and then second domain is x is greater than 2. And here is 3x squared minus 2. If x is greater than 2, yeah. Okay, so what do we do for a piecewise function? Well, we know that an integral from a to c, let's say, of f of x dx, right, is equal to integral of a to b f of x dx, and then add on integral of b to c, right, f of x dx. And if you don't know why this is the case, it's because, well, draw out a graph. If you just call this a, call this b, and then call this right here c, what you get is that if you find the area under this graph right here, if you go from a to c, right, like this first one, you go the entire way, right? It's just this entire area right here. And if you just do it from a to b, then you get the area on the left side of b, right? But then adding this area right here gets you the entire thing again. So it makes sense geometrically. It's like instead of doing the entire thing in one go, you first stop here and then you go again. And that applies right here too, right? And this is important to us because this is piecewise. And here there's a obvious place where we would need to make a separation because these are two different functions, right? So yeah, let's first go from 0 to 2, and then 2 to 5. So we go from 0 to 2. And then f of x from 0 to 2. Notice that it's just 10, right? Since this is always less than or equal to 2. So we just have 10. And then in the x world. Add. And then the remaining part, where x is greater than 2, right? We're going from 2 to 5, is just that function right there. 3x squared minus 2 dx. Alright, now we have a pretty simple integration case on our hands. From 0 to 2 of 10 dx, integrating 10, you just get 10 times x, of course. And then you have to plug in 0 to 2. And then we have to add on this right here. 3x squared, integrating 3x squared, you get x cubed. And then integrating negative 2, you get negative 2x. And then don't forget, this one, we have bounds. We're going from 2 to 5, yeah? Okay, for this one, notice that this is empty 0, right? It has no value. And then plug in a 2, and then you just get 20. First term gives you a 20. Alright, and then we add. Plug in a 5 first. So you get 5 cubed minus 2 times 5, right? And then you want to subtract off the second part, which is plugging in 2. 2 cubed minus 2 times 2. Close. Alright, and here, evaluate this. This is 125. Subtract off 10, you get 115. Alright, and then this right here, 2 cubed is obviously 8. Subtract off 2 times 2, which is 4. You just get 4 back. 115 minus 4 is equal to 111. And then you just combine these two guys back together. So basically, here, it doesn't matter what the graph looks like, right? This is A, this is B, this is C from A to B, which is from 0 to 2. This area we found is 20, right? Since we got that from doing this. And then from B to C, which is 2 to 5, we got that the area is 111 because that comes from this integral right here. Right, so if we know that this is 20 and this is 111, then adding them together is going to get you from A to C. Right. Okay. Finally, you get the answer is 131. Done. That's an ugly box. Okay, there we go. Alright, that's number 80. Alright. We're 80% done. We're 4/5 of the way there. Yeah. Next, number 81. Back to relatively normal integration. We have integral of sine of 1 over x cubed. If the inside of the sine was just normal x, I am sure that this would be non-elementary. However, it's a 1 over x, so let's just make a substitution, right? Since, yeah. Let u equal to 1 over x. Differentiating both sides, you get du is equal to negative 1 over x squared dx. Notice here, you have kind of, if you just split up the x cubed, right, you get an x squared times an x. So here you have an x squared. You don't have the negative, so let's just divide both sides by negative to get rid of it on the right-hand side. There you go. Alright, so let's plug it all in. First of all, this negative is multiplicative, move it outside. Second of all, notice that this x over here that we took out is actually 1 over x being multiplied into the rest. So that is actually one of our u's. sine, and then inside the sine we have 1 over x, which is a u, and then we have our dx, which is, well, that. We took care of the negative on the outside. Alright, and this is a very simple case of integration by parts. We just differentiate u, and then integrate sine. And, you know, I'm going to move this negative to the inside, right? So we can integrate negative sine. Integrating negative sine, you get cosine. Integrating cosine, you get sine. Multiply diagonals. There's no rows to integrate since this guy went to 0. So what you end up getting is, sorry, I don't know why I drew an integral, u cosine u. And then minus 1 times sine u, which is minus sine u. What is u? U is 1 over x. So here you get cosine of 1 over x, but then over x, right? Since u is just 1 over x, we can put the cosine of 1 over x in the numerator. Same idea here. We just plug in the 1 over x is equal to u. So you get sine of 1 over x. There we go. Add c and you're done. Alright. And that's it for number 81. Okay, number 82. Well, let me erase this first. I'm gonna turn the lights on and see how good the lighting is still. Okay, well, it looks fine, so. Number 82. Rational expression. This is gonna be fun. We have x minus 1 over x to the 4th minus 1. Just factor, well, notice that this is in the form, the bottom is in the form of x to the n minus 1. So that means you're able to factor out an x minus 1 and then have another polynomial being multiplied in. So let's factor the bottom first. The bottom, to factor out an x minus 1, the other factor just becomes x cubed plus x squared plus x plus 1. And you can factor by grouping this, but I'll show you in a second. First of all, this and that cancel out, so that makes it nice. And then, yeah, we have to factor by grouping the bottom. So, group these two and then group those two, right? Grouping those, the first two you can factor out an x squared, and then you get an x plus 1. Second group, you can just group the x plus 1. Sorry, it's red. Alright. And then, for both of these terms now, you can factor out an x plus 1. Alright, so you factor out an x plus 1 to the front, you're left with an x cubed plus 1. Alright, and then you're able to factor this, sorry, not an x cubed, an x squared. So we're not actually able to factor this anymore. That's what I thought. Though we have to do partial fraction decomposition, our good old friend. Let's just break it up then. PFD 1 over x plus 1 times x squared plus 1. And then we want the first one to be constant over linear, and then we want the second one, it's an irreducible quadratic, can't do much with that, so we just want it to be a linear over, a linear on top, since it's 1 degree less than the bottom. Okay, let's do this. We can do cover method if you like to. I'm going to multiply everything by the common denominator, so we can pull everything up into the numerator. If we multiply this first term by whatever's in the denominator here, the x plus 1 and the x plus 1 cancel, you're left with the x squared plus 1. And then the second term right here, bx plus c, we also multiply it by this. X squared plus 1, x squared plus 1 cancel, you're left with the x plus 1. Alright, and then from here on, you just expand it out. I'm going to start writing stuff in black. We just distribute the x squared, and then we get an a, and then distribute this. Bx times x is bx squared, bx times 1 is bx, c times x is cx, c times 1 is c. And then, almost done, group them by term degree. So, yeah, let's just, 1 is equal to, grouping the x squared terms, the coefficients of the x squared terms, you get a plus b all times x squared, right? And then these two right here represent your linear coefficients, so you get b plus c, x, and then finally you have your a and your c right here that represent your constant coefficients. Alright, and now I want you to notice, left hand side we don't have an x squared, we don't have an x either, however we do have a constant, and that is 1. So this and that have to match, and then this and that both have to be 0. Therefore, a plus b must equal to 0, b plus c must equal to 0, and then a plus c must equal to 1. This is yeah, let's just do some elimination. Let's do this bottom one minus the second one. A plus c minus b plus c. The c's cancel, you get an a minus b is equal to 1 minus 0, so I'm not going to write that down. Finally, add this and that, right? A plus b plus a minus b. The plus and the minus, they cancel, and you get 2a. 2a is equal to 0 plus 1, which is just 1. Therefore, a is equal to 1/2. That is a. And then you can just plug it in and solve for the rest, right? If a is equal to 1/2 here, 1/2 plus b is equal to 0. B has to be negative 1/2. And then finally, 1/2 plus c is equal to 1. Well, c must also equal to 1/2 then. There's your three three constants for the coefficients on top. So I'm going to write this to the right here. We broke this big fraction on the inside here up into this and that. I'm going to also split up the integral then. First integral has this first term only. So you have, and I'm going to move the 1/2 outside. And then on the inside, you just have 1 over x plus 1, right? Dx. Add on. The second one has a negative 1/2 and a positive 1/2. You can factor out a negative 1/2. So what I'm going to do, I'm going to write a negative 1/2 here. And then integral of, well, after factoring the negative, this is just an x, and this is just a minus 1. So the top is x minus 1. Okay, I hope that was clear, because we plugged it in and factor out a negative 1/2 all in the same step, but if you just distribute it back in, it makes sense, right? Okay. How do we do this? Well, first of all, you want to split up the fraction, the second integral. You want to split the integral right here. So you get, well, the first one you're already ready to integrate. All right, so I'm going to keep it like that for now, and then integrate all in one step because I find that relatively satisfying. Okay, and also remember to distribute the negative 1/2 among the two integrals too. First, you have the negative 1/2, and let's put down the negative 1 first. Negative times negative is positive, so you get a positive 1/2. And then integral of 1 over x squared plus 1 dx. All right, and the second one, you have to distribute it, is this x over x squared plus 1. Distribute in the negative 1/2. Well, it's still going to be a negative 1/2. And then an x over x squared plus 1 dx. All right. Pretty sure we've done this one multiple times before, but if you can, do the u substitution in your head. Let u equal to the bottom. The top, it would need to be 2x dx, so you have to divide by 1/2 on the outside, and then you get du over u. Right. So I'm going to write this all down again. Well, in fact, not even. Let's just do this all in one step. I'm getting kind of lazy. Remember we had to divide by 1/2 because we have an x squared here, but we don't have a 2x on the top. So multiply that on the outside, you get -1/4 integral of du over u. Do the u substitution in your head, right? Finally, we're ready to integrate all of these. First two are relatively easy. This one is natural log of the denominator. Second one is inverse tangent case. Then the third one is another natural log. So -1/4 du over u gives you natural log of u. Notice that u is just x squared plus 1. And it's always positive, so we just leave parentheses. And yeah, that's it. That's it for number 82. It's a rational expression. Most rational expressions go something like this, unless you can do long division. But if the top is of a lower degree than the bottom, then you're kind of stuck with factoring and trying to wiggle your way through. Okay, that's number 82. My board is getting kind of dirty. Okay, number 83 looks kind of weird. I'm going to move my little stool back over to the other side. But, I mean, let's give it a shot and see how it goes. Number 83. Integral of square root of 1 minus x, was it minus, 1 plus x minus 1 over 4x, this part squared, dx. It looks weird. Don't try to make a u substitution. The differential isn't going to treat you well. Let's expand this part out and see how it goes. So the 1 remains. Okay, expanding this. First square the first term, right? X squared. Then do 2 times this times that. So you want to minus. This times that just gives you 1 over 4. Multiply that by 2, you have 1/2. -1/2, right? And then finally, you just want to square the second term right here. You get positive 1 over 16x squared. Okay. And here we have like term, the constant term. So let's write it like this. X squared. And then 1 minus 1/2 is positive 1/2. And then plus 1 over 16x squared. And if you recognize this as a perfect square trinomial, that's the right word to describe it. This is a perfect square, 3 terms that can be condensed down into a binomial squared. Well, not even a binomial, just 3 terms that can be condensed down into 2 terms squared. Okay, and what we can do now is just rewrite it. So if you don't get it, it's just I'm pretty sure it's x plus 1 over 4x squared dx. Expand this out, feel free to expand it out, right? Notice that the second term squared is that. Multiply this 2 times this times that, you just get whatever's on the inside. So now we just cancel the root and the square. And then we get integral of x plus 1 over 4x dx. Alright. Home free now, because integrating x, we get 1/2 x squared, and then integrating the second term right here, move the 1/4 to the outside, integrating 1 over x, you get natural log of x. And then don't forget the absolute value, of course. And yeah, that's it. Pretty cool. It looks kind of weird from the beginning, but, don't overthink it. Just expand it out and then reduce it down. That's number 83. Okay. Number 84 is integral of e to the, what was it? Tangent? Yeah, e to the tangent x over 1 minus sine squared x. Immediately notice the bottom 1 minus sine squared x is cosine squared x. Right? So we can replace the bottom with the cosine squared. And also notice that the reciprocal of the cosine is just secant. So let's put that up in the numerator then. So cosine squared is, in the denominator, is a secant, but squared in the numerator, like this. Now let's just make a substitution. The argument of the exponential function is a tangent, and then this is the differential. Let u equal to tangent x, and then differentiating both sides, du is equal to secant squared x dx. Alright, and then, of course, e to the u, and then secant squared x dx is just your new du. Integrating e to the u just gives you e to the u, and then, of course, u is tangent, so you get e to the tangent x. Graphing this, I think it might look pretty cool. Anyways, yeah, but that's it. It might look something like that. Flat growth and then straight up. And then again and again and again. Add C and you're done. It seems kind of weird to see like, oh no, there's a trig function in the argument of the exponential function. You just don't come across that very often. So it might trip you up at first, but just think about it logically. Think about E as a function instead of just a number that you shove something in the exponent of. Okay. Number 84 done. Let's move on to number 85. Integral of inverse tangent x over x squared. How do you do this? Differentiating inverse tangent is really nice, and so is integrating 1 over x squared. So let's do integration by parts first. Differentiate the inverse tangent guy, and what you get is you get 1 over x squared plus 1. Integrating positive 1 over x squared gives you negative 1 over x. Integrate. Multiplying the diagonal gives you negative inverse tangent x over normal x. And you have to negative makes a positive, so you add integral of this and that combined. So you get 1 over x cubed plus x dx, because you distribute the x in the denominator into these two right here. And for this one, we can do the trick that we learned a while ago, actually, and we can factor out an x cubed and then move it up top. If you forgot, here's what it looks like. Factor out an x cubed from both. First term, you just end up with a 1. Second term, you end up with a x to the negative 2, right? And then the top still stays a 1. And the next step is to move this factored thing into the top. Like this. So there's now an x to the negative 3 in the top over a 1 plus x to the negative 2 dx. Alright, use substitution because the top is basically the derivative of the bottom. So we would let u equal to the bottom, right? 1 plus x to the negative 2. And then differentiating both sides, du is equal to reverse power rule, move this to the front, negative 2. And then, and then subtract 1, you get x to the negative 3 dx. Here we have x to the negative 3 dx. We don't have a negative 2. So we're going to divide both sides by negative 2. You get negative 1/2 du is equal to x to the negative 3 dx. Like that. And negative inverse tangent x over x. And then now we just implement the substitution. Negative 1/2 is multiplicative across the entire thing, so I'm going to move it outside. Now it becomes minus 1/2. And then the bottom is u, and the top is du, so you get du over u. And then integrating that, you get a natural log. So minus inverse tangent over x. and then subtract off a natural log of the absolute value of u. And u is just 1 plus x to the negative 2. There we go. And that's it for number 85. This is technically the final result. Although you can expand this middle guy out a little bit more, I guess. Well, yeah. Okay. Number 86. Number 86. Oh, the whiteboard is really, really dirty, but let's finish this off. We have inverse tangent on the top again, but this time on the bottom we have 1 plus x squared. And I'm telling you this is better, and here's why. 1 over 1 plus x squared, which is being multiplied with inverse tangent x. Well, 1 over 1 plus x squared dx is your differential if you let u equal to the top. So, yeah, let's give that a shot. Let u equal to inverse tangent, right? Because taking the derivative of both sides, you get 1 over 1 plus x squared dx is our differential du. So you have a u on the top, and then times du, right? Over 1 plus x squared dx, that's our du. So you end up getting is just the integral of u du, which is, of course, 1/2 u squared, and then u is inverse tangent, so, well, don't do this, right? Because that's not how the inverse exponent notation works. Let's just put it down as a square outside. I mean, this exponent convention, the notation convention, is very annoying to deal with. However, I mean, this result is somewhat satisfying, at least. And then add c. You're done with this one. Okay, that's it for number 86. A lot easier than you might think. Originally, the first time I tried doing it, I did the DI method, right? For integration by parts. And it worked. It took a few extra steps to condense it down to this, though. And I'm pretty sure this is so much easier. Alright. Next, we have number 87. Number 87 is integral of natural log of x squared. You can also write this as natural log squared of x, because that is technically that is valid notation as well, I guess. This one let's do integration by parts. We would differentiate the entire inside, because we don't know how. I mean, if we were to differentiate ln x and then integrate ln x, it might work, but you know what? I feel like this is more classy. Differentiating ln x squared and then integrate 1. So differentiating ln x squared, taking the 2 to the outside, and then now the exponent is 1. Multiply by the derivative of the inside, which is just 1 over x. So you get that. Integrating this, you get this. Multiply the diagonal, integrate the rows. And then, so you would get x times natural log squared of x minus the integral of, let's bring the 2 outside. Okay, and then this x and the x in the denominator, they cancel. So you're just left with the normal natural log of x on the inside, dx. We've done this before. Just do integration by parts. Differentiate natural log of x, you get 1 over x. Integrate 1, you get x. So you get x times ln squared x. Don't forget we have to multiply and then integrate. And we have this negative 2 on the outside bothering us, so negative 2. Let's distribute it into the 2 terms that we're going to create. So first term is x ln x. And the second term is negative, well, integral of -1. So we have to distribute the -2, and then integrate -1. So if we bring the negative sign outside, this becomes +2, and then we just integrate 1. And don't forget, we're still in the x world. And we are basically done at this point. X natural log squared x minus 2x natural log x plus 2 integral of dx is just x. Add c, and we are done. Yeah. Yeah, that looks right. Alright. The board is dirty. I think I'm gonna go clean it really quickly. Okay. Number 88, we got the integral of square root of x squared plus 4 over x squared dx. This one, don't overthink it. I think I would just recommend you to do a trig substitution. That's like the most obvious choice. So, here we would let x equal to, our a value is 2, right? And then since it's sum of squares, we use tangent theta. And then differentiating both sides, you get dx is equal to 2 secant squared theta d theta. So let's put this all down. Plugging in this 2 tangent theta into where x is, you just square the whole thing, so you get 4 tangent squared theta. And then you still add 4. On the bottom right here, you just square x, which is 4 tangent squared theta. And then you also multiply in your differential, which is 2 secant squared theta d theta. Okay, and then now what we can do is in the top, we're able to factor out a 4, and that lands us with the 2 outside, right? So we have a, well, let me write it this way. We have a 2 that we factored out, and then we have square root of tangent squared plus 1 now, which is square root of secant squared, which is just normal secant. So that's nice. And on the bottom, we still have our 4 tangent squared. And then notice that we have, well, yeah, you know what? I'm just going to put this down on the side. Sorry. I think this other crap should all be in black since we're not changing anything about it. Okay, so the bottom is 4 tangent squared. And then here we have 2 secant squared. Alright, and now notice that 2 times 2 is 4. 4 divided by 4 is 1, so these 3 cancel. So now on top, you can combine these 2, and you get a secant, but now it's cubed theta, and then the bottom you still have the tangent squared theta d theta. Now, it may look like you can do something with this, but I'm just going to tell you it's kind of hard. So what you can do now is write it in terms of sine and cosine to make your life much easier. And secant is 1 over cosine, right? However, if the secant's cubed, then the cosine's going to be cubed. In the bottom, you have tangent, which is sine over cosine. But same idea down here. If the tangent's cubed, then the sine is... Oh, sorry. If the tangent's squared, then the sine is squared. And the cosine is squared. And still with respect to theta. Now, this is a complex fraction. You want to get rid of it. And I think it's a better idea to draw in parentheses. Alright. But now, just multiply both the top and the bottom by cosine cubed, since that allows it to cancel in the top. So you're integrating. The top, you're just left with the 1, and the bottom, the cosine squared cancels, and you're still multiplying in 1 more cosine, so you get sine squared theta, and then you're left with 1 cosine theta, d theta. And yeah, okay. So now this is easier because remember what I said. If it's not easy to work with, just introduce more stuff to work with. In the top, let's use the Pythagorean identity. 1 is equal to sine squared plus cosine squared, yeah? And then, not just that, you're actually able to break this into 2 integrals. So we can do that in a second. Alright, take a look. And d theta, of course. Okay, and now, to break it into 2, the first one, sine squared over sine squared cosine. The sine squareds cancel out, you're just left with integral of 1 over cosine, which is integral of secant, right? 1 over cosine is secant. And the second term, cosine squared over cosine, well, think about it like this. One of the cosines on top cancels with the only cosine on the bottom. So you have cosine over sine squared. Now, let's split that up into sine over cosine. Cosine over sine times 1 over sine. Cosine over sine is cotangent, and then 1 over sine is cosecant. So this is really plus the integral of cosecant, cotangent, right? So that's nice. Here these are both standard forms, right? Integral of secant theta is natural log secant theta plus tangent theta. Right here, integral of that, you get a negative, so I'm going to change this to a negative. Cosecant theta. Yeah. What the hell? Cosecant theta. Alright, and now we want to get back to the x world, because that's where we started, right? So let's do this. X over 2 is equal to tangent theta. And then let's draw a right triangle using this statement right here. So our right triangle is going to look like this, because it is a right triangle, right? This is our angle theta. Tangent is opposite over adjacent. Opposite is x. Adjacent is 2. And this side is just going to be the square root of the sum of the squares of these. So a square root of x squared plus 2 squared, which is 4. So yeah, that's your right triangle. Now let's put it back in terms of x. First of all, notice that secant is hypotenuse over adjacent. Tangent is also is opposite over adjacent. So they both have adjacent in their denominator, so I'm going to combine the two and write this like this, right? Let's put down tangent first, since that's very easy. First of all, we can take a look at this, or we can use the right triangle. This tangent is just x over 2. And you're adding secant, so that's why this combining fractions works. And secant is this over that. We already have the 2 taken care of, so we just got to write the numerator down, which is root of x squared plus 4. Close the absolute value bar. And in fact, this is always positive. Feel free to take a look at the graph. But this is always positive. And also, if you think about what the plus 4 in the root does, then you might be able to figure it out. Okay, and next we have the cosecant. The cosecant is cosecant is hypotenuse over opposite. It's inverse of sine. It's the reciprocal of sine, sorry. So we have this over that. So I'm just going to write it as it says. And, it's subtraction. So we have root x squared plus 4 over x. And you're almost done. However, notice that this is natural log of a quotient, right? So that means we can do the natural log of the top minus the natural log of the bottom. And when you do minus the natural log of the bottom, notice that you're just subtracting ln2. ln2 is a constant, so you can put that in your plus c at the very end. So you can just ignore the divide by 2 in the bottom and just have this be natural log of x plus root of x squared plus 4. And then this is still minus root of x squared plus 4 over x. And then add c and you're done. Yeah, Very nice. Okay, that's number 88. All right, let's take a look at number 89. Number 89 has a similar form to this, but the way you solve it, I think, is completely different. It's not trig sub. That's a given, but let's take a look. Number 89 is integral of root of x plus 4 over x dx. Okay, for this one, what would we do for this one? Well, let's try making a substitution u is equal to the root, because that's always worked out nicely for us in the past, so I don't see why we shouldn't do it now. We would let u equal to the root of x plus 4. And then this way, du would be equal to, well, you know what? Let's use the classy way of finding our differential by squaring both sides. U squared is equal to x plus 4. U squared minus 4 is equal to x. And then now taking the derivative on both sides, you get 2u du is equal to dx. Alright, so now let's implement the substitution. Yeah, okay, so on top we just have a u. However, this 2u is du is multiplied in. So if you have a u times another u, you get a u squared. This 2 is multiplicative, let's bring it outside. On the bottom, however, and we have a du on the side, let's write that first. Well, okay, as I was saying, on the bottom, you have an x, right? And we solve for x. It's u squared minus 4, so let's put that down. Okay, and the next step is to simply, as we did before, subtract 4 from the top and then add 4 to the top. So you get integral of 2 times u squared minus 4 is just 1. And then remember we have the plus 4. So let's put down, a plus 4 over u squared minus 4 du. Okay, and then, in fact, let's distribute this 2 in. Because that way we don't need to deal with pesky constants that we need to distribute later. This becomes a 2, and that becomes an 8. Now for the second one, there is an inverse hyperbolic tangent property you can use. However, I think I'd rather just do a partial fraction decomposition, since when it comes to the inverse hyperbolic tangent and cotangent, they both have the same form, right? If you integrate 1 over 1 minus u squared du, this can either be, it can be f of u such that this is inverse hyperbolic tangent on some domain, right? And then inverse hyperbolic cotangent on some domain. Sorry, not x, u. And in this case, I'm pretty sure this is 1 is negative 1 is less than u is less than 1, and this one right here is u is less than negative 1 or u is greater than 1. So it depends on what interval you're working on. So I feel like the clearer way to state both of these is just to do partial fraction and then write it using the natural log. Yeah. So let's do that. All right. Partial fraction decomposition. So we want 8 over u squared minus 4 to be equal to, well, you can actually factor the bottom right here. 8 over u squared minus 4. This is equal to 8 over, the bottom factors into u minus 2 times u plus 2. Right? And, yeah, we can now set this equal to 2 different fractions. 8 over this, and then b over that. Let's do cover-up method. For this term, for the denominator here to be equal to 0, u has to be equal to 2. So we cover up this guy right here and then set u equal to 2. You get 8 over 4. That means a is equal to 2. B, same idea. U, however, now is -2 to be able to, and then we cover this up, and then we plug in -2 to U. We get -2 minus 2 is -4. 8 over -4 is -2. So B is -2. Alright, so now what we can do is rewrite this. So the first term stays the same. We didn't touch that. But we broke this fraction into two fractions. A, which is 2 over U minus 2. And then minus B, right? -2 is B over U plus 2. Finally, notice that the derivative of the bottom is the top for both of these. Actually, no. Treat the 2 as like a constant that you can move outside of the integral using the linearity of the integral. I'm not going to break up all the terms, but just think of it like that. What I'm getting is this is equal to integral of 2 in the U world is just 2U. 2U. And you know what? In fact, I'm going to replace U with our expression x plus 4, which is in terms of x, right? And then integral of this second term, you bring the 2 outside, take the natural log, and then absolute value of U minus 2, and U is just that. So absolute value of x plus 4, because that's our U, right? And then minus 2. And then finally we subtract 2 times the natural log of U plus 2, where U is root of x plus 4. And then, add 2. Okay. Now what you can do is you can combine these natural logs, yeah? You can combine these natural logs because they have the same coefficient. But this is subtracting, right? So the argument of this natural log goes in the denominator. And then you can rationalize, I'm pretty sure. But yeah, you're able to do that. I think I'm too lazy. But yeah, I'm pretty sure you can, this is like a standard form. Where you have the natural log of like x minus 1 over x plus 1, yeah. But yeah, this is a standard form. Add C and you're done. Okay, so that's number 89. Whew. Alright, next we have number 90, and this one I am recording a separate clip for, because when I recorded the 100 integrals thing, and I came across this, I realized that I don't actually know how to solve it, and here's the integral. It is the integral from 0 to pi over 2 of the bottom you have sine cubed plus cosine cubed. And then on top you have just the sine cubed. Would be much nicer, the functions, if you had a cosine on top. However, this works exactly the same. Now, I did a bit of thinking, and I figured out the way to solve this. The way to solve this, and the way most people don't get. No, you don't factor the bottom, right? You don't factor the bottom. Instead, what you do is you multiply a cosecant to the 5th power into everything. In other words, divide everything by sine to the 5th. And here's why this works, okay? So 0 to pi over 2, and the top, after dividing by sine to the 5th, you just get 1 over sine squared. Yeah? The bottom, dividing sine cubed by sine to the fifth, you also get 1 over sine squared. And then dividing cosine cubed by sine to the fifth. Well, I'm going to split this up into cosine cubed over sine cubed, right, times 1 over sine squared. And this is significant because let's convert all of these into their cotangent, cosecant counterparts. 1 over sine is just cosecant, right? And then, well, let's do this one first. Cosecant, and don't forget that it is squared. And then the second one, we have cosine over sine is cotangent, and don't forget it is cubed. So we have cotangent cubed. And the last one, you just multiply in another cosecant squared. And then the top is also a cosecant squared, right? Okay, and now this is very significant because you can make a substitution. Notice how the top is cosecant squared x dx, and that is almost the derivative of cotangent. At the bottom, you may think, oh, you have cosecants. No. What you can do is you can change the cosecants into 1 plus cotangent squares. So let's do that, and then let's make a substitution. You go from 0 to pi over 2. On the bottom, you have, I'm going to change it to 1 plus cotangent squared x, and then plus the cotangent cubed stays. And then you have 1 plus cotangent squared x once again. And in the top, we're going to keep it cosecant x dx. Okay, and now you can make the substitution, u is equal to cotangent, right? And in fact, we don't even need to remember this for the future because we have bounds, right? So we can just work with bounds in the u world. Let u equal to cotangent. Differentiating both sides, you get du is equal to negative cosecant squared, right? So we have the cosecant squared x dx. We don't have the negative, so let's move the negative to the other side. Negative du is equal to cosecant squared x dx. So what you end up getting is a negative on the outside first, and then from here you have to evaluate the bounds and then put them into the u world. So these are in terms of x. We want them in terms of u, so let's plug it in here, right? Cotangent of 0 is actually undefined. So let's do the pi over 2 first. Cotangent of pi over 2, if you'd like a reminder, it is just cosine of pi over 2 over sine of pi over 2. And then, of course, this is cosine of pi over 2 is 0, sine of pi over 2 is 1. Therefore, this is just 0. The top bound is 0. What about the bottom bound, though? Because this is improper, right? Plug in 0 into cotangent. No, it's not going to work. Plug in 2 into, So the way we do this is a limit, I guess. But we're not going to do this too formally because it's easy to think about. Now, let's write it again as cosine of something over sine of something, right? So we can plug in zeros to both of these. And the top, this would give us just a 1. Cosine of 0 is 1. The bottom, however, is going to give you 0. Right? So, yeah. How do you deal with this? Well, recognize that on a graph, and I'm going to explain this a little bit more. If we're going from 0 to, say, pi over 2, then this 0 right here, we're kind of starting from 0 plus, because we're going to be only moving right. So we're taking an integral from the right side, if you kind of get what I mean, because we're never going to be taking it from the left side. We're going to be taking a limit from the right side because we're integrating this area right here. Nothing to the left has to do with what we're doing. So, in fact, we can write down a sine of 0 plus since, the right side, positive side. And if you look at the sine graph, which is what I drew out right here, if you approach a 0 from the right side, Yeah, well, if the x value right here approaches 0 from the right side, the y value also approaches 0 from the positive side, right? Right side means positive side, meaning out here, this is also 0 plus. And 1 over 0 plus, if you take a look at the graph of 1 over x, 0 plus is this side, right? Because it's going from the right and all the way up to infinity. And this distinction matters, plus or minus matters, because if you go from the other way, you're going to hit negative infinity. So that's very, very important. So this approaches infinity. So the lower bound is actually infinity. Okay, and then we just have 1 plus cotangent squared. Of course, cotangent is u. And then the u squared. Right, and then plus cotangent cubed. Well, and then, cotangent is u, yeah. So you have u cubed. Oh, that's not. And then you have 1 plus u squared. Why is this thing dying? That's so hilarious. Okay, and then we have just a negative, and then a negative du. So we can write this as negative 1 times du. This is our new integral. And then now all we can do, this is a rational expression, factor the bottom, yeah? And then we can do partial fractions, since that's typically what we do when we have a polynomial on the bottom. One more thing is notice how this right here, you can use the negative to interchange the bounds. So let's go from 0 to infinity instead of infinity to 0, because it makes more sense that way. All right, and then let's factor the bottom. Factor out 1 plus u squared. So you're left with a 1 plus u cubed, and then we factored out the 1 plus u squared. And then we still have the 1 in the du, and then finally, we have, this is sum of cubes, right? So you're able to factor it more. It factors into u plus 1 times u squared minus u plus 1. Last guy right here, we can just switch the order of addition, no problems, and make it u squared plus 1. And this is because we're going to be doing a partial fraction decomposition. Okay, so that's most of the work done with the trig stuff and the substitution. Now let's work on the partial fraction. So let's get rid of all of this to make room for our work when it comes to the partial fractions. Okay, so for the partial fractions, 3 factors. So you want to break it into 3 different fractions. You have 1 over 1, x plus 1. Sorry, no, not x. We're going to be using u. Can't forget that. Cannot forget u. U plus 1. And then u squared plus 1. And then u squared minus u plus 1. Alright, and then we want this to be equal to a over your first factor right here is u plus 1. Add on. Then the rest of these guys are just irreducible quadratics, so the top is going to be linear instead of constant. And then u squared plus 1. And then finally, we have du plus e over u squared minus u plus 1. And now we got to find what all of these equal. I'm not going to do any cover-up. I'm going to do this completely formally. It might be kind of tough to do it, but actually I'm doubting myself. Should I do cover-up? You know what? I think I should. Just for the sake, because there's 5 variables, and I don't want to deal with this system of 5 equations. For the denominator here to be 0, we want to set u to be equal to -1. So, therefore, a would be equal to 1 over, cover this up, plug in -1. So, this would give you -1 squared plus 1, and then here you have -1 squared minus negative 1 plus 1. Alright, and this first factor right here, negative 1 squared, is just 1. 1 plus 1 is 2. And then the second factor right here, negative 1 squared is 1, negative 1 is 1, plus 1 is 1, 1 plus 1 plus 1, 3. Therefore, A is equal to 1/6. So that is our first answer. And I'm going to put it up in this corner right here for us to refer to it. A is equal to 1/6. Alright, and that's it for A. I'm going to erase this because, well, actually, you know what? I think it should be okay. Okay, what we're going to do now is we're going to multiply the least common denominator on both sides and hope everything works out for us. Left side, you're just left with a 1. And then here is equal to, the A remains, but sorry, not the A. We can actually replace this with the 1/6. That's the whole point, to make it such that we don't need to find another variable. U plus 1 cancels to U plus 1. You just have these two quadratics left. U squared plus 1 times U squared minus U plus 1. Right here, the numerator stays. BU plus C, right? And then the U squared plus 1 cancels the U squared plus 1. You're left with U plus 1 times U squared minus U plus 1. And this earlier is actually the factored version of the sum of cubes that we arrived to earlier. U cubed plus 1. And then our final term right here, the du plus e on top stays. Then the u squared minus u plus 1 cancel the u squared minus u plus 1. You're left with this times that. And in fact, let's just yeah, you know what? Let's just put it down as it is. U squared plus 1, and then u plus 1. Well, said it in the wrong order, but anyways, next, let's expand them out. Okay, so expanding this polynomial out, u squared times u squared is u to the 4th. U squared times negative u is negative u to the 3rd. U squared times 1 is u squared. 1 times u squared is u squared. 1 times negative u is negative u, and 1 times 1 is 1. So yeah, first one, pretty simple. Second term, also really simple, because so bu times u cubed is bu to the 4th. C times u cubed is cu cubed. Bu times 1 is just bu, and then c times 1 is just c. So that's the second term. And then the last one, the du plus e, let's just keep that there for now, because we want to expand out this one right here. U times u squared is u cubed. Well, actually, u squared times u, and then u squared times 1 is u squared. Now let's move on to multiplying this. Well, not multiplying the 1, sorry. 1 times u is u, 1 times 1 is 1. Like that. And then expand it out one last step. Just distribute the 1/6. I'm going to do all this in black. However, note that there's 2 u squares, so this is 2u squared. 1/6 times 2 is 1/3. So I'm going to actually write this down as 1/3 u squared. But it doesn't change anything. And then the parentheses aren't necessary here anymore, so I'm just going to get rid of them. Well, they weren't necessary in the prior step, however, yeah. This is actually going to be h terms, I think. So we can take up 2 lines if we need to. Du times u cubed is du to the 4th. Du times u squared is du cubed, and etc. This is just going to be d and then u in descending order. And then same thing. E times this, e times that, e times... Yeah, you know. You get the point. Plus eu cubed plus eu squared plus eu plus e. I tried to fit all of this in one line. You can tell I ran out of space. Now let's group these by their coefficient. Oh, no. Group them by their term degree. For the fourth degrees, we have the 1/6 right here. We have the plus b right here. And we have a plus d. And I think that's it. And close that. Put down a u to the 4th. Plus. Okay, for the u cubes, we have a negative 1/6. We have a plus c. we have a plus D, and then we have a plus E. Oh, I need to cross this out. All right, and then now we have the quadratics. We have the plus 1/3. So we have the 1/3. Cross this out. D. Cross this out. Then the E. Cross that out. Next, we have the linears, almost done. -1/6. Actually, I'm going to write this down first. All right. Anyways, linears, -1/6. Cross that out. B. Cross that out. D, and then E. U. And then I'm going to cross this and that out. And then you're left with 3 constants, 1/6. All right, cross this out. 1 C and then a D. Oh, sorry, not D, E. Once again, I've run out of room, but I'm able to make it fit. Okay. Notice that on the left-hand side, you only have a 1. You don't have any of the higher degree terms, right? You have that means these all have to be equal to 0 since they don't exist on the left-hand side, and they have to be equal. And on the right-hand side, the only thing that does exist is a constant, meaning this has to equal 1. So let's set up a system of equations. And how do I want to do this? Let's just have this must equal to 0. So therefore, B plus D, if you just move the 1/6 over, you get B plus D is equal to -1/6. And then how should I do this? Maybe I should put it here. I'm gonna do this one next for a reason you'll see later. And this also equals 0. So I'm going to move the 1/6 over as well. Therefore, B plus D plus E must equal to positive 1/6 now. All right, and then you have this and that, which I'm going to also put to use together. 1/6 plus C plus E must equal to 1, right? So therefore, C plus E, there's a 1 on the other side. If you subtract 1/6 on both sides, then you get 5/6. Okay, and then finally we have, what was I thinking? This one right here. And this one is also equal to 0, so we can move the 1/6 over. C plus D plus E is equal to positive 1/6. And in fact, I'm pretty sure this is all you need, and we'll work with this. Notice that there's a B, D here, B, D here. Therefore, -1, we can replace BD with -1/6. Therefore, BD -1/6. Still a plus E. This is equal to 1/6. Add 1/6 on both sides, you get E is equal to 1/3. So that is the second value we've obtained. Same idea here. There's a C and an E. There's a C and an E, and that's equal to 5/6. Therefore, we can replace this C plus E with a 5/6. So we have a D, and then we have to add 5/6. And remember, this is equal to 1/6. Therefore, when you subtract 5/6 on both sides, it might be kind of difficult to do in your head, but it is just -2/3. And yeah, so that's why this is completely unnecessary, because if you put down this is equal to 0, then you can just plug this into check, right? 1/3 plus 1/3 minus 2/3 is equal to 0 indeed. So these two are valid. We're not going to be using this, however, we're going to be plugging it into this. B plus D, well, we can substitute -2/3 into D. And then this is now -1/6. And therefore, B is equal to, if you just add 2/3 on both sides, you get B is equal to 1/2. And then C, very similar story. You get, plug in an E, a 1/3 into where E is here. So you get C plus 1/3 is equal to 5/6. And subtract 1/3 on both sides, you get C is equal to, this is taking, okay, just 1/2. Okay, so you've actually found all 4 of your other variables, right? So yeah, let's put them down up here and then erase this because we're going to be putting down another equation and then we're going to be finally solving. Okay, so b is equal to 1/2, so is c. D is equal to negative 2/3. And then E, I'm just going to tell you, maybe you can see, maybe you can't, I have no idea, is equal to 1/3. Okay? So that's our partial fraction decomposition work. We can get rid of this now and then go back to this step because we have this down here to refer back to. What's the whole reason why we're doing all this algebra? Well, it's because we're trying to break this up, right? And if the insides, this and that are the same, therefore this and that are also going to be the same, we can just place this guy into our integral instead. Alright, so therefore, this is going to be equal to integral from 0 to infinity of that. And because this is a bound integral, I don't want to write the bounds again and again. And plus, at the very end, we're going to be addressing this as one massive equation, right? So, no point in breaking it up. Let's just keep it as it is. A is 1/6. I'm going to move the 1/6 to the side of the fraction, so it looks nicer. Next up, B and C are both 1/2, so let's factor that out. And you know what? In fact, what you're able to do is break up the fraction first. So let's look at the BU over U squared plus 1 part first. You get 1/2 times, well, yeah, 1/2 is the B, and then on top you just have a U over U squared plus 1, right? And then don't forget you have another term, C over U squared plus 1, which is actually going to be more important than it looks, just a little random variable, right? No, it isn't. Anyways, before we get too far ahead, C is equal to 1/2. And then this is times 1 over U squared plus 1. Add, finally, that. Now, this one is not that hard to think about. D, negative 2/3. E is 1/3. You can actually factor a negative 1/3 outside. So we can make this a negative. Have 1/3 be staying out here. And then on the inside, we have, if you factor a negative 1/3 out of D, you just remain with 2. And then factor a negative 1/3 out of this, you just get negative 1. U squared minus U plus 1. Close du. Okay, and what you may notice now is that you're able to integrate all of these. This, the top is already the derivative of the bottom. This, almost. And what we can do here to make it more obvious is multiply 2 on the top and the bottom. So on the bottom, 2 times 2 makes a 4. Okay, and then here, inverse tangent, of course. And then here, the top is the derivative of the bottom. And then this is also natural log. All right, natural log, inverse tangent, natural log. Okay, here we go. This is the fun part. Let's put down a bracket because these bounds still exist. And it looks really intimidating. However, I'll show you how to get rid of that. You know, it's pretty cool. This one, 1/6. Yeah, and then natural log of U plus 1. And I'm not going to put down absolute value because U, notice that we're going from 0 to infinity. That's always going to be positive if you add 1, right? So it's not necessary for us to put down the absolute value bars. Next one, we have the 1/4 stays on the outside, and this one, the 1/6, should actually be in black. And then in here, the top is the derivative of the bottom, so we just get natural log of the bottom. And of course, the bottom is always positive, so I'm also going to put down the parentheses. Middle one is inverse tangent. We'll do that later. And then this one first, because I want to group all the natural logs and then have our inverse tangent at the end. Negative 1/3. And then the top is the derivative of the bottom, so we just have the natural log of the bottom. And of course, the bottom right here, if you check the discriminant, the quadratic discriminant, it is always positive, meaning parentheses. Lastly, right here, integrating U squared plus 1. Don't forget the 1/2 though, right? Integrating U squared plus 1, you just get inverse tangent of U. Finally, we were able to close the bracket and put the bounds in. Want to make an observation before we actually start plugging in bounds. putting in an infinity. This is finite, like inverse tangent. It has a horizontal asymptote towards infinity and negative infinity. So this we can worry about later. However, putting an infinity into here, you get negative infinity, right? Putting infinity into here, you get positive infinity, infinity plus infinity minus infinity. It doesn't mean anything because you have a negative infinity, and that's indeterminate form. So you can't do much with that yet. I'll show you what to do with it later. But now, let's deal with the 0. Because if you plug in 0 here, you get natural log of 1. That's 0. This term is now 0. Same idea here. Plug in a 0, you get natural log of 1. This is 0. Plug in 0 here, natural log of 1. This is now 0 too. Plug in 0 here, inverse tangent of 0 is also 0. This is actually an empty 0. And finally, how the hell do we deal with infinity? Well, notice that it approaches infinity inside of all three of these natural logs. And the fact that they're natural logs are important because maybe we can find some way to combine them so it's easier to deal with, right? Into just one log, so we can move the limit inside and treat it as a rational expression. Now, to be able to combine these, you need a coefficient on the outside that's the same. Like the positive or negative doesn't matter. That matters in where like your argument goes inside of the combined log. However, right now we're just dealing with 1/6, 1/4, 1/3, and to get a common denominator out of that, that's just 1/12. So we just want 12 in the denominator. So I'm gonna keep the brackets here since technically just putting an infinity there, I'm pretty sure that is notation you can use. It's kind of scuffed, but 1/6 is 2/12. However, I'm going to write this as 1/12, and because I'm going to take the 2 and bring it up top, right? Because we want this all to be 1/12, and the only way you can get rid of that 2 is you can't factor it out. You just bring it up to the top. ln of u plus 1, but now there's a 2 up here, so that's where the 2 goes, all right? And then same idea for all the other ones. Plus 1/4 is just 3/12. I'm going to bring the 3 up top. Right. 3, right, like that. And then finally here, minus, and then 1/3 is equal to 4/12. However, I'm going to bring the 4 up top as well. Yeah? And then finally have this inverse tangent, innocent little inverse tangent, completely finite, causing no trouble whatsoever, but we're going to just keep him here for now. Okay, let's combine these logs. Because, alright, now notice this term is positive, this is positive, and this is negative, meaning u squared plus u plus 1 squared and u squared plus 1 cubed goes in the numerator, and then u squared minus u plus 1 all to the 4th power goes in the denominator because there's a negative sign there. Once again, there's the 1/12. We did this so that we can combine the logs, so the 1/12 stays outside, right? And then the logs we all combine. So here we go. On the top, we have a u plus 1 squared. And then we also have the u squared plus 1 cubed. In the bottom, because this is negative, then we have the inside of that log, which is u squared minus u plus 1 to the 4th. Okay. And then finally, we have our little friend, inverse tangent again. I love this guy. Alright, and then infinity. Yeah. Okay. We can take a limit now, but it's easier than you think it might be. Because when we evaluate a limit as it approaches infinity of a rational expression, we're looking for the dominating part of the rational expression, right? So natural log is continuous, we can bring the limit to the inside, and the limit as u approaches infinity of this guy is now what we're trying to evaluate. So basically what we're doing is we're finding the leading coefficient and the degree of the top, and the leading coefficient and the degree of the bottom. So the leading coefficient, as you can tell, is both 1. However, the degree on top, well, let's just do this u squared, right? And then times u squared cubed. U squared cubed is u to the 6th. U squared times u to the 6th is u to the 8th. So the top is, well, u to the 8th. I'm going to move this. move this guy out a little bit. And then the bottom, u squared to the fourth, is also u to the a. So notice how they're the same power, u to the a over u to the a. As they both approach infinity, this guy approaches 1. That means this guy approaches 1, right? So it's... Well, let me write this down before we keep talking about this, because this is also... Well, this is the most important part of the entire thing. Inside approaches 1. This thing, this part right here, it just approaches 1, believe it or not. So, well, I'm going to now plug in the bound, because we know that we evaluated it already. It just approaches 1. As u approaches infinity, which is what we're plugging in. That means, and then, well, let's do this guy right here. Plus 1/2 inverse tangent of infinity. I'm just going to do that, Don't, just, I don't care. I don't care if it's not formal. Natural log of 1 is 0. This term is now 0. Yeah. So all we're left with is 1/2 of the inverse tangent of infinity. Inverse tangent of infinity, well, the horizontal asymptote, as x approaches infinity, y approaches pi over 2, right? So this is, the 1/2 stays, and then inverse tangent of infinity is pi over 2. Top and the top multiply, bottom and the bottom multiply. So what you get is this, all in all, is pi over 4. Beautiful. That's pi over 4. And in fact, you can use a similar technique where you, no matter, as long as this, and that are all the same, then you can use the exact same technique. You just need to divide by sine to the n plus 2 power, so that you're left with a cosecant squared on top, and the bottom, regardless, you're going to be able to manipulate it to make a substitution. So that's the trick. It's just that you just have to know that all the time this is actually going to evaluate to pi over 4. Pi over 4. So yeah, that's it. It's pi over 4. It's really nice. Also, one more thing to keep in mind about what I just said. 0 to pi over 2, the bounds need to be from 0 to pi over 2. I'm going to box this one more time because of how nice it is. Look at that. Okay, and that's it for number 90. I came up with a solution entirely by myself. So, yeah, I'm proud of this, honestly. I'm pretty proud. Yeah. Okay, that's it for number 90. All right, number 91, we've got integral of x over 1 plus x to the 4th. What can we do here? Factor the bottom, factor into like irreducible quadratic and then 2 linears. Yeah, let's try that. No, don't do that. Instead, what you can do is notice that if you want to make a substitution, and your top is your derivative, right, x dx, then you want x squared to be what you substitute. And this is completely possible. You just break up this x to the 4th into an x squared. And then now you can make your substitution. Let u equal to x squared, right? And then du would be equal to 2x dx. You have an x dx here, no 2. 1/2 du is therefore equal to x dx. 1/2 is multiplicative across everything, so you bring the 1/2 outside. And then integral of x dx is now just a du, so I'm going to put a du on top, and you get 1 plus x squared is u. Don't forget that it is squared on the outside, however. This is a standard form. This is just inverse tangent of u. So 1/2 times inverse tangent of u, where u is equal to x squared. So final answer, 1/2 times inverse tangent of x squared. That's it. Add C, you're done. That's number 91. Okay. We have like, what? Not much left. Let's do number 92. Number 92 is a little quirky looking, but it is integral of e to the root x. Let's make a substitution where the argument of the exponential function is our new variable. Square both sides, right, and then take the derivative, 2u, yeah, that's failed. 2u du is equal to dx. Okay, and then what you get is 2 is multiplicative, so across the entire thing. I'm not going to bring it outside though. Let's just put down 2u first, right? And then put down our original integrand, e to the root x, however root x is u. And then our du, can't forget the du. Okay, and then now we can do integration by parts. 2u is a monomial or a polynomial, so you have to differentiate it. And it's easy to integrate e to the u. So, differentiating 2u, you get 2. Do that again, it's 0. Integrating e to the u, you get e to the u, and then e to the u again. Multiply diagonals. No rows to integrate since it reached 0. So, 2u e to the u, however, right, 2u e to the u, however, u is root x. E to the root x. Subtract off 2 times e to the u, which is root x. Add c, and you are done. That's number 92. My black pen is running out. I'm gonna stick with it for like maybe 2 more questions. Well, not 2 more. I feel like I can do much more. We'll see. All right, we have number 93 is the integral of 1 over cosecant cubed x dx. Reciprocal of cosecant is sine, so this is really just sine x dx. And well, don't forget the cubed, right? Integral of sine cubed x. And of course, might look kind of weird. Is there an identity we can use? No, don't do that. Instead, what we can do is simply break it up into a part that's in terms of cosine and then 1 sine left for our substitution. So, we can make a sine squared of 1 minus cosine squared. And that means you're left with 1 more sine, right? However, now you're able to make a substitution, u equals the cosine, and then, well, yeah, and then you're able to use that as your differential. Let u equal to cosine. Du would therefore be negative sine x dx. And we have a sine x dx, no negative. But what we can do is we can multiply in a negative on the outside, right? Multiplying another negative on the inside. But what we can use that negative for is to switch the order of subtraction right here. So this now becomes cosine squared x minus 1. Okay, so we're now ready to go. The negative stays outside. The cosine becomes a u. Don't forget it is squared, and then minus 1. Sine x dx is now our du. And maybe it's a better idea if I move that negative on the inside right here, like so. Negative sine x dx, like this. So now you can see that's our du. Alright, and then now, finally, and there's no more negative here, right, because I brought it inside to use in the differential, so we're just integrating this, Integral of 1 of u squared is 1/3 u cubed. U is cosine, so 1/3 cosine cubed x. Subtract. Integral of 1 in the u world is just u, and u is cosine, so we just subtract off cosine. Add c, and we're done with number 93. Okay. All right. So, number 93, that's it. Number 94. Integral of inverse sine x over root of 1 minus x squared dx. Similar to earlier when we did the thing where we had inverse tangent over 1 plus x squared. This is u, inverse sine, we could set as u, and then our du would just be the derivative of inverse sine, which is right here. It's 1 over root of 1 minus x squared dx. So, therefore, we can make u substitution. We would let u equal to inverse sine, and then du would just be what we have left, 1 over root of 1 minus x squared dx. So therefore, this would be equal to, I'm going to place inverse sine with u, right? And then the 1 over root of 1 minus x squared dx is just simply du, so like that. And then, almost done. Well, we can just integrate straight away, so integral of u in the u world is 1/2 u squared. Well, I'm going to color code this the way I typically do. 1/2 u squared. And then finally, we would like to replace u with its counterpart in the x world, which is just inverse sine. Square it and we're done. Add c. Yeah, so that's pretty cool. Need to check everything is still recording, and it is, so. Alright. Next. 95, almost done. We have integral of root of 1 plus sine of 2x. And it looks pretty intimidating at first, but let's try some things. Let's expand out this, to make it such that an argument is easier to work with. And what I wouldn't do is make a u substitution, because you can't really, it's really difficult to do root of 1 plus sine x, right? Think about it. How would you approach that? So instead, let's expand this out. We have integral of 1 plus sine of 2x is just 2 sine x cosine x. Multiplying to dx. Alright, now notice how this kind of looks like the middle term in the case of a binomial squared. Or in this case, it would look like sine x plus cosine x squared, right? This looks like the middle term. What are we missing? We're missing a sine squared and a cosine squared. Sine squared plus cosine squared is 1, so we can turn this 1 into a sine squared plus cosine squared. So let's do that. 1 is sine squared x, and then we have the middle term. And then plus cosine squared x. And that's the root, and that's our differential. Now, we can rewrite this as something squared. Sine x times cosine x squared. Not times cosine. We do plus cosine. Yeah. And then finally, that cancel. You're left with integral of sine x plus cosine x, which we've all done before, I hope, because integral of cosine x is simply equal to sine x, and then integral of sine x is just negative cosine x. That's your final answer. Add c. Alright, that's number 95. Okay, number 96, we've got another integral of fourth root of x dx. I'm going to rewrite this real quickly since everyone should know how to do this at this point. This is just reverse power rule. So we're going to write this using exponent notation. Adding 1 to the power, you get 5 over 4, right? So you get something x to the 5 over 4. However, you need to divide by the new power, so you multiply by the reciprocal, 4 over 5. And then finally, we are presented to it using this radical form, so I'm going to rewrite it using the radical form. The 4 in the denominator of the exponent means this is a fourth root, and then x is to the 5th power. Yeah? Add c, and we're done. That's number 96. Okay. Number 97. We have integral of 1 over 1 plus e to the x dx. Okay. Now, what we can do, what most people first instinct would be to do is to make the substitution u is equal to e to the x, since that would make your differential e to the x, which also is just u, right? And that's a really nice expression in terms of u. Either way, the rest of the problem is still going to be worked out the exact same way. So whether you add e to the x and then subtract e to the x and then make the substitution. In fact, let's give that a shot. I'm not sure how that would work out, actually. So integrate 1 plus e to the x is just 1. And then we still have a minus e to the x over 1 plus e to the x. So 1, and then minus e to the x on top over 1 plus e to the x on the bottom. Is this how this works? I'm not completely sure. Let u equal to the bottom. Well, let's integrate the 1 first in the x world. Just get x, right? Alright, for this one, we would let, since notice at the top is just the derivative of the bottom. So we would let u equal to 1 plus e to the x. Du would therefore be e to the x dx, which you notice you have right here. So then, this is really just x minus integral of e to the x dx is just your du. 1 plus e to the x, which is the bottom, is our u. So this gives us x minus natural log, right, of u. U is 1 plus e to the x, so I'll write that back in. There we go. And in fact, you don't need the absolute value bar, since 1 plus e to the x is always positive. E to the x is always positive. Adding 1 to it is still going to be always positive. Add c and we are done. Very cool. Other way to do this would have been, well, as I mentioned earlier, setting u to be e to the x, and then your differential dx would become du over u, right? So you get 1 over 1 plus u times u, all in the denominator. And you would have needed to do, yeah, there's a variety of ways to do that. Most people would turn to partial fraction decomposition. There's another shortcut you can use, but I'm telling you by far this is the easiest way to do it, yeah? Okay, so that's 1 plus e to the x in the denominator. What if we put 1 plus e to the x in a radical? So this is number 98. Integral of radical 1 plus e to the x. Okay, now the strategy is completely different. Let's just make a substitution where it's the entire radical, right? Since, firstly, typically in the past, whenever we've made a substitution, u equals to a radical with something linear on the inside, it's always been nice. And even if this isn't linear, this is actually geometric. This it's e to the x, which also has a nice differential, so it might work out pretty well for us. And plus, you're able to just isolate x if you let u equal to this thing. So it's going to be a nice differential to work with. Let x equal to, let u equal to 1 plus e to the x. Isolating x, you have to square both sides first. Subtract 1 on both sides. And then take the natural log. Sorry, no, not e to the x. Natural log is equal to x, right? Now you take the derivative on both sides. Remember, as a reminder, derivative of a natural log is just 1 over the argument is in the denominator. Take the derivative of the argument, the inside, and then multiply it in, so you get 2u. Don't forget you have a du, and then on the right side, dx. Alright, so this is integral of, notice that this 2 is multiplicative, right? Since this is your new differential, you're multiplying it in. So let's move the 2 outside. This is a u, this is another u, and they multiply. So let's write this as u squared. On the bottom, you solve the u squared minus 1, and then times du. Alright, just like many times before, we can subtract 1 and then add 1. So subtracting 1, u squared minus 1 over u squared minus 1, that just gives you a 1, and then you have to add 1 back, so plus 1, right? And then over the same denominator. Alright, this, we can do partial fraction decomposition really quickly, and I'll show you what the standard form is for this. It's a natural log of 1 minus u over 1 plus u, and we've actually touched that before in question 89 when we dealt with the root over the, But I'm going to show you, this is the most basic and condensed form for it, and I'll show you how that works. Okay, and you can derive a formula for this one, of course, but I don't. But most people just do the partial fraction decomposition. You can call it standard. You don't need to. PFD. You want 1 over u squared minus 1. You can factor it into u squared plus. Sorry, no, not u squared plus 1. U plus 1, and then times u minus 1. So you want a constant term over your first guy, and then a constant term over your second guy, right? Okay, now we can do cover-up method. For this denominator to be 0, we want u to be equal to -1. And then we cover this one up, and then plug in a -1 into the second one right here. -1 minus 1 is -2, therefore a is -1/2. Alright, and then right here, for this one to be equal to 0, we want u to be equal to 1, and cover this factor up right here, and then you get this left. 1 plus 1 is 2, 1 over 2 is 1/2. So therefore b is equal to 1/2. Alright, now let's rewrite this. I'm going to distribute the 2 in, right? So we have integral of 2, and then, alright, so you broke this guy into this, and which is equal to that. And you can just plug in a and b. So let's do b first because it's positive. This is 1/2 over u minus 1. However, notice that you're going to distribute the 2 in. 2 times 1/2 is just 1. So you get 1 over u minus 1. And then secondly, you have the a, which is -1/2. Once again, distribute the 2 in, you get -1. So you're subtracting 1 over u plus 1. And then multiply by du still. Alright, and all these are, you're able to integrate now. First term, you get 2 times u. And plus 1 over, well, no, sorry, no. If we're going to take the integral of both of these terms, the top is the derivative of the bottom. Therefore, du over u gives you natural log of the bottom. Same idea with the second one. I'll just write it down really quickly. I'll show you like this, right? Okay, and this time let's combine the natural logs. And for this first term, I'm going to write it in terms of x again. Notice that u is equal to root of 1 plus e to the x, so I'm going to write it like that. Okay, and then now combining the natural logs, this is positive, right? So it goes in the numerator. You get a u minus 1 in the numerator, which is root of 1 plus e to the x minus 1. And then in the denominator, you have this one, u plus 1, because it is negative on the outside. So root of 1 plus e to the x plus 1. Now, I'm pretty sure, well, let me think. Yeah, I'm pretty sure this is always positive. So, get rid of these. You don't need them. Parentheses. Yeah? Okay, now what you can do is you can multiply a conjugate in the bottom. The bottom you have 2 plus, well, what do you think? You just have e to the x on the bottom. Should we do that? Is it worth it? Let's actually give it a shot and see how it goes. I'm not completely sure. Let's work on this alone and then simplify it algebraically. I didn't actually go over this beforehand, so root of, so the conjugate of the bottom is well, yeah, it's exactly the top, right? So what we can do is we can just square the top, 1 plus e to the x minus 1 squared, and then the bottom, what you get is this first term squared minus the second term squared. First term squared is just 1 plus e to the x without the root. Second term, and then minus the second term squared is just minus 1. So you have 1 plus e to the x minus 1. So the bottom just becomes normal e to the x. And of course, because this is a quotient, what we can do now is you can break it up, right? You have natural log of the top, root of 1 plus e to the x minus 1, right? Squared, but then we can bring the, well, yeah, let's bring the 2 to the front. And then minus ln of e to the x, because e to the x is in the denominator, that's why you have the minus, but then ln of e to the x is just x. Alright, so I'm going to do a little bit of extra math to see if you're able to do any more simplification with this first term right here. Squaring this, you get first term squared times 2 times this times that. Well, so you have minus 2 root of 1 plus e to the x. And then you have the last one squared plus 1 again. Sorry, plus 1. Yeah, I don't see much you can do with this, so I'm guessing this is the simplest form. Alright, so figured out that this down here is equal to this right here, right? So let's rewrite it. We have, let's put down this first. 2 times root of 1 plus e to the x. Let's put down, yeah, let's just do it in order. Plus 2 times natural log of root of 1 plus e to the x minus 1, and then minus x. Add c, and yeah, that's it for number 98. Okay, my black pen's almost out. I'm going to switch out my black pen for this last question, actually, also because it's staining everywhere. So yeah, give me 1 second. We have 3 more if you want to count the bonus one. Number 99 is integral of square root tangent x over sine of 2x dx. How would you do that? Well, I mean, first obvious choice is to make it such that all of the arguments of all the trig functions are the same. Let's just write it all like in terms of x. So let's expand out the sine of 2x. Expanding out sine of 2x, you get 2 sine x cosine x. And then you have the root tangent x dx. Now, what can we do next? I wouldn't recommend breaking the tangent up into sine over cosine. I've tried that before. It didn't work. Maybe you can get that to work, but I wouldn't do that. Let's think of some smart substitutions we might be able to make. Since, well, let's first take the 2 outside, right? So it's not bothering us on the inside. Okay, if you lay u equal to the inside of the root, right? Tangent x, you get root of u, which we're probably able to sort out later on. So you have root u, right? If u is tangent x, then what our differential will be? Secant squared x dx, right? If we have a secant squared x, well, I mean, on top, then, if we have, no. Okay, so, yeah, let's just write this out. I'm not going to walk you through the thought process. Let's try out u is equal to tangent x. Du would therefore be equal to secant squared x dx. Now, before we go on, because some cost fallacy is going to rip us apart later, will this work? If you divide secant squared on both sides to isolate the dx, you get du over secant squared. Notice how if you replace that, you now have a cosine x times secant squared in the denominator, which is, cosine x times secant. Well, 1 over cosine times cosine is just 1, so they cancel. You're left with 1 more secant, and you have a sine, right? So you have sine times secant in the bottom. Well, if you remember from a long time ago when we did sine x, secant x, tangent x, sine x, secant x is just tangent x. So at the end, we're actually able to rewrite everything in terms of u, right? So yeah, let's give it a shot. 1/2 times the integral of, remember we replace this with u, and then we have sine x cosine x. So, and then we also have to divide secant squared on both sides, so we just have du over secant squared x. One of the cosines cancels with one of the secants, because they're reciprocals of each other and we're multiplying them. So you just end up with a sine x secant x. On top, you have root u du. Sine x secant x is a tangent x in the denominator. So let's put that down. Yeah. We on the top we still have root u du. We still don't have everything in terms of u, but u is tangent x. Let's just replace the bottom with the u. Alright, this looks so much better now because we're able to divide both the top and the bottom by root u, take the 2 inside, well, root u divided by root u divided by root u is just 1. We took the 2 inside, and then u divided by root u is root u. This is now the standard form for the square root of u. So let's replace this with just root u. And then, one last step, u is equal to tangent x. So at the end, you get this whole thing is equal to the square root of tangent x plus c, box it, and you're done with number 99. Pretty interesting, right? Okay. Alright, that's number 99. Let's do, number 100. And we're almost done. We actually have a bonus one we can do afterwards. Number 100 is a bounded one because it is number 100. We have 0 to pi over 2 of 1 over 1 plus sine x dx. Alright, well, to deal with this one, I would multiply the bottom by the conjugate 1 minus sine x, right? So that way you get 1 minus sine squared x, and you're able to deal with more trig functions too. 0 to pi over 2. The bottom, 1 minus sine squared x. You multiplied in a sine squared, 1 minus sine x on both the top and the bottom to get this thing, so we have to multiply it on, we have to represent it on top too. This thing is now cosine squared. And we are able to break up the fraction like this. So we have 0 to pi over 2. And then 1 over cosine squared is just, well, secant squared. And then our second fraction, we subtract off sine over cosine squared. Now, feel free to make a u substitution if you'd like to. However, I feel like the better option would just to be recognize that you can break it up into sine over cosine times 1 over cosine, right? Think about it. Sine over cosine is tangent, and then 1 over cosine is secant. So you have tangent times secant. So this is secant x, tangent x, and then multiply by dx. Finally, you're able to integrate both of these. They're both very standard, very nice. Integrating secant squared, you get tangent. Integrating secant x tangent x, you get secant. And then plug in bounds, 0 to pi over 2, yeah? Okay, then final move is to evaluate this at pi over 2 and 0. First of all, notice, well, actually, you know what? Notice that this is improper. Plug in pi over 2 at both of these. It's both undefined. So let's do some trigonometric manipulation to make it such that we're able to plug in pi over 2. First step is noticing that, well, both of these have a denominator of cosine, right? This is sine over cosine. This is 1 over cosine. So let's combine it. We have sine. We have sine, right? Minus 1 all over cosine. Right, and then all over cosine. And what if we multiplied, well, okay, first of all, let's make this 1 minus sine x by multiplying a negative, because I feel like it's easier for us to think about it that way. Okay, and then now, don't forget the bound, 0 to pi over 2 for that one, and then 0 to pi over 2 for this one. Multiply a 1 plus sine x on both the top and the bottom, you know, because that's our conjugate, right? And then on the top, you get a cosine squared, and that's able to cancel with the cosine on the bottom. So just think ahead a little bit, and it'll help show you what to do. So 1 minus sine squared, right? And that is just cosine squared. So on the top, I'm just going to simply replace this with cosine squared. On the bottom, you have your little cosine x here. Remember, we multiplied in the conjugate on both the top and the bottom, which is 1 plus sine squared. So I'm going to multiply in a 1 plus sine squared. No, sorry, no, not sine squared, just normal sine. And then don't forget, we're evaluating 0 to pi over 2. We're not done with the trigonometric manipulation. Notice that you can cancel this down here with that up there. So this is just negative cosine x over this is all that's left. Alright, now try plugging in bounds. Plugging in 0, cosine of 0 is 1. Well, let's plug in pi over 2 first. Okay, so cosine of pi over 2 is, cosine of pi over 2 is 0. And actually, no, we don't need this because if the top is 0, then everything's going to be 0. So this pi over 2 is 0. So now all we need to do is subtract off this thing evaluated at 0. So we have a negative. Cosine of 0 is 1. 1 plus sine of 0 is 0. So two very important things. These two double negative, they cancel. Finally, 1 over 1 plus 0. 1 over 1 is just 1. So that gives us 1. And we are done. This bounded integral is equal to 1. And I guess you can call this the finale of sorts. And I think it's pretty satisfying, 1. However, we do have a special guy at the end, so we're not done yet. Let's do one more question. Question number 101. Okay. So, for 101, we have integral, indefinite, once again, of sine x over x plus natural log x cosine x. Now, this one, think about it a little bit. You might be able to recognize it. It looks like product rule, right? You have derivative of sine x is cosine. Derivative of natural log of x is 1 over x. So you could just say that, well, we use product rule. This is u v prime. This is v u prime. But if you want to use more traditional integration techniques, well, I mean, how are you going to do that? None of these, I don't think either of these are elementary, right? So, yeah, none of them are elementary at all. How would you do this? Well, let's break it up first. We have integral of the first term, sine x over x dx, right? And then we have the integral of the next term, ln x cosine x dx. For this one, I wouldn't use integration by parts, because that's just going to get you something that looks very like this. In fact, you can use integration by parts on both of them. However, I would instinctively do this one since you are able to differentiate natural log of x and integrate cosine x very nicely, right? So let's do the DI method once again for the very last time. Differentiate ln x. This becomes 1 over x. Integrate cosine x. This becomes sine x. Multiply the diagonals and integrate the rows. So our first function stays the same. Integral of sine x over x dx. Second function, let's put down the minus sine x over x first. Sorry, and this is actually under an integral sign because it is a row, right? So we're integrating. And then let's put down the diagonal. Natural log of x sine x. Okay, now this minus itself, it cancels. These two cancel to make 0. So you're just left with the antiderivative, right? You never needed to evaluate either of these in the first place. Just do integration by parts and you find that this cancels with itself and you're just left with something that's outside of an integral sign. Yeah, really, really cool. So you're left with natural log of x times sine x plus c, and you're done with all 101 integrals. All right, yeah. That was fun, wasn't it?